Check. Yeah. I just start. Yeah, I think so. Yes. Okay. Okay. Hello, everybody. And well, welcome back to the second day of this conference. On behalf of the organizers, I have just one small announcement to make before we start. We would like to remind everybody that there is today's outreach event, and if you want to attend it, please take a minute to register on the web page of the conference. There is the link. You should go there, register in order to be able to attend this afternoon's outreach event. Okay, please do. And now I pass the microphone to the chair of today, Boris. Thank you.
Thanks, Michele. Good morning. It's a pleasure to chair this morning session. I'd just like to take this privilege to make a very brief personal statement, not endorsed nor even authorized by the organizers, which is to draw your attention to a petition which has been circulating for a few days about the appalling humanitarian situation in Gaza. The petition was initiated by our colleagues in TIFA Mumbai, and it has garnered over 2,800 signatures over less than 6 days, and it includes several Nobel Prizes and Fields Medals. It's open to any scientist with an academic affiliation, from PhD student to retired professor, all fields of science, including humanities. If you have not received it, and if you would like to get it, please feel free to send me an email, boris.turlin@gmail.com, or ask any of the colleagues in this room who have signed it. It will be soon announced publicly. Without further ado, let me introduce the first morning speaker, Samir Muti from King's College, telling us about black holes and their microstates. Thank you.
All right, thank you very much. Can everybody hear me in the back? Okay, I'll try to use this screen. I don't know, this will be on anyway. So thank you very much for the invitation. It's my first time in Sweden, and I've been enjoying it a lot so far. I should begin by congratulating the organizers for putting together such a wonderful and exciting conference. So far, it's been smooth sailing, and I know that that requires a lot of work. Also, I should say that I really enjoyed the poster session yesterday. All the posters were very clear, very professional, and very informative. So well done to all the participants. So I was asked to give a review on recent developments in black hole thermodynamics. Now, this is a large subject, and in fact, in the last few years, it's seen remarkable developments along different fronts. And I will be talking about a set of related subjects which I try to tie together in this title, near extremal black holes and their microstates. And I should say that there are other developments which I will not cover, both because of lack of time and because I don't feel particularly qualified to do so. Notably, the relation between black holes and operator algebras, and also about the dynamics of near extremal black holes. Okay. So in the first 10 minutes, I'll try to give an overview. It's an hour's talk, so it might get boring. So please do interrupt. That'll make it more lively. I'll try to pitch it basic, at least in the first half hour. In the first 10 minutes, I want to give an overview. And because it's basic, I'm sure, because I know some of you, that many things I say will be well known to one or the other of you. So in which case, feel free to make advanced comments. That's also very nice. Okay, so let's start. So what's a near extremal black hole? So by that, today we mean this. Consider a black hole carrying mass and charge. Okay. We could also consider spin, but for most of the talk, I will not do that. Maybe I'll give some comments later. And all the statements I make applies to a large range of theories, but in order to be concrete, I'll take as a running example just Einstein-Maxwell theory. Okay, so general relativity coupled to one gauge field, and consider a black hole solution with mass and charge. When I talk about other theories, I'll try to say it explicitly. So this is a well-known solution, the Reissner-Nordström solution, and it has two horizons given by this easy formula. I've put G Newton to 1 here. And that's the temperature. The temperature is proportional to the difference between the positions of the two horizons. And it's clear from this formula that the mass has to be greater than or equal to charge. And when the mass when the mass approaches the charge, the two horizons approach each other, and the temperature goes to 0, and that's called the extremal limit. So when the two horizons are on top of each other, we'll call that an extremal black hole, and the temperature is 0. And when temperature is close to 0, we'll call that a near extremal black hole. I should say that in the extremal limit, the event horizon radius is given by Q, so that's our parameter. And that also sets the scale. The curvature of the horizon is inversely proportional to Q square. So when I say something is small, when the temperature is small, I mean with respect to that scale. Now, why are we interested in near extremal black holes? Now, there are many reasons. Maybe many of you have many reasons. Well, firstly, you could say, well, because they're there, we should study them as theorists. Here's the solution. They're also there up there in the case of spin. So there are spinning black holes, which carry a lot of spin, and they also approach extremality. Okay, this is this black hole survey that we've seen. Today, my reasons are twofold. So firstly, at very low temperatures, when the black hole is near extremal, quantum gravitational effects are enhanced. And we've learned in the last few years how to treat this quantitatively. Okay, we can do calculations. So that's my first reason. And secondly, one of the big successes of string theory is the explanation of microscopic black hole entropy. And mostly, not always, but mostly, that has to do with the situation that you discuss is always extremal or near extremal black holes. So we want to revisit that in light of these new developments. Okay, these are the two things we want to discuss. Okay, now let's say t is small. So then instead of m and q as parameters, I could take q and t themselves as parameters. And you can ask, what's the area of the event horizon? That's the entropy. And you get this formula. Okay, when t is 0, the radius is q. So the extremal entropy is pi q square. And then you have corrections. So that's the first order correction in t here. I've put back L Planck. And then there's a systematic series of corrections. Okay. That's very easy to do. And you see here the appearance of a certain energy scale. And I'm going to call that 1 over E gap. Okay, so that energy scale I'll call E gap. Okay, that's set by the black hole. Any near extremal black hole has such a scale. The details really depends on what black hole you're considering, but roughly it'll scale as an inverse power of the entropy. Okay. Now, this picture that I present here of the semi-classics has been the state of the art for many years until recently. But there's something about this that should bother us, and it has bothered many people, namely that it's very different from what we are used to in usual quantum statistical mechanics. So you have a large system, and when you take the temperature to 0, usually we expect that the number of degrees, the entropy, goes to 0. This is the so-called third law, in quotes, of thermodynamics. It's more of an expectation coming from quantum mechanics. That unless there's a symmetry underlying the system, there's one or a finite number of ground states. Okay? This can be made more precise, and in fact, this was done in this nice paper by Preskill, Schwartz, Shapir, Trivedi, and Wilczek back in '91, that something must go wrong at low temperatures. And roughly the argument is as follows. So when the black hole has high temperatures, then, so let's say it has some energy above extremality, and then you consider the process of Hawking radiation. So there's a small Hawking quantum that is emitted, and then the black hole will sort of decrease its energy just a little bit, but that process is essentially continuous. It's an adiabatic process. And so you can write the Hawking rate, and you can ask what's the decay rate, and then integrate this equation. Okay, that's what we learn in school. But when this energy becomes very small, at some point, it's going to be comparable to the size of the typical quantum of the Hawking radiation. And in that case, let's say it's twice the Hawking radiation, then emission of one quantum will drastically change the quantum state of the black hole. Let's say E goes to U/2. Okay, so clearly the adiabatic approximation is not true. And moreover, if it's really small, you could also have quantum fluctuations. If you just naively do what we do at high temperatures, there's a Hawking quantum which takes you below extremality. You could emit something which is larger than the gap. Okay, and that of course violates all kinds of ideas and expectations from classical general relativity. Okay, so that was the basically what the puzzle that was presented here. Okay, now what we've learned in the last few years is that this picture is dramatically modified. This picture is completely incorrect. Okay? And in fact, a near extremal black hole is like an ordinary quantum system. And when temperature goes to 0, the density of states actually goes to 0. Okay? And the reason we've been able to make this kind of statement, the technical engine, is the discovery of a certain light mode, nearly gapless mode, which lives near the horizon of the black hole. Collectively, so it's a set of modes called the Schwarzian modes, which we've learned how to quantize. And so that's the driving force, the technical engine, that allowed us to make such calculations and such statements. Okay. I want to note that when Q is large, the horizon of the black hole is weakly curved. Okay, so the regular dimensional analysis will say that 1 over Q squared is small. Nevertheless, the quantum effects are large because there's a new scale which appears, which I hinted at, which was this E gap. Okay. The strongly coupled mode that appears. So today what I want to do is, the first half, I want to just discuss what I just said. Okay, I want to explain what is this nearly gapless mode, what is this density of states, and what's the mass gap. Okay, the first half will be, many of you would have probably heard about this, but I thought it doesn't hurt to review it. Okay, review it from a slightly, from a point of view which maybe not all of you have seen. That's how I got into it, so that's how I'll present it. Then I want to discuss some consequences on supersymmetric black holes, on Hawking radiation, and if I have time, then perturbative string theory. And then in the last 20 minutes, I want to revisit black hole microstate counting and string theory, okay, with in view of these developments. Any questions about the plan or the idea or the basic points? All right, so let's, sorry, what time did I start? I'll just put a, I'm 10 minutes, okay. Let's put a timer. Okay, so let's start with the nearly gapless mode. So how does this appear? So let's begin by framing the question. It's getting hot. So we often hear about the black hole Hilbert space. You would have heard these words. What do we mean? Different people mean different things, and it depends a little bit on the situation. But more or less, what everybody means is the following: that imagine a universe with some time direction at asymptotic infinity. So you have the notion of a Hilbert space, a Hamiltonian Hilbert space, and inside that you have a black hole solution. Okay, so consider such a situation and imagine there's only one black hole, and then we have this idea that there's an inside and the outside of a black hole, and this is the quantum mechanical analog of that the full Hilbert space factorizes into the black hole Hilbert space and outside. Okay, that's roughly what we mean. This is the zeroth order framing. So this is like what you would do when you have, let's say, a cold atom or a molecule, a bunch of things, and let's say they're separated from the rest of the environment. You'll say that's the Hilbert space, and then there's everything else, and there's a weak interaction. Okay? The difference, of course, is that the black hole Hilbert space has a huge dimensionality. It's equal to the exponential of the entropy that we just saw. All right. Now, what we want to do today is to ask whether this picture is correct. All right? Now, clearly when t is large, this picture is clearly wrong. It's at best an approximate picture. It's wrong because there's Hawking radiation. Okay, there's the horizon of the black hole, and there's quanta which is constantly being exchanged between the black hole and its environment. There's pair creation. So there's no sense in which you can say this degree of freedom belongs to the black hole and that one to the environment. Okay, and the correct description is clearly the canonical ensemble. We have a heat bath in which the black hole is in equilibrium. Okay. I should make a caveat here that if you go to, let's say, 2 or 3 times the event horizon size, and if you look at the potential which a particle feels when falling into the black hole, there's a sort of hump to the potential which is peaked around 2 or 3 times the black hole horizon size. And if you take your system, the inside of the system, to be that much of space, then essentially the gray body factor can be made very small. So there's radiation going out of the black hole, but if the hump is very large, then very little of it leaks out. Then more and more it becomes like a molecule or an atom, okay? Except, again, that it has a huge dimensionality. Okay. All right. Was there a question? No. Okay. Now let's see what happens when you take the temperature to 0. Okay. So in the semi-classical theory, so again, I'll work with this effective low energy theory. There's Einstein-Maxwell theory. So in the semi-classical theory, as we all know, the black hole develops a throat, a very long throat close to the horizon, and that's given the near horizon configuration is ADS 2 times S2, and the gauge fields take up has a constant electric field. Okay, that's the near horizon, and that's connected by a long throat to the asymptotics. And when t equal to 0, let's just do semi-classical physics. When t equal to 0, this near horizon geometry decouples in the sense that in its own right, it's a solution to the equations of motion. I could have never told you about the black hole and just said, consider Einstein-Maxwell theory, and that's your solution with good asymptotic boundary conditions of ADS2. Okay. It's fixed completely by the charges. Okay. And in particular, even when the theory is more complicated, like supergravity, when you have scalar fields, and there are asymptotic data which typically participate in the full solution, the near horizon geometry does not depend on this asymptotic data. This is the famous attractor mechanism of Ferrara-Kaloshin-Strominger. Okay? Very good. So that's the sense in which semi-classically the black hole, the near horizon black hole, is decoupled from the environment. Okay. Now, the question we want to ask is this true quantum mechanically? Because I'm trying to make the question more and more precise. Is this true at the quantum level? Okay. So the way I'm going to answer this question is as follows. So what could go wrong? Well, I said that when you take t goes to 0, there's this long throat which attaches the near horizon and infinity. Now, there could be degrees of freedom in that throat which don't quite decouple. That's the main idea. And the point of view I'll take is not to postulate any type of degrees of freedom, but instead work from inside the black hole. So I'm going to take this point of view that semi-classically, there is this ADS 2 times S2, and now I'm going to quantize this system. Okay, this is a point of view which was proposed by Ashok Sen about 15 years ago while trying to calculate quantum corrections to this black hole entropy. Okay? So the idea was that you have this ADS2, let's think of ADS2 CFT1 and try to quantize it. Okay? So how would you do that? You have ADS2 boundary conditions, ADS2 times S2, it's a 4-dimensional theory, and you have all the fields of gravity, and then you have to put some appropriate boundary conditions on ADS2. That is well known by the rules of ADS CFT. What are the fall-off, what are the decay conditions to put? And then you have these fluctuations, and you have to integrate over all this field space with the action of gravity or supergravity or what have you. Okay? So almost all of these modes, when you do this kind of path integral quantization, almost all of these modes, the action of these modes, which are off shell, are given by set by the characteristic scale of the black hole, which is just Q. Okay? So that's how you do that. Now, the subtlety is that, in fact, that is not quite right. There are there's one family of zero modes. Okay, so just by the effective action, I just mean Einstein-Maxwell theory. When you quantize this, what you find So there are always these set of so-called pure gauge modes. So this is just harmonic analysis on Euclidean ADS 2 times S2. This is a very nice article by Camporesi and Higuchi. They do harmonic analysis on ADS space and spheres, and you can put it together. And what you find is that while in higher dimensional ADS2, they write down what all the harmonics are. For ADS2, there is something very subtle, namely that there are these pure gauge modes. So what does that mean? So imagine ADS2 written like this has the hyperbolic disk. So rho is the radial coordinate with this kind of metric. Then you consider a coordinate transformation, a diffeomorphism, which asymptotically looks like this. It's labeled by integers except 0, plus, and minus 1. Okay? So it's some kind of coordinate transformation that you do here. And then you ask, what's the corresponding gauge field, in this case, the metric? Okay, so that's the usual formula that you would write. Now, if you've not seen this before, you should say, why are you considering this? Of course, there are gauge transformations, and we always throw away pure gauge modes. Now, the problem is that because the space is non-compact, there's a normalizability condition that you need to put. And these gauge modes are not normalizable. Here I wrote to you what the gauge mode is close to infinity. You can see it's a constant, and therefore it's not normalizable. Okay, it goes as e to the I and tau. Tau is the time direction. Okay, but when you differentiate it, then that gauge field or the metric is normalizable. Okay, so another way to say it is that if you think of the gauge parameter as the ghost is not present in the spectrum of the theory, but the gauge field is, and that makes it physical. Okay, the ghost does not run in the loop to cancel it. Okay. However, because formally they're pure gauge, the action is 0. Okay, that's the reason why there's 0 modes. Okay, these are physical 0 modes of the theory. Okay, you can write it in a better way. You can collect all these modes into one field, which I'll call epsilon as a function of tau, and then write down what this is in terms of this one-dimensional field. Okay. Again, I emphasize that these 0 modes are physical, and in fact, they've been used. So in the past, in this whole program of SEN, while quantizing the fluctuations inside ADS2, you had to countenance this. So you say, how do I do that? Well, at that time, we didn't know how to do it. So you assumed, so what do you have to do? You have an integral over these parameters epsilon, or this field epsilon, as part of the integral over the metric fields. But the action is 0. So what you're calculating is the volume of field space. Okay, that's a hard problem. We don't know how to do that. It's ill-defined. And at that time, what Sen did was to say, well, let's assume that this volume is finite, and then ask, how will it change if I change the size of the black hole a little bit? Okay, and that is a tractable problem. You can use arguments of ultra-locality of the measure due to Witten, and you can calculate that. What you get is some kind of correction like this, logarithmic corrections to the extremal entropy. So e to the pi q square plus this coefficient here, which I'll call C log times log q. Okay, so that was calculated, and that has been used. It was also used in other methods, like you can use localization to calculate the quantum entropy, and these 0 modes are also important. Okay, so it's definitely physical. Okay, any questions about this? All right. Now we're faced with this. We want to say, okay, there is this volume, but now we can't just throw it away. What if the volume is 0 or infinite? Then the whole problem becomes ill-defined. So we want to do this correctly, and the way to do this is to regulate it. So you give a small temperature, just heat up the black hole a little bit away from extremality, and solve the equations of motion. So the near horizon configuration looks like this. There's this ADS 2 times S2, and there's a linear correction in temperature and higher orders. What does this look like? Well, the leading contribution here, it looks like this. So this is the ADS 2 times S2, when T is 0, the sphere has a constant radius throughout ADS 2. This is the extremal attractor ADS 2 times S2 we're used to. And what this perturbation does is it changes the size of the sphere, and it grows exponentially towards the boundary, okay, with coefficient T. Okay. Now, this should already tell you that something is funny, in the sense that this, by no means is this a good sort of system to consider. You can't put boundary conditions here if your perturbations are growing exponentially. Okay? But what we can do, and that's what we'll use it here, is to use this as a regulator. We'll turn on a T, we'll study the quantum fluctuations of this mode, and then take T to 0. Okay? It's a bit like how we study magnetization, right? Spontaneous magnetization. You have to put an external field, ask how does the system react, and then take the external field to 0, and ask what remains. Okay, that's the idea. Okay, so that's the metric has changed. And now, of course, the semi-classical entropy takes this form, which I showed you in the first slide. Okay, so that's the appearance of E gap. And now you begin to see the meaning of E gap, the significance of this E gap. So these zero modes of pure ADS 2 times S2, which we just discussed in the last slide, pick up a T dependence. The action of these zero modes is no longer zero, because now there's a linear term here. So you'll have a term which is like, let's call the zero modes H, like we did. Then there is a GHH type of coupling when you write the action. And that gives you the first order quadratic correction. Okay, so what you get is something like this. You get that the Einstein-Maxwell action picks up of epsilon of this sort of nearly zero mode has this form. Okay, it's proportional to T because of this background T. And then it has this certain shape. This is a quadratic, quartic in the derivatives. Okay, and you begin to see. So now you might recognize this. So let's make some comments. So this is the thing we'll study a bit. So firstly, you see it's strongly coupled. So when T goes to 0 in units of E gap, okay, the coupling clearly becomes very large. So that's what it means to be nearly gapless or strongly coupled. So that means the quantum fluctuations are very large. And this is the action that essentially controls the coupling of the black hole to the asymptotic region. Okay. Now, when you turn on T, like I said, the whole metric changes. And when you go here, it goes wild. So there are many operators that couple the near horizon and the asymptotic infinity. But most of them in the near horizon were massive. They already had a large energy. Okay. So the correction due to this T will be very small compared to what was already there. So there's a smooth limit. Okay. But it's these ones which had zero action, which now pick up a small action. So this difference is going to be enormous. Okay. So this is the, let's say the leading is the dominant coupling that controls the coupling. Okay, any questions? Very good. So that theory, sorry, I should have said, of course, that it might be familiar to many of you, is precisely what is called the Schwarzian theory. Okay, this may not be how you've seen the presentation. Okay, typically you might have seen some effective two-dimensional theory, the theory of Jakob-Teitelbaum gravity, which is some dimensional reduction, and then you sort of ask what's the correct boundary condition. So this is a way to do this intrinsically from the near extremal black hole. But you can actually just do a change of coordinates. We wrote this in this paper to get back to what you might have seen. This is the picture which I think most of you have seen. So in the picture I presented, the boundary conditions were fixed, okay, of all the fields, and the metric changes when you turn on T. An alternative presentation is that you insist that the metric is always locally ADS2, but the boundary conditions change. So this epsilon mode that I showed you can be put equally into a wiggle of the boundary. So you said that the boundary has fixed length, but its shape is not fixed. Okay, those two are completely equivalent by certain coordinate transformation that I'm not writing. You can read this paper. All right. And in this way of writing it, it's sort of very geometric. What is this mode? This is essentially diffeomorphisms of the boundary. So there's a circle. So there's time reparametrization invariance symmetry at the boundary. And the ADS, so the theory has that symmetry, but the ADS2 solution breaks that symmetry. But the ADS2 does not, you can't change time, you can't reparameterize time at ADS2. So the ADS2 breaks that symmetry. So this is like spontaneous symmetry breaking. Okay. But ADS2 has isometries. It has SL2 isometries. The easiest one we know is just the rotation of the disk. That's L0, and then there's L+1 and L-1. So those are not part of the spontaneously broken modes. Okay, so the system that we're studying is diff of S1 quotient by SL2. Okay? And this action, this Schwarzian action that we saw, geometrically describes the motion of this coset. Okay. I'll come back to this. And in the last 5, 6 years, actually going back to 10 years, there have been many different methods that we've learned to solve this theory. As I said, most of them have been through this two-dimensional JT gravity, but essentially you have to solve this one-dimensional theory. And there are many methods. There's a nice review by Mertens and Turiachi, which you can read. And the result is that this theory is one-loop exact. Okay, so you can write the one loop partition function, and here I gave you the answer. Okay? In fact, this is quite easy to just, if you just want the one loop calculation, you can essentially just argue it out. The reason is that, so think of what you want to do. What you want to do is to integrate over epsilon. So you have all these modes of epsilon, okay, with this action. It's some quartic action. That's not very easy to do a priori. But if you just want the one loop result, then you can use ultra locality. So you say that at high energies, the measure, the Gaussian measure, is such that the integral of the field itself is 1. Okay, that you have to put some condition of that sort. And what we want is the integral over all the fields of all the modes of the field except SL2, except 3 modes. Okay, so the answer is 1 divided by the integral over those 3 modes themselves. But each of those 3 modes are just bosonic modes, and it'll pull down a 1 over square root of t because that's a bosonic mode. And therefore, when you divide by it, you get t to the 3/2 in the numerator. Okay, so it's as simple as that. You can also do it by more sophisticated methods. Okay, so that's the one loop answer. And now I said that. So this theory is one loop exact, and so that's why I gave you this. Thank you. Any other comments, questions? Yeah. So one loop exact is not so easy to argue, but it's still true. Good. So now we want to put this all together. So here's the extremal entropy of the black hole, pi q squared. These were the first corrections, semi-classical corrections. These were the logarithmic corrections to the extremal entropy. And now you have here this T over E gap to the power 3/2 as a prefactor to the partition function. Okay. And the notable thing is, although it multiplies something very large, it goes to 0 as T goes to 0. Okay, so that's what gives the dramatic change. So here is, so if you give the partition function, you can read off the density of states using a Laplace transform, and this is what it looks like. So for large energies, so this is the density of states versus energy above extremality. So large energies, the dotted line is the semi-classical curve. So it goes like that, and then it hits this semi-classical result of e to the pi q squared times the one loop correction. And then you see that at large energies, it essentially follows, the quantum curve essentially follows the semi-classical curve. But at low energies, set by the scale of E gap, there's a dramatic change. And in particular, when you go to T equal to 0, then the whole density of states go to 0. Okay. Yes. Yeah. Can you shout? Yeah. Yeah. Yes. Yes.
Yes. By what some of us had explored.
Yes.
By in addition to doing the one loop Schwartzian localization by Stanford and Witten. But strictly speaking, that's a disk path integral result where there's literally one boundary. And within the limit where you have just one boundary, then you can take t to 0.
Yes.
But however, there's a catch. If you want to consider the full path integral, one cannot take that limit t to 0 because there would be non-perturbative effects because of loop corrections, high genus corrections, which are exponentially small in the black hole entropy.
Yes.
So in that sense, strictly speaking, t to 0 limit is at this level we cannot do because this still is exploring a certain energy level above the ground state. So do you have any perspective?
Absolutely. No, so I would just repeat. So firstly, I hope I refer to the right paper of yours, somewhere here, over there. I don't know if it's something else, you should tell me. But it's a very good comment, which is that, I'll just repeat it. I'll repeat what Upo said, which is that I've been a little glib when I say t goes to 0, because these are perturbative corrections, okay? And there can be non-perturbative effects. Okay? And so very, very close to here, you should stop trusting it. Okay? So somewhere here, so when you have t between E gap to the exponential correction, which is e to the minus the entropy of the black hole. So this is 1 over the entropy to some power, but here you have e to the minus entropy of, right? When you have, let's say, it's the scale of energies where you have 1 or 2 quanta. There you should stop trusting the result. Yeah, did I summarize the comment correctly? Thank you. Okay, that's a very good comment, and in fact, thanks for I should have said that. Thanks. Okay. Other comments, questions? All right. Okay, so here you see this. By the way, this plot is from this paper. So this whole, if you want to sort of see this development with Luca Liusiu and Joaquin Turiachi, we wrote a paper in 22. We wrote two papers. One is called Revisiting Revisiting Logarithmic Corrections. All of this is contained in that if you want to read it in detail. This plot is from this paper. And now we can repeat this for supersymmetric black holes. And for supersymmetric black holes, yeah, so here I should say that the semi-classical intuition is strongly corrected. For supersymmetric black holes, now in this throat region, you have more light modes. Because you have supersymmetry, you have supersymmetric partners of the Schwarzian. So you have to quantize the whole system. So there's the Schwarzian modes, the SL2 modes, there's fermionic superpartners, and also bosonic superpartners. There's a bit of a story here, which I will not tell you unless you're interested later. But roughly speaking, there's an exact cancellation between the bosons and fermions. And instead of t to the 3/2, you get t to the 0. You get 1. Okay? So for supersymmetric black holes, the naive semi-classics plus sort of extremal loop corrections is correct. Okay? So now it looks like something like this. Okay? When you draw the density of states, so again, that's the semi-classical picture is the same for supersymmetric and extremal black holes. But now the quantum density of states is completely different. So here it follows it. And then instead of going to 0, at 0, there is all the states of the black hole. So that's what this is like a delta function. That's what I mean by this. And then there's a mass gap. There's an energy gap. Okay. So another way to, one sort of slightly loose way of thinking about it is that semi-classically, there's a lot of states near the horizon of the black hole. But quantum mechanically, these states sort of spread out, because of perturbation theory, spread out and merge into the continuum. That's for the non-supersymmetric black hole. Okay, this merge here. While for the supersymmetric black hole, they really clump up exactly at 0 energy, and then the continuum begins after an energy gap. Okay, so this is important because now it means that this supersymmetric black hole is actually decoupled from the environment with a gap. Okay, this was one of the worries which people had long ago when Strominger first wrote this. But at that time, it was sort of such an advanced question. People are just beginning to find the matching that it took a while to understand this. So you could ask in the Strominger calculation, there's some microstate counting of BPS states, and then there's a BPS black hole. But if the black hole is not decoupled, then you should not really think of it as an independent quantum system. Okay, so is that really true or not? And now we see with these calculations that indeed the supersymmetric black hole can be thought of as an independent quantum system. Okay, so that finishes the first half of the talk. Any questions or comments? Okay. Then let's move on. So now I want to flash some applications, and now I'll change style a little bit. Instead of a development, I want to show you some snapshots. Okay, so I don't expect everyone to understand everything, but ask questions, or you can also ask me questions later. Okay, so there'll be 3 applications I'll give. The first one is to the exact entropy formulas of supersymmetric black holes. Okay. So 12 years ago, Ashok Sen had started this idea of trying to calculate quantum corrections to the entropy of a black hole. And we had pushed it to using methods called localization to calculate all quantum corrections. Okay. Of course, now because of this decoupling of the black hole that has been put on a solid footing. But in fact, there is a little more that the Schwarzian is useful for. So the way this went, I'll give you a very brief snapshot, is that you had some microscopic counting. This is called d micro in string theory. There's a number of states, there's an integer. And using methods from analytic number theory, this is the type of thing Lawrence was discussing yesterday. It's called the Rademacher expansion. There's a way to write this as an infinite series of analytic functions. Okay, that's a Bessel function. Okay. And now the idea is that you think of this ADS2 CFT1, and this is really the partition function of the black hole, okay, of the ADS2 black hole. Now we want to interpret this. You want to check whether this is true. And that's what we've done. And basically, this part of the formula you could derive from this all-order fluctuation analysis that's using some localization, lots of methods. In fact, there's a whole many works here, and that you can using that you can capture this. The sum over C itself, I should have begun with this. The sum over C itself are interpreted as orbifolds of ADS2, some ZC orbifolds of ADS2, and you see that the Bessel function asymptotically goes exponentially. So higher C is exponential corrections. Okay, so that's that. And here there's this thing is called the Klosterman sum. We also saw that yesterday. It's a sum over phases, and that also could be accounted for by certain Chern-Simons theory on this orbifold. And I've divided, then what remained was a power of C. C is just this number. And I've divided it into 7, it was 9/2, and I divided into 7/2 and 1 over C to show that actually this part is actually the one that's captured by the localization. At C equal to 1, you can't tell because it's 1. But it turns out that what was missing in this old analysis was this 1 power of 1 over C. And that's exactly what we find is the volume of the space of this super-Schwarzian on the orbifold. Okay? So I just wanted to flash this to tell you that this Schwarzian is actually doing some job. It's not just some philosophical thing which helps you to say that it's decoupled. Okay? So it's a very tiny contribution. Okay, another contribution, the second, I'll call this 1B application is the following. So the context is like this. So consider this ADS2 times S2. So these are 4-dimensional black holes. These are spherically symmetric, and they have 0 angular momentum. Okay. Now, by spin statistics, 0 angular momentum means 0 fermion number. Okay. Now we think of this black hole as an ensemble of quantum states, as a collection of quantum states. Okay. Then, and the statement in supergravity that this black hole has 0 angular momentum means that on an average, this ensemble has 0 angular momentum. Okay, that's what gravity is like the average. But now you run the rules of ADS CFT, and you find that at the boundary of ADS2, if you think of any gauge field, there's always 2 legs. And in 2 dimensions, the order is flipped. It's the field strength that dominates in 2 dimensions rather than the potential, unlike higher dimensions. So the natural ensemble here is microcanonical. So that means you have to fix the charge. Okay? Unlike higher dimensional ADS where you fix the potentials. Okay? Now you put these 2 statements together, that on an average, the charge is 0, but every state in the ensemble carries the same charge. That means that every state has charge 0. Okay? So that means that every state is bosonic. Okay? So this is a vanishing theorem that we had developed. And what it means is that trace of -1 of the F is actually equal to trace of 1. Okay, so we developed this about 15 years ago. And now the new thing is that because now you have the Schwarzian mode, we missed this 0 mode, you have to repeat this argument. I won't show you the calculation, but you can do that. And again, using this density of states, you can show that only J equals 0 contributes. Okay? So this Schwarzian, if you want, is like something like a skin of the black hole. It's a very thin layer sitting on top of the black hole, but it's very floppy. It's the one that connects you. And because it's very floppy, its effects multiply everything that goes on in the bulk. Most of the entropy and all these arguments comes from the bulk, but there's a small contribution that's very important. All right. The second application is to Hawking radiation. In fact, this was the first puzzle that that I presented you with. So these are plots from this paper, and Luca kindly gave me these plots that I'm allowed to show. I mean, it's from the paper anyway, it's published. So this is a plot now of the rate of Hawking, so dE over dt d omega as a function of omega. Omega is the frequency of the scalar, of the field that is emitted. Okay? And so they call, what I call E gap, they call E breakdown, E break. And when the initial energy of the black hole is large, 100 times the E gap, then you basically are very close to the semi-classical picture. But in the quantum regime, when the initial energy is 0.1 times the gap scale, there's a huge correction. There's a very strong correction, exactly like we saw for the density of states. Okay? So the Hawking radiation formula, semi-classical formula would be this, but that's completely incorrect. And instead, this quantum correction goes like this, and it stops. And that's very important. That's the fact that saves you from going. This puzzle that was seen by Preskill et al., this is the thing that allows you to evade the puzzle. Okay. There we go. Okay, so it affects the low temperature radiation and resolves this paradox. Okay, you can also do, so I call this 2A, and 2B is the opposite of it, which is instead of Hawking radiation, you can ask about absorption. You take a black hole and throw something in. You can ask, what's the cross-section of absorption? Okay. So at very low energies, if I have an extremal black hole, and I throw, let's say, a scalar wave at very low frequency, then essentially the absorption cross-section is the area of the black hole. Okay, this is well known. So that's this black line. And the red line, these are plots from, so I should say there's lots of works here. Roberto Emperan, Anna Biggs, Emperan Trezzi, who's here in the audience, and he had a very nice poster yesterday about this, and also this paper. So these red lines are the quantum corrected curves, and as you go close to extremality, you actually go upwards. It's slightly counterintuitive that the absorption cross-section increases. So the density of states inside the black hole actually decreases. So that's one effect of the Schwarzian. But in fact, the absorption, so transition amplitude itself is also affected by the Schwarzian, and that's affected in a positive way. So these two things play off, and in fact, overall, you get an increase. So that's one point. And the other point to note is that there are these kinks. I'll just check the time. Okay, let me just explain briefly why these kinks come. I should have said something long ago. So here, when we saw these pictures, so that was the semi-classical. Here I showed you the overall density of states, but you can do something slightly more refined. You can ask, what's the density of states for a field of a given spin? Okay, it turns out that there's a classical gap, which is J is the spin, J times J plus 1. So this is spin 0, it starts here, and then spin 1 starts like that, and spin 2 starts like that, and so on. Okay, there's a gap. While for the supersymmetric black hole, there's an intrinsic gap even for the spin 0, and then there are further gaps because of the spin. Okay. So why I said that? It's because that explains these kinks. Sorry about this. There we go. So these kinks are precisely when you hit one of these new spin modes. It's like a new channel of scattering or absorption. Okay. So that's that. Here is scattering in supergravity. You see that now there are lots more channels because there are more fields. Okay. Here is a plot of the probability of absorption when the initial state is the BPS state, is the extremal state. Okay, and now you see something interesting. You remember that for the BPS black hole, there was a mass gap, there's an energy gap, and therefore if you send a scalar or a wave of very small energy, less than the gap, then it should not absorb because it's by the Fermi rule. And indeed, you see this gap also in the absorption probability. Okay, so this is called quantum transparency. Okay, I'll move. Okay, I've done 45 minutes. I'm going to skip this. I'll just flash what the other, there are many other things I just thought I'll give you, but I'll give you the keywords and you can ask me later. So one of them you can ask is, I won't have a discussion. One of them is, okay, all this Schwarzian was a discussion in gravity. What happens in string theory? Okay, so in perturbative string theory, so that's one question. You can ask which superalgebras, this might be of interest to many of you here who study string spectrum and so on. You can ask which superalgebras arise. You can ask, so the discussion so far was close to the black hole. You can ask what happens to the Schwarzian modes far from the black hole. And then you can ask what happens when there is spin. And there's some interesting comments, but I want to skip this in view of time and move to the next topic. And later we can come back to that if you want. Okay, so now I want to sort of switch gears and discuss supersymmetric black holes in string theory. Let me pause if there are any questions about what we discussed. Okay, spin, let's postpone spin to the questions. So that was one of the things. It has been, so very briefly, so it has been, you can repeat this kind of analysis that we did also for spinning black holes. But there's actually something you have to, let me make the comment. You have to be a little bit careful because there's this classical super radiant instability for spinning black holes. And later I can show you, can quickly derive on the board, but roughly speaking, what happens is that unlike charged black holes, where the Schwinger decay process is exponentially suppressed, for spinning black holes, the superradiance of this decay process is not suppressed, and therefore you have to ask, how do they compete? And it turns out that they compete, the time scale of decay is comparable to the Schwarzian time scale. So the classical effects actually tend to drive you away from extremality. You can do the calculation, but this is really what happens. Okay, I can tell you more about that. Good. So supersymmetric black holes, good. So what's the usual picture? Usual picture is that you have this supersymmetric black hole, and then you have this set of microstates. Okay? They both have the same charges, and you do some counting here, and you calculate the area here, and then these two are related by some tuning of parameter of modulus, which we can call G string. Then everything is supersymmetric. Okay. Now, because now we have understood that this black hole decouples, and you can really think of it as an independent quantum system, it allows us to start asking really detailed questions. Okay, and one of the questions I want to discuss today is something, again, which was in everybody's head from the very beginning, but somehow hadn't been spelled out fully, which is that the way, what is done in string theory is this. Okay, so you start with this picture, you calculate the area of the black hole, maybe with quantum corrections. But on the microscopic side, what you do, you don't count the number of states, you count the supersymmetric index. That's the number of bosons minus the number of fermions. Okay? And these are the two things that agree. Okay, beginning with Strominger-Waffe and all the calculations ever since then, okay, in this game. So the question is, why does this work? You're comparing two different things. Okay, is it only an approximate agreement? Now, for a single black hole, you can make an argument to show why this agreement happens. And it goes like this. So these are the two things I already discussed. Firstly, that the supersymmetric black hole is decoupled. There's a notion of Hilbert space of a black hole and outside. And now, if you start with weak coupling and calculate the index, that index is protected as you go to strong coupling. Let's imagine there's nothing else outside the black hole. So that index really becomes the index of the black hole. But then we had this other argument that the index of the black hole is the same as the degeneracy of the black hole. Okay? And you put all these things together and argue why the index, weakly coupled index, equals the black hole entropy of supersymmetric black holes. But it's a bit long-winded. And you can ask, is there a direct explanation from the asymptotic theory? Okay. Now, so far in this discussion, there was an implicit assumption that, in fact, there's nothing outside the black hole, but that's not the case. You can have other configurations, which is not just one black hole. And in fact, they're well known. There are supersymmetric black hole bound states. Okay, so imagine this has charge gamma 1 plus gamma 2, and now you have gamma 1 and gamma 2, two black holes with charges gamma 1 and gamma 2. Okay, this is discussed a lot by Denef and collaborators. And in all cases where we can calculate the microscopic index, where these configurations also contribute, you can check that the index also accounts for that. Okay, in particular, there's a nice series of works by Manscott, Piolin, and Sen, which shows how to calculate that. Okay, so you really know that starting from infinity, you have a black hole saddle point, but you also have these multi-black hole saddle points. Okay, but now if you want to decouple, you're in trouble, because if you decouple the two black holes, suppose you, like this, you say, I'm going to zoom down the throat of this, there's some ADS2, you can do all that, but you lose sight of the bound state, you lose sight of the other black hole has gone off to infinity. That's not what you want to do. 5 minutes, okay. All right, thanks. So you want to ask, can I put all of these things inside one path integral, okay, or inside one accounting framework? Okay, and the new picture is that there's a direct way to define the index in the gravitational theory. And again, you use the temperature as a regulator. Okay, and this is the relation with the first half of the talk. And in fact, this is what Witten had originally done when he defined the index. You have some quantum mechanical system. You write something like a thermal state, e to the minus beta h. Beta is not 0, because only then does the trace converge. And then you put a minus 1 to the f to ensure cancellations. And so you have to use a beta to define the index, and the answer is beta independent. Beta is the inverse temperature. Okay? So we want to do something like that in gravity. We don't know how to do that with the trace, so we're going to use path integrals. So this can be converted to a path integral. It's just you have a time circle, you give periodic boundary conditions to the fermions. Okay. So in gravity, you can do that. You can study the analog of Gibbons-Hawking with periodic boundary conditions for the fermions around the time circle. And the question is, what are the saddles? So this is what I call the gravitational index. Okay. And the question is, what are the saddles of the gravitational index? Okay. Now, the fact that the microscopic entropy equals the, microscopic index equals the entropy of supersymmetric black holes might lead you to think that the saddle of this is the supersymmetric black hole. Okay. However, that cannot be the case for two reasons. So in gravity, when you give some temperature circle like this, you expect a solution of this sort. There's some contractible circle. Okay. And where it contracts is the horizon. But supersymmetric black holes are extremal. They don't have beta finite, they have beta equals infinity. And correspondingly, the throat, there's an infinite throat in the interior, which we just saw earlier. You can even try to ask, suppose I start with the finite beta and impose an extremality on the solution. People have tried that, and you get some incompatibility. You either get a singularity or you get zero entropy. So that's the first problem. And the second problem is that this kind of cigar topology, which we expect from a Euclidean black hole, admits only one smooth spin structure, which is anti-periodic. That's the opposite of what we want from a supersymmetric situation. Okay. All right. Now, the resolution is as follows, that there's actually a family of non-extremal supersymmetric configurations in the Euclidean theory. And the way you construct it is as follows. So firstly, at infinity, you turn on a holonomy for an R-symmetry gauge field, okay, equals to pi I. So what this does, by definition, R-symmetry charges bosons and fermions differently. Okay, so that mimics for you the -1 to the f. So now you can put smooth boundary conditions, smooth conditions, spin structures for the fermions. Okay, so you've converted the fermionic problem to a bosonic problem. Okay, now you have to solve the equations of motion of supergravity with this boundary condition. Notice that this is complex, this is imaginary, so the solution in some way will be complex. Okay, but you can find such solutions, and there's a real slice along which this is smooth. It has a cigar-like topology and a non-zero, I call it temperature in quotes, because it's a Euclidean complex solution. And the extremal supersymmetric black hole is recovered in the t goes to 0 limit. Okay, so this is the same type of philosophy that we were using in the first half of the talk, but now applied to the extremal black holes. Okay, and the sort of miracle, if you want, is that if you calculate the Gibbons-Hawking free energy of this gravitational system, you find that that's exactly equal to the free energy of the extremal black hole. So it's independent of beta. Okay, so that's exactly what you would expect from an index. It's a smooth solution with some beta, with the correct fermionic boundary conditions, and the answer is independent of beta. Okay, that's the kind of thing which is the analog of what we're used to for the Witten index. Now, this was first done here in ADS5, but then it was repeated to in all ADS spaces and also flat space. One comment, very quick comment, is that these are allowed by the so-called Kontsevich-Siegel-Witten criterion. I don't want to discuss that because of time. Maybe a couple of more slides and I'll stop. Okay, I thought I'll give you one example because it's nice. Instead of ADS5, the simplest example is back to Einstein-Maxwell theory. So this is kind of fun, so I thought I'll say it. So you want to write down a supersymmetric solution, and this is known for a long time. And it's given in terms of two harmonic functions, v and v tilde, and this is the metric. And you see that there's a rotation parameter in the metric, and there's also a gauge field. There's an electric monopole and a magnetic dipole. Okay. When v equals v tilde, the rotation goes away and the dipole goes away. The solution becomes extremal. This is the Reissner-Nostrom solution when v equals v tilde. Okay. And now, if you take the two harmonic functions to be two sources with charge q by 2 and q by 2, there's a half here because of this normalization here. What you've done is you have a double pole solution for the extremal black hole with charge q, and you separate it into two single poles of charge q by 2 and q by 2. So I call it the north pole and the south pole. That's what gives you a dipole. And then you have to do a Euclidean continuation. I mean, that's T is the Euclidean. And you can do it either by recognizing that it's a Kerr-Newman solution and demanding smoothness at the tip, or by saying that, look, there is this source means that there is a Dirac-Misner string, and that has to begin and end smoothly at the poles. So in either way, you can do that, and what you find is that the angular velocity of the black hole equals 2 pi I over beta. Okay? And what that means is that the index is, according to Gibbons and Hawking, what you're calculating in the solution is trace e to the beta omega j to the minus beta h. That's what a GR person would do. But now beta omega is 2 pi I. So you have e to the 2 pi I j, which is precisely minus 1 to the f. Okay? So that's the sense in which these solutions give you indices. And now you can repeat this in many different contexts. So you can do it in 4-dimensional flat supergravity. So you have these attractor black holes. Now they become rotating black holes. You can do it in 5-dimensional asymptotic flat supergravity for black holes, black strings. So there's a lot of work in the recent years. You can do it for multi-center black holes with the same boundary conditions. Each black hole now becomes a little dipole. And now you can study its moduli space. You can study wall crossing in the path integral. You can study 5-dimensional black hole bound states. You can study black rings. This is some work in progress. This is really brief snapshots. In all these cases, the point I want to make is that you have some temperature at infinity, and all of these are non-extremal saddles which belong to the same path integral at infinity. Okay, so I'll stop here. Maybe I'll just flash this and stop here. Thank you very much.
Thanks a lot, Samir. So we still have time for a couple questions.
Arkan.
Just to clarify the logic about the first box. So you were mentioning that ADS2S2 is special, and that's a 4-dimensional black hole. But then you quickly mentioned Strominger-Waffa, which is 5-dimensional.
Yes. So maybe, sorry, I should have said this. I thought I said this. So all the statements that I made apply to near extremal and extremal black holes of all types. I just took the Einstein-Maxwell theory in 4 dimensions as a concrete illustration. So you can take 5-dimensional black holes, you can take ADS2, with the near horizon always has an ADS2 times a compact factor. That's the only thing that's the same. Yeah, but near extremal black holes of all types, near horizon always develop an ADS2 factor. That's the only thing I've used here. And thank you very much, Arkady. I should have made this absolutely clear. So everything I say is not only for the Royston-Austin black hole, but for any extremal black hole. Because after all, the only thing I use is the appearance of ADS2. Thanks.
I have a quick question. So you emphasize that this Schwarzschild mode affects the logarithmic corrections to the entropy, but somehow it's not the whole contribution. Could you quickly comment on the other contributions to the logarithmic corrections?
Wait.
So you had this power of Q to the C log.
Yes. So that was the thing that you and I know very well from
the days. It came from the volume of the gauge mode, but somehow this is already encountered.
No. Sorry, let me just go back to the formula. Sorry. Here it is. So let's go here maybe.
Exactly, that's the slide. Yeah.
Here. So this was already present in the extremal black hole. It's not the volume of the zero modes of the gauge field. This was sorry. So let me clarify. Thanks. So the way I presented it, I separated the zero modes and the non-zero modes, but then I did something which, for ease of presentation, which is that here there's no Q. But in fact, there should also be a factor of Q here, because the zero modes, as you say, also contribute to a T-independent answer. I have rescaled the theory such that all the Q dependence has already gone here, and then you get that. So that comes out of the usual type of calculation of the loop calculation that we're used to. So that you can almost think of it as dimensional analysis, and then you're left with this thing.
Thanks for the clarification. I don't see any further questions. Let's thank Samir again for the beautiful
lecture. Thank you very much.
Our next speaker is Andrew Svesko, also from King's College. The slides will be on in a second. We talk about finite boundaries in gravity.
Great, thanks. No worries. Okay.
There should be some time for questions.
Yeah, sounds good. Thanks. All right. So first, I'd like to thank the organizers for having me. It's a privilege to be here today and speak with you. This is actually my first time to Sweden and my very first Eurostrings, in fact. I'm an American, so let me move this over here. Boundaries play a foundational role in physics. This is particularly the case in gravitational physics, where even the notion of conserved charge and mass requires a boundary. And of course, to have a microscopic interpretation of gravity, the time-like boundary of ADS is proven important in the context of holography. So today, what I'm going to be telling you about is recent developments on finite boundaries in gravity. And this is based on my work with my colleagues here. In particular, I'll be focusing on work with Avita Verheiden, Manis Visser, Eric Verlinde, Batul Banashemi, Ted Jacobson, Sergio Aguilar-Guettez, and also some recent work with my colleagues at King's, Damian Galente, and his truly remarkable PhD student, Chawarkorn Manarat. Okay. So let me give a kind of heuristic picture. Imagine you have some space-time manifold M with some finite boundary gamma. Here I'm imagining a Lorentzian spacetime such that gamma will be some finite time-like boundary. By finite, I mean it has a finite size, so you really carve out a finite cavity or a world tube where inside and outside you can have dynamical spacetime. And these kind of finite boundaries have been used in gravitational physics before, as it has a long history. So sometimes they're used in numerical relativity in practice. The stretched horizons of black hole, so black hole membranes, or stretched horizons of cosmological horizons. These are examples of finite time-like boundaries, and this is particularly useful in trying to do some modeling of astrophysical black holes. As you hear more about from me later, finite boundaries have been very useful in characterizing gravitational thermodynamics of black holes and de Sitter space. And of course, finite boundaries also have played a role in holography. They appear in holographic normalization. Brain worlds are an example of finite boundaries. And TT bar or finite cutoff holography, the finite boundary plays a critical role. Okay. Now, so far, I've only told you part of the story. What I've said is incomplete, in that you need to further specify the boundary conditions that your fields, in this case the metric, will obey at the boundary. And this is a choice that we make. And most often, the choices we use are, say, Dirichlet boundary conditions. This is where you fix the induced metric on your boundary. Or you can take Neumann boundary conditions, where you roughly fix the extrinsic curvature at the boundary. You could also use combinations thereof. These are known as Robin boundary conditions. But these are the kind of boundary conditions usually impose on the applications I was mentioning on the previous slide. Now, it turns out, and some of these results came out quite recently, that generically, these kind of boundary conditions are in fact ill-posed. What I mean by ill-posed, I'll say more in a later slide. But these proofs come from our friends in the mathematical relativity community. And it's in Euclidean context. This was shown by Anderson some years ago, and later reviewed again by Witten. In Lorentzian context, this was shown just a few years ago by Ann and Anderson. It turns out that it doesn't matter what cosmological constant you have in your background. So adding lambda doesn't ameliorate these issues of well-posedness. I should also say, though, that there are special cases where you do have that Dirichlet boundary conditions can be allowed, you can be well-posed, but you have to add in additional conditions, which I'll explain later what those are. But because of this, generically, these boundary conditions tend to be ill-posed, this led our colleagues in mathematical relativity to consider other types of boundary conditions. And one in particular is the conformal boundary conditions. And these are, you fix the conformal class of your metric induced at the boundary. So you fix your induced metric up to a conformal factor. And you also fix the trace of the extrinsic curvature. Okay. And these tend to be better behaved. So the point of this talk is I'm going to be explaining to you a little of this history and also the utility of adding finite boundaries, particularly in the context of Euclidean gravity and what they tell us about gravitational thermodynamics. So in the first chunk of the talk, I'm going to be talking about finite Dirichlet boundaries and the thermodynamics, particularly for de Sitter space. So we'll see how these can lead to important insights about the thermodynamics of the de Sitter static patch, defining ensembles. It'll also help us clarify this particular minus sign that appears in the first law of cosmological horizons. Then I'll switch gears and I'll talk about the thermodynamics you get from using conformal boundaries, finite conformal boundaries. And there's many interesting things. We'll see that you have thermally stable cosmological systems. It'll lead to new scalings for the entropy as you approach near extremality. And it turns out that the effective description of these near extremal black holes in the conformal ensemble is not actually characterized by JT gravity, but something else. And then if we have these boundaries that are dynamical, there's an effective description, at least in a particular case, which isn't described by a Schwarzian, but rather by a pair of Schwarzians. So that's essentially the outline of the talk. So that'll be our roadmap. Now, I should say I'm only covering a small sliver, a finite sliver of a lot of developments on this topic of finite boundaries. Here's kind of the various subfields that finite boundaries have appeared. Some results are relatively old and some are quite new. This is essentially a preemptive mea culpa for names that I will forget as I go along. But yes, there's been lots of work on this topic. Okay. So before I get to the thermodynamics of de Sitter, let me just first briefly summarize the status, what happens for black hole thermodynamics. And luckily, Samir gave an excellent review talk, so I can rip through this. So Bekenstein first proposed that black holes have an entropy proportional to the area of their event horizon. Hawking found that they actually radiate at a temperature proportional to their surface gravity. And this here, I just write down in terms of the Schwarzschild black hole in 4D. And what this tells us that, black holes are genuine thermal systems. The laws of black hole mechanics can be identified with the laws of black hole thermodynamics, in which the internal energy of the system is identified with the conserved ADM mass of your system. And you can derive this using Gibbons Hawking prescription with using a Euclidean path integral derivation. Basically what they showed was that you define a canonical partition function and to leading order in some stationary phase approximation. It's given in terms of some on-shell Euclidean action, which you can compute. And from there, using basic stat mech principles, you can then write down your various thermodynamic quantities. Now, a peculiar thing about the Schwarzschild black hole is that it actually has negative heat capacity, which means it's thermally unstable. This is not so surprising. You put this black hole, there's some infinite space, it's radiating, and so it's not going to be in thermal equilibrium. But what this means is that since it has negative heat capacity, this comes from elementary stat mech, means that the canonical ensemble is actually ill-defined. And this was even noted by Hawking long ago. And so, one suggestion is you should appeal to the microcanonical ensemble where you fix the energy of your system. And this has also been, considered by Brown and York and others since then. Now, another approach championed by York was to put a black hole in a box. So the idea here is let's take the Schwarzschild black hole of some mass m, and we'll put it inside of some finite sized box of some fixed radius. So on the right-hand side here, imagine this is my Euclidean cigar, which now I've put some finite boundary gamma there. Okay. Now, what York did is he assumed Dirichlet boundary conditions such that the metric induced on the boundary is fixed. And fixing these kind of boundary conditions, they tell you, they also fix your thermodynamic data, which then specify your thermal ensemble. So in particular, the canonical ensemble is you fix the temperature relative to this finite boundary. So you're fixing the proper periodicity associated with that boundary, which is not the Hawking temperature, but rather what's known as the Tolman temperature, which is essentially equivalent to the Hawking temperature up to this redshift factor, this root here. Now, in the limit that I take this finite boundary and I send it all the way back to infinity, such that I have the entire Euclidean cigar, you'll notice that the Hawking temperature just becomes the Tolman temperature. You then just apply basic Gibbons-Hawking prescription to write down your essential thermodynamic quantities. And what you find is that the total internal energy of the system is given by the Brown-York energy, which takes this form here. This is some conserved quasi-local charge. Notice that in the limit that r goes to infinity, this just recovers the ADM mass of the black hole. You find that the entropy is the same. It's still just area of the horizon of the black hole. Notably, though, what what York showed was that these systems have positive heat capacity, at least for large enough black holes relative to the size of your boundary. And perhaps this isn't so surprising because this is the same thing that happens when you put black holes in ADS. You can find systems where you have positive heat capacity. What this means is that the canonical ensemble is well defined in this context. And what's more is that you can take these thermodynamic quantities, you can derive a quasi-local first law, where now EBY, this Brown-York energy, appears on this side here, but you also have a new term, this kind of pressure area-like work term as well. Okay, so now black holes aren't the only systems that have horizons. Particularly de Sitter space also has a horizon. So here's a picture of de Sitter space, the Penrose diagram. This shaded blue region is the static patch covered by these coordinates here. And to observers, static patch observers stuck in the static patch, in our case, Chawakorn, he would encounter a horizon at at r equals L, known as the cosmological horizon. Okay. Now, since it has a horizon, what this suggests is that there is some, you might expect that there's some thermal description of the de Sitter static patch. And indeed, Gibbons and Hawking showed that the area of the horizon is related to the entropy of the system, and that also has a temperature proportional to the surface gravity. They also derived this using Euclidean path number derivation, where they found to leading order, the on-shell action is proportional to the Gibbons-Hawking entropy, and that the energy is vanishing. Now, to my colleagues and I, we thought this derivation was a bit cavalier, because when you take the static patch, when you Wick rotate it, you find that the system is just a sphere, which has no boundary. So there is no location for you to define fix a conserved charge or fix other thermodynamic data to define thermal ensembles. Now, even ignoring this puzzle for us, de Sitter thermodynamics is also curious in that it has this minus sign that appears in the first law of cosmological horizons. So here on this side, on the right-hand side, this is a mechanical statement. So you add in some killing matter, say, and you pick up, this is the response to your horizon, to your cosmological horizon. And this is why we often say you throw something into the static patch, it reduces the entropy of empty de Sitter. And it's because of this minus sign. Now, if we want to understand this as an ordinary first law, we should also have an interpretation of this minus sign. And so that's another puzzling thing about de Sitter thermo. Okay, now both of these puzzles for us, you can clarify if you put de Sitter in a box. So what we do is, this is the setup. You take a finite boundary. We're going to assume Dirichlet boundaries. You put it inside of the de Sitter static patch in this way. This divides the static patch into two regions. One is this bluish purplish region here between the pole at r equals 0 and the screen. This is known as the pole patch. The complementary region is between the screen and the cosmological horizon. This is known as the cosmic patch. Now, an important limit that we can take is you can have the full static patch limit. So if you're confined to the pole patch, so you don't see the cosmological horizon, you can take the limit that r goes all the way to the cosmological horizon. And that would then fill, and you'd have the entire static patch. You can also go the other direction, where if you're confined to the cosmic patch, you take the screen and you send it all the way to the pole, and that would also give you the full static patch region. Now, just in the same way that York did, we can consider the canonical ensemble. So these boundary conditions they define for us are thermal ensembles. And the canonical ensemble, just as for black holes, is you fix the Tolman temperature of the system, and you also fix the size of the system. From there, you can just then apply basic stat-mech principles, and you will find that the total energy of the system is given by EBY, the quasi-local Brown-York energy, and the entropy is just that of the Gibbons-Hawking entropy. And I should also comment, this is the same kind of setup that one uses when trying to find a macroscopic interpretation of the Sitter static patch using TT bar or TT bar plus lambda-like formalisms. Okay, what's more is you can derive a quasi-local first law. We did this using some covariant phase space methods. This E sub m here, this is just the change of the killing matter energy that you put inside of your static patch. And this limit I was mentioning, let's suppose you're in the cosmic patch and you take the limit such that you go all the way to the pole, to the full static patch limit. Then as r goes to 0, your Brown-York energy goes to 0, the Tolman temperature goes to the Gibbons-Hawking temperature, and you simply recover the historic first law of cosmological horizons with its minus sign. And prior to our work, what was often assumed was that this, the interpretation was that this E sub m should be viewed as the total internal energy of the system. And then what's more is that you should view this not as a first law with respect to the static patch, but actually beyond the horizon. So this was an interpretation by Strominger, Volovich, and Sprodlin. But by our calculation, what you see is that what you should view is that the Brown-York energy, just like in black holes, is the total energy of the system. So you should not view EM as the total energy of the system, and that the minus sign does appear, but it's just at this, static patch limit. And you should view this first law as really being a first law inside of the static patch. So it's one that a static patch observer would see. Okay, I'll skip this comment actually. I can come back later. Okay, so that's kind of the status about Dirichlet boundaries and what they can do for us regarding thermodynamics of de Sitter. So let me move on and talk about other types of boundary conditions. You might ask, okay, why should I consider other boundary conditions? Well, first, what I didn't explain yet is that actually with these Dirichlet boundaries, there are no cosmic patches and no systems that have cosmological horizons that are thermodynamically stable. You always compute having a negative heat capacity. So that means we're back at the same problem that York was first trying to overcome, and that the canonical ensemble is not well defined in this case. Now, aside from that, just generically, Dirichlet boundary conditions in GR are generically opposed. And so what that means is, so for example, in the Euclidean context, what you find is that Dirichlet boundary conditions are not what we say are elliptic. And what that means is that it doesn't lead to a sensible perturbation theory that you want to have if you're trying to do some sort of semi-classical gravity and describing gravitational thermo. This was proven by Anderson and then again later investigated by Witten. There's also, in the Lorentzian context, proven just a few years ago, that generic Dirichlet data will not satisfy existence or uniqueness conditions for having a well-posed initial boundary value problem. So basically, for generic Dirichlet data, they will not satisfy the Hamiltonian constraint projected onto the boundary. Now, there are existence and uniqueness issues also in the Euclidean case, which was also proven by Anderson as well. Now, there are exceptions also recognized by Anderson and Witten and my colleagues at King's. And essentially, in addition to Dirichlet boundary conditions, if you impose having the extrinsic curvature or the Brown-York stress tensor having a definite sign and having the same sign as the induced metric, then you can find situations where the boundary conditions will be well posed. But generically, that is not the case. So this led people to investigate other types of boundary conditions. In particular, you had conformal boundary conditions where you fix the conformal class and you fix the trace of extrinsic curvature. What this means is that now what K will do is it will tell you basically the size of the system. It also tells you kind of where the position of the boundary will be in your space, whereas the shape of the boundary will be governed by the conformal class, which is fixed, but it'll have some dynamics because you have this free conformal factor that you have not fixed. Now, the first immediate thing that happens at the level of the action is when you change these boundary conditions, you need a new boundary term to have a well-posed variational problem. So it's no longer the Gibbons-Hawking-York boundary term, but rather it's this kind of rescaled version of the Gibbons-Hawking boundary term. And you also find, instead of the Brown-York quasi-local stress tensor, kind of the analog with this conformal boundary conditions. You notice that it's traceless, and if you're at fixed K, it is also conformally or covariantly conserved. And even though this extra factor here might seem innocuous, we'll see it has profound implications later. Just a couple more comments is that these kind of boundary conditions, they were proposed originally by York back in the 70s, but for space-like surfaces when he was trying to understand the Hamiltonian evolution in GR. These are, in fact, these same boundary conditions that we use in ADS CFT, so we're actually quite familiar with them. One thing we often forget is the extrinsic curvature of the infinite time-like conformal boundary of ADS is actually fixed. So when I say putting things in a box from now on, it basically we're putting things into an ADS box. Interestingly, using conformal boundary conditions appeared in the fluid gravity correspondence some years ago. This was shown that when they're trying to find solutions to when you're looking at a time-like boundary very, very close to the horizon of black holes or cosmological horizons, there was an obstruction actually with Dirichlet boundary conditions, but they found that this obstruction went away if you included conformal boundaries. They're well posed, they're proven to be well posed, by Anderson and Witten. And about a year ago, it was found that there was a one-parameter extension leading to some kind of generalized conformal boundary conditions by our colleagues Liu, Santos, and Wiseman. These were also proven to be well-posed in the Euclidean context. Okay, so let me just have a one-slide summary of the status of well-posedness of these boundaries in Lorentzian GR. So just very recently, a few months ago, it was proven by Ann and Anderson that they satisfy a linearized proof for any Einstein background. But it turns out, initial boundary value problem, I should say. It turns out that nonetheless, for spherical boundaries, you have these growing modes at large angular momentum. And these growing modes were used by Liu, Santos, Wiseman, and Real to show that there is actually a violation of the so-called Hadamard criterion, which basically just says if you perturb your initial data, you can have wildly different solutions. Now, I won't go into more details about what's going on with the well-posedness of the Lorentzian context. There is a wonderful talk by my colleague Damian. It's on YouTube. So when you download my slides, you can just click on this link. But all this is to say is that there are still some open questions about the status of conformal boundaries and their stability. And so, interesting question is, why do these conformal boundaries have growing modes? And this is work in progress with my colleagues at King's, Dio, Damian Chawakorn, and a very good postdoc who's also here today, Sylvia Georgescu. She's here a week, so if you also have questions, you can talk to her. Okay, so back to Euclidean gravity with conformal boundaries. So we can now just use the usual Gibbons-Hawking prescription. We have the canonical partition function expressed in a stationary phase approximation in terms of just this on-shell action. The boundary conditions, just like in the Dirichlet case, our boundary conditions will give us a new type of thermal ensemble. For the canonical ensemble, so the conformal canonical ensemble, what we fix is not the Tolman temperature, but we fix the so-called conformal temperature. And this is essentially a conformally invariant quantity that you can construct from your Tolman temperature and your radius of your system. You also fix the trace of the extrinsic curvature. You then apply basic stat mech principles, and you will find the internal energy, the entropy, and so forth just by appropriate beta derivatives of your canonical partition function. And as an explicit example, take the Schwarzschild black hole in any dimension, but you can. And what you find is that the energy is given by the conserved quasi-local Brown-York energy, assuming conformal boundary conditions. This was a charge that was originally derived by Odak and Speziale. The entropy is just the area of the black hole horizon. And you can also write down quasi-local first laws like this, where you have the conformal temperature, this is your quasi-local energy, but you also get a term that goes like this, where this V here is the volume, or it's proportional to the volume of your spatial boundary. Okay. Now, there are loads of interesting things that come out of working with conformal boundaries. The first thing is that you actually have stable cosmic patches. So this is in even empty de Sitter space. You can find a region in your parameter space of your thermodynamic data that you'll find, you compute a positive heat capacity. This is in stark contrast to what we saw for the Dirichlet case. So this means that you can, you have well-defined canonical ensembles that you can explore with conformal boundary conditions. What's more is that if you take the high temperature limit for spherical black holes and also empty de Sitter, you'll see that the thermal entropy just goes, it scales in this way here with the conformal temperature. And this just is precisely the scaling of a thermal CFT in one dimension less than your bulk gravity theory. So this is, and this function, this NDOF here, is suggestively written to indicate that perhaps this gives you some kind of generalized notion of some central charge of whatever your putative dual of your finite system would be. Let's take, for example, the bottom line here. This is if you had a negative cosmological constant. One thing is if you take the quantity k times L, where L is the ADS length scale, and you go to infinity, you'll just recover what the flat space analog of it is. But what's more is, let's suppose we take KL and send it to this value d minus 1. What you find, so this is taking the conformal boundary, the finite conformal boundary, and sending it to the infinite conformal boundary of ADS. And what this gives you is you'll recover the central charge of your CFT that's living on the boundary. And so particularly in the ADS3 case, if you take KL to 3, you would recover the Brown-Hanot central charge. And so this shows that as you push the boundary in, you get these, this quantifies corrections to your generalized central charge of your system. So this is, quite tantalizing, and then it suggests that this finite region with these conformal boundaries is described by a local quantum field theory. Essentially, what you've done is as you push in the boundary, now your conformal factor has dynamics, and it couples to bulk gravitational degrees of freedom. And you could ask, what are particular proposals of this dual theory? And just a few weeks ago, Edgar Shigulian and his student, they were exploring this in the context of ADS3. Okay. Now, what's more is if you take a charged black hole and you put it in one of these finite ADS boxes, you'll be led to other temperature scalings of the entropy as you approach low temperatures. And this is because when you have these conformal boundary conditions, basically near extremality is found by a pair of limits, by some double scaled limit. So you take your conformal temperature and you send it to infinity. But you also have this quantity kq, where q is the fixed charge of your black hole. You let it go to 1, and you let the quantity beta tilde times kq minus 1 be some constant. And this will lead to a family of various scalings you could get. So here's a plot that we computed. This green region is when you go near extremality. And what you find is that in this region, that at very low temperatures, you'll see that the entropy, so you take the entropy minus the extremal entropy, and it scales as linear with the conformal temperature. This is precisely the same kind of thing that Samir was looking at in the previous talk. But also as you increase in temperature, you'll see that it scales like quadratic in the conformal temperature. And in this whitish region here, you're approaching higher temperatures. So if you're, say, the Reis-Nordstrom black hole, in the conformal ensemble, what you have is that at high temperatures, it will behave, the entropy will scale like a thermal CFT in 1 dimension less than your bulk theory, so say a CFTD minus 1. But then as you get really close, it scales like a near CFT1. Okay. Now you can ask, okay, what is the effective description describing these near extremal black holes in the conformal canonical ensemble? So just very briefly, when you have an extremal black hole, say the extremal Reis-Nordstrom, the near horizon geometry goes like ADS2 across S2. You can also have the same thing, or a roughly similar thing, when you have de Sitter black holes. So you take a black hole, even uncharged, put it in the de Sitter static patch. There's a limit, known as the Naria limit, where the black hole horizon matches or coincides with the cosmological horizon. And in that geometry, the near horizon geometry looks like DS2 cross S2. And by now, it's essentially common lore that deviations away from extremality is captured effectively by a 2D dilaton theory of gravity, either ADS2 JT or de Sitter 2 JT gravity. And you can put in, finite Dirichlet boundaries, for example, to explore the quasi-local thermodynamics of these systems. And that was one of the things that we looked at. Now, we can play the same game, but let's investigate the conformal thermodynamics of these near extremal black holes. And so what you do is you perform a spherical dimensional reduction of your full theory. So that includes the boundary conditions as well. And these are what the boundary conditions would look like in this blue box. Phi here is just the dilaton, alpha is just some constant. So this is just the dimensionally reduced conformal boundary conditions from the higher dimensional GR perspective. You also get the action that takes this form here, where it goes, this U phi is the dilaton potential, but you also have this term here, which is the analog of the Gibbons-Hawking-York boundary term, which is the right term that you need in order to have a well-posed variational problem, assuming these boundary conditions, but it's also just the dimension-reduced Gibbons-Hawking boundary term for conformal boundary conditions. And the main takeaway of this slide is that if you want to describe the thermodynamics of the near extremal system that I was looking on the previous slide, the linear potential, so if you go linear in phi, is not sufficient, and that would be JT. In fact, the linear potential is it only describes the extremal black hole physics, except for maybe a constant shift in your energy. So actually to recover the near extremal black hole thermodynamics in the conformal ensemble that I was looking at in the previous slide, you need to go to at least a quadratic order in your dilaton potential. Okay. So far in this whole talk, I've only just been thinking about static boundaries. So I have, fixed the conformal class, but I'm assuming that the conformal factor is static. One thing you can do is, since we have conformal boundary conditions, you can allow this boundary to become dynamical. And so let's consider the case where we have spherically symmetric spacetimes where we allow this conformal factor to be non-static. What you find is that when you impose conformal boundary conditions, this will be led to a complicated second-order differential equation which characterize the dynamics of your conformal factor. And to kind of grapple or make this tractable, what you can do is let's consider the simplifying case if you take a ADS-D system. And then we're going to take our finite conformal boundary and send it very, very close to the infinite conformal boundary. And this is deviations away from that boundary is characterized by this change in k here. So this is what the value of k would be at the actual boundary. And to leading order in delta k, such that we're now just inside of the ADS boundary, this is what the differential equation would be governing the dynamics of omega would look like. It's a bit simpler to look at, and particularly it simplifies in the case where you have ADS3 in the bulk, because then you see that omega just obeys some one-dimensional Liouville equation. You can ask, okay, what is the effective action of this 1D Liouville equation? And essentially, if you follow the same procedure that you would have done for, say, deriving the Schwarzian description of ADS JT gravity, what you find is that the boundary action that governs this dynamics is given by the following. This first term is just the usual Schwarzian that we have for parameterizations, this T of U parameterizations of as you put your boundary inside of your space. But then you also have this additional Schwarzian where gamma here is related to this omega in this way. And what's interesting is you have this relative minus sign between the two Schwarzians. And this is the same thing that you see when you couple a Schwarzian to 1D conformal quantum gravity. This was first observed by my colleagues here. And this is basically just, again, showing that as you push the boundary in, you have that the conformal factor, some boundary dynamics, is coupling to your bulk degrees of freedom. Okay. That's at least in this particular case here. All right. Oh. Let me go back. Very good. Okay. So just to briefly summarize, so I hope I've conveyed that finite boundaries are very interesting in the context of gravity. They're applied in various contexts. There's also been some synergy between the mathematical relativity communities and high energy physics. In particular, conformal boundaries and finite conformal boundaries invite new kinds of physics, and they really help us hone in and try to understand microscopically a finite piece of space-time. There are loads of future directions one could go. We haven't really explored the microscopics of these various theories, even in the lower dimensions. So you can ask, is there a TT bar-like description? There's been some work on this already, some pretty recently. I've only talked about the tree-level thermodynamics of the system for these exchangeable black holes. So you can ask, of course, what happens if you add one-loop quantum corrections. And there's still some outstanding questions regarding the well-posedness and stability of conformal boundaries, particularly in the Lorentzian context. But with that, thank you again. I'll take any questions.
We have plenty of time for questions.
So how does this change the story Samir was just telling us for the Reisner-Nordstrom black hole?
So we don't know the answer yet, but I would say because you have this linear order temperature correction for near extremal black holes, it seems like the story would be, probably similar. But the problem is our low D theory is not just this Schwarzian action anymore. So we have this coupling that happens. Now the other thing is, if you want to ask this question and looking at one loop corrections as well, you have to also we have to include all sorts of geometries in our Euclidean path integral. We have to sum over all various saddles. And that means we also have to include these dynamical boundaries, which we don't know how to do yet. But that would be the first thing. So there should be a similar effect as what Samir is saying. I don't think we're saying anything surprising there.
You mentioned a one parameter extension of this conformal boundary conditions. Can you just
Yeah. So basically, there's this. If you write the trace of it's the trace of your induced metric raised to some power. It could be a rational number times the trace of the extrinsic curvature. That basically modifies. That's like it replaces one of your just fixing the trace of the extrinsic curvature. And fixing that, various powers of p will lead you to different types of conformal boundary conditions. And there's certain limits of p that you will recover, the usual ones that Anderson had first was looking at. And then in some other limits, you will actually recover the Dirichlet boundary conditions as well.
And it would still ensure the well-positiveness?
Yep. Just unless you go to I think it's p minus infinity or p plus infinity where it becomes Dirichlet. But away from there, it's well-posed in the Euclidean sense.
Any further question? If not, let's thank our speaker again.
Thanks.
So we break for coffee and reconvene at 11:40.
Perfect. Perfect. This is
Okay, brief announcements before we start. A cell phone has been found in the coffee lounge. It's in the hands of Madalena, in case you don't find it. And I'm very happy to introduce the next speaker, Agnese Bissi from ICTP, telling us about multi-particle states in CFTs.
Thank you very much. Thanks a lot, first of all, to the organizers that I happen to know all of them very well. So this conference is always very nice. I really like the Eurostring conference every year. So I'm very glad that this year happened here in this beautiful auditorium. And thanks a lot also for inviting me here to present my work. So what I'm going to discuss today is essentially how to deal with multi-particle states in conformal field theories, in particular in unequal force superior Mills, that I'm going to discuss a bit later. And we started this program a couple of years ago with Giulia Fardelli, who used to be my PhD student and now is a postdoc at BU, and with Andrea Manenti, who used to be a postdoc in Uppsala. So what I'm going to discuss is mostly based on these two papers, and I'm also going to discuss something that we are thinking about now. Okay, so what I'm going to present today is how to study correlators in unequal force superior Mills. And we think about unequal force superior Mills having a SUN gauge group. And I'm going to focus in the regime in which the Toft coupling lambda, which is G square n, large, so I'm going to consider the regime of what we usually say strong coupling, and I'm going to consider these correlators in a regime in which the rank of the gauge group is going to be taken large. I'm going to be very specific a bit later, but just to set up a bit what I'm going to discuss. This is actually the reason why we studied this kind of regime is because this is what is called holographic regime, meaning that we can also relate the correlators in our unequal force superior Mills with amplitudes on ADS, and this I'm going to discuss later on. But the main aim and what I'm going to discuss today mostly is how essentially we can read off, I mean this I think all of you already know, the fact that if we study correlators, we can read off the spectrum of the theory. So specifically what I'm going to discuss today is how to extract from correlators in unequal 4 the spectrum of multi-trace operator in the theory. That's the goal, or at least that's what I prepare to discuss with you. So let me first start a bit by discussing the ADS-CFT dictionary, just because I want everybody to be on the same page. So as I said, I'm going to discuss four-dimensional unequal 4 superior Mills with SU1 gauge group and an SU4 R symmetry. This is going to be important later, so just remember that each time that we are going to see an R on my slides means that I'm talking about R symmetry. And this is dual to be superstring theory in ADS-5 cross S5, as we heard already yesterday. So, as I mentioned before, the gauge group rank is n, and the coupling constant is G Mills. On the ADS side, we have the string length, which I denoted here a root of alpha prime, and the string coupling. So the relation between these two two theories is made in this block here. So n, the rank of the gauge group, is proportional to the inverse of the strict coupling, and lambda, which I already introduced before, like g square n, is alpha prime to the -2. So in particular, in this talk, I'm going to consider the leading order in this expansion lambda. So I'm going to consider only the first correction in this parameter here. So I'm just considering leading order there, so just supergravity regime. And instead, I'm going to consider expansion in n, so expansion in the inverse powers of the string coupling. Okay, so this is very important for what I'm going to present. So in particular, also, as we know from ADS-CFT, we know that we can consider correlators on the boundary here. So correlator on the conformal field theory side are mapped into amplitude on the ADS side. So this is much more generic on what I'm going to discuss. But in particular, we know that the weakly coupled regime in the bulk is supergravity. And this essentially corresponds to this expansion that I already discussed, which is a large central charge or large n, because the central charge is proportional to n, and string length to 0, which is what I said already. So in particular, if we consider 4-point correlators in a large n expansion on the conformal field theory side, this corresponds to loop amplitude in ADS for the same reason I said before. So we said that n is proportional to G strings, the inverse powers of G string. So we see that each time that we take a large n expansion on the CFT side, we are probing a loop expansion on ADS. So in particular, let me just introduce a few objects on the conformal field theory side, just to introduce a bit the notation. So here, let's consider the 4-point function of 4 identical operator. We know that due to conformal symmetry, this is fixed to be a function of only u and v, where u and v are the cross ratios which are defined in this way. And then there is this factor here, which depends on the dimension of this operator. Sometimes I refer to this operator as external operator, and this is the dimension now of my external operators. And yeah, this I already said. So another point is that we can expand this 4-point function in terms of conformal block, meaning that we can write down our 4-point function as a sum over the dimension and the spin of what I instead call intermediate operator that I denoted here. So this is a sum over all the possible primaries which appear in the operator product expansion of these two guys and these two guys. And these conformal blocks are completely fixed by conformal symmetry. And this A delta and L is nothing but the 3-point function between O and this operator, which has dimension delta and spin L. Okay, so the most important point that I wanted to stress here, because this is going to be slightly different in a few slides, is that this sum here is a sum over all the possible primaries which appear in this operator product expansion. So when I'm going to introduce supersymmetry, there will be a slight change here. Okay, so now what is the logic? The logic is that I'm going to take my 4-point function and I'm going to expand it in large n, as I said. So there will be a leading term, then there will be a sub-leading term that goes like 1 over n squared, then another term which goes like 1 over n to the 4, and so on and so forth. And if we think about that in the holographic context, the one that I introduced you before, and I'm going to discuss a bit later, so the G0 term is going to correspond to just a disconnected diagram here. Then at order G1, we are going to have this quartic term and this other term, which is just an exchange here. So this is again order 1 over n squared, while at order G square, in principle, so that there is this this diagram here. There can also be bubbles, but in this the particular case of n equal 4, they are not appearing. But this is a kind of pictorial illustration relating how we can expand again our 4-point function in inverse power of n, and the fact that this corresponds again to the loop expansion. So here you see that there is the disconnected part. This is what I will talk and denote by the tree-level part. So the 1 over n squared is what I call tree-level, and then you see that here there is a loop, then there will be 2 loops, and so on and so forth. Okay, so this is why I'm referring to that as loop expansion. Okay, so let me just comment a bit on the spectrum of n equal 4. So most of you, I think, know what I'm saying here, but this is a bit a motivation that we had before starting this whole program. So we know that the spectrum of n equal 4 super Young Mills, I think it started actually here in Sweden, that using integrability methods, we know that the single trace sector of the spectrum is very well understood. So we, at any value of the coupling constant, essentially we know the dimension of single trace operators in n equal 4 super Young Mills. And so by now, I think we can reconstruct all, we have equations that is it possible to solve, and this gives rise again to the dimension of the full single trace sector. Now, if we go away, and again, this is mostly based on integrability methods, which essentially require our theory to be planar. So if we want to go a bit away from the planar limit, it's much more complicated. And in particular, for the multitrace sector of the spectrum, very little is known. So there is some information that one can infer from studying higher, like 4-point function using integrability method in the weak coupling regime. But other than that, very little is known about multitrace sector of n equal 4 super Young Mills. And the kind of question that I would like to address, or at least say something about, is how we can access this piece of information. So in this part of the talk, I'm going to essentially present 2 methods out of the 3 that I could think of. So the first one, again, remember that I'm going to work in this expansion that I said before, in the regime I was mentioning before. So one way to access this sector is to study large n expansion of single trace 4-point function. I will discuss much more in details what I mean by that in the following part of the talk. Then there is another way, is by studying, again, large n expansion of 4-point function of higher trace operator. What I mean by that is that instead of starting with the 4-point function of single trace operator, so where the external operator is single trace, we can start inputting some operators which are intrinsically higher trace, so that we will give access to the multitrace sector. Or there is another way that I'm not going to comment about it, but I wanted just to point out to, because maybe some of you work on that or they are more familiar with this, is that instead of studying 4-point functions, we can study higher point function of single trace operator. This is very similar to the point 1, but I don't want to comment more about that. We can discuss over lunch if you want. But this is another way to access this multitrace sector. So what I mean by that is that essentially in this sum, that let me maybe go back a bit, that in this sum here, there will be both single trace, double trace, and all the higher possible trace operator. So I would like to essentially understand the sector that appear in this sum, which corresponds to higher trace operator. So what I mean in the previous slide is that if we study these correlators here, so for instance, this G1, we soon have, if we study by single trace operator, we soon have that this object contains a double trace operator. So this, I think, is what I have in my next slide. So scenario 1, so the one that essentially involves the study of 4-point function of single trace operator. So let's try to understand it a bit. So this is a 4-point function, and again, if we study it in the large n expansion, as I said before, so in this disconnected part. So if we study the correlator and leading order in N, we see that as intermediate operator, we only have double trace operator. So in particular, the reason is that this 3-point function here is of order 1. So the full 4-point function is of order 1. So we just have the identity operator and these double trace operators. Again, in the limit I discussed before. Then, if we go to the 1 over n square case, again, we also have only double trace operator. And so in this case, we are still fine. Then also in this particular case, we only have double traces. The reason, again, is that the 3-point function, when we start considering this kind of operator, so this notation, maybe let me, this notation here means that those are M-trace operators, and we normalize it in this way. So you see that essentially triple trace operators starts appearing at order 1 over n to the 6. Okay, so this is 1 over n to the 4, so still we only have double trace operators, so we still have access, when we study G1 and G2, we have access to double trace operators, and if we start going to, for instance, G3, we are going to have in the OP decomposition both double traces and triple traces, and so on and so forth. So the more we add here terms, the more we can explore. So, one way to study these Eiger trace operators, which now are mostly mentioned by Eiger trace triple trace operators, we have that we can either go in this direction, as I said, in such a way that by doing this partial weight decomposition or conformal block decomposition, we have access to this kind of operators here. So this is one way to go. Another way is, as I said, instead of studying 4-point function of single trace operators, we can go and take one of the external operator to be a double trace. So instead of studying O itself, we study the double trace of O. And then, for instance, if we take 1 double trace and 3 single trace, so each time that I put this dt means a double trace. In this particular case, the 3-point function of these guys is contains already a 1 over n. So in this particular case, already a leading order, which I mean at order 1 over n square, so in the 3-level part, we are going to have a triple trace operator. So you see that we can either access triple trace by going here in this direction, so studying single trace but Eiger in loop, or we can start introducing Eiger trace operator, and by doing that we explore already Eiger trace at very leading order. This was just a way to tell you what could be the various options that you have to study such operators. So what I'm going to present today is this second scenario. Okay, so the aim, the final goal would be to use together this way together with this other way. So combine together the study of Eiger loop correction, so to large n correction of a 4-point function of single trace operator together with this double trace. But today I want to focus on this scenario 2. Okay, so let me just start by listing for you what is the sect, because, okay, so far this is fully generic. It doesn't really require to have n equal 4 super Young-Mills. I want it to be a bit more generic, but now I want to switch to n equal 4 super Young-Mills. So what is the main advantage of n equal 4 super Young-Mills? The main advantage, together with having this connection with amplitudes in ADS, there is also the fact that we have a set of operators which are protected operator, which essentially they are much more easier to deal with, because again they have the dimension which doesn't acquire any anomalous correction together with their 3-point function. So this is the main difference, and this is what we are going to use heavily. Let me list them a bit, and then we can discuss a bit more what they are. So generically, I'm going to discuss in this talk 2 classes of protected operators. So the first class that I'm going to discuss is half BPS operators. So the dimension of BPS operator is fixed to be some number. And this number is essentially related to the way in which they transform under R symmetry. So if we take half BPS operator, the dimension is equal to P, and they transform under the 0P0 representation of SU4 R symmetry. And I wanted to mention that the 3-point function of two half BPS operator with another half BPS operator is just a function of n. So here I didn't put any lambda, not because it's a typo, it's just because this object, they just depend on the central charge, on the rank of the group, but they don't depend on the coupling constant. So this does not depend at all on lambda. Those are dual to states on the ADS, and the mass is related to this to the dimension here, and P is related to the angular momentum. So now we want to go back to the question before. So what are the single trace, what are the double traces? So up to P equal to 3, this half BPS operator, which here I wrote it, this is maybe is not 100% correct, it's just a symbolic way of writing it. So if you have O2, so this operator which has dimension 2 is essentially trace of phi square. If you have P equal to 3, you have roughly trace of phi cube. So both of them, they are essentially dual. For instance, if you take this operator O2, this is dual to the graviton. So those are scalar operators on, sorry, there can be generic operator in the ADS, so in particular this guy sits in the same supermultiplet of the graviton. This guy is a Kaluza-Klein mode of the graviton, and also when you go to P equal to 4, you have actually two options. One option is to have this guy trace of phi to the 4, which again is similar to the guy that we said before, but now there can be another guy, so this operator here, which is trace phi square, trace phi square. You clearly see why you cannot have anything before dimension 4. And this is dual to a bound two-particle state on ADS. Okay, so already in the half BPF sector, we have two options when we take large enough dimension. So we have the possibility of having a single trace operator or an operator dual to a single particle state on ADS, but we can also have a two-particle state. And those are the guys that I'm going to consider. Okay, so then we also have another set of protected operators, which are a bit less protected than the half BPS one, which are quarter BPS. And here we have a bit more complicated representation of SU4. Those are also bound states they are dual to bound states in ADS, and I'm going to consider mostly these guys that they transform in the QPQ of SU4 R symmetry, and the dimension again is fixed by supersymmetry to be of this number here. So now the issue with this quarter BPS states is that it is not 100% clear how the 3-point function of this operator is, so if it is protected or not. For some operators, we know that their 3-point function is protected, for other not, so generically I didn't want to write anything. The only thing that we are aware of is that this dimension is completely fixed. So let me just write down an example. So if we take this O02, this is going to be an object of this form. So you see that they are multi-trace by construction. So all quarter BPS operators are multi-trace. So they have essentially more or less the same structure as the previous guys. So there will be trace of phi I, phi j, then phi k, phi l, and then there is a projector here. And this projector essentially tells us which is the SU4 representation under which this operator transform. Okay, so differently from the previous one, there is this object here, which makes it have a different way of transforming under that symmetry. Okay, sorry. And these guys, they have dimension 4, and they transform under this representation of R symmetry. So I'm going to present both cases. I'm going to present these correlators whose external operator involve this one here and the previous one that I showed you earlier. Okay, so this is what I just said. So I'm going to consider 4-point correlators made of single and double trace operators, both half BPS or quarter BPS. And what is the logic behind? So the logic behind is that essentially what I'm going to use heavily is the fact that now when we consider the operator product expansion of such operators, they can either be half BPS or quarter BPS, there will be inside this operator product expansion a certain sector of operators which is protected. And we would like to understand how to deal with this protected part. And then from this protected part, understand, infer information about the anomalous dimension of double and higher trace operator, which instead depend on the coupling constant. This is just an overview. I'm going to be more specific later on what I mean. But this is the idea. So study 4-point correlators where we have double trace operators. Okay, so let's start with the simplest case, even if we did the opposite. So we started with, chronologically, we did first the quarter BPS and then the half BPS. But let me start with the half BPS. So let's consider 4-point function of 4 half BPS operator. So I already said how do they transform under R-symmetry. And here I listed the dimension of those operators that we know they are protected from supersymmetry. And the way in which we can write this 4-point function using now superconformal symmetry is essentially we can write down a kinematical term here, and then we can write down this 4-point function. So this is nothing very special, but essentially now since these operators they transform under some R-symmetry, we need to take into account how they transform under this R-symmetry. So we need to introduce some null vectors, which essentially denote the R-symmetry. So essentially this we need to introduce, in addition to the usual cross ratios, also sigma and tau, which are called harmonic cross ratio. This is nothing very special. Now, what do we have? This correlator here, this function g curly g, contains information of all the primaries, as I said before. This is essentially the same as we had in the previous slide, that transform under the tensor product of these two representations and under these two. Essentially, here I'm just considering all the possible R-symmetry representation under which the intermediate operator can transform. So now we didn't use as much as possible supersymmetry. What is very important is the fact that we can use the superconformal word identities. All this work started with some paper I forgot to write it down. I think I had it, but then it disappeared, by Dolan and Osborne about a bit more than 10 years ago. And this, if we study the superconformal word identities, the solution to the superconformal word identity, we are able to disentangle the contribution of protected operator in this among all the possible operators that appear there. And so, for instance, if we consider the simplest possible single trace operator, there are several representations. And for instance, here you already notice, I just put a circle here just to let you notice that among all these operators, there will be some half BPS operators sitting here, but also in other representation. This is just an example. And then by solving the superconformal word identities, we can write our 4-point function in this way. So we will have a part here, which essentially contains all the protected operator that appear inside this, the operator product expansion of my half BPS operator. So this function does not depend at all on lambda, while this function here instead takes into account the contribution of the long multiplet. So this function R is just, again, a function that is completely fixed, is kinematical. And then there is an information here of operator coming from long multiplet. Okay. And in addition, this function H now can be expanded in this way here. And now instead of expanding this in conformal block, we can expand it in superconformal block. And the main difference is that now on this sum, it runs only over the dimension and the spin of the superconformal primaries. That's the most important point. And the R symmetry of the superconformal primary is restricted to be this one here. But the most important point that I want to convey with this is this part here. So if we are able to solve the superconformal with identity, we are able to essentially strip off the contribution of the protected operator which appear inside our operator product expansion. So now what is the strategy? So the strategy is that we start with our protected operator. Then we compute the protected part of the correlator by solving the superconformal word identity, and then we use crossing symmetry to see which consequences has in, so imagine we completely fix this function, then we say, okay, using crossing, what can we say about this function H? That's the logic. Let me just briefly mention how we do it in practice. So what's the tool that we are going to use? So the tool is the inversion formula. So the Lorentzian inversion formula put out in this paper in 2017. So essentially, the idea is that we would like to understand how to relate the operator product expansion with the correlator itself. So we can essentially study the singularities as v goes to 0, and then essentially relate this C, that I'm going to specify in a second what this is, with the double discontinuity of my correlator. So what is the double discontinuity? The double discontinuity is nothing but the difference between the Euclidean correlator with the analytic continuation around z bar going to 1, or essentially is equivalent to 2v going to 0. So what is the point? So the point is that now we are going to input here inside my correlator here, I'm going to study essentially the singularity of the protected part to get information about this C here. So what is C? This function, this object C has poles at the dimension of the exchange operators, and the residues is the square of the 3-point function. So the main logic is this one here. So we study the protected operators. So we fix the function of the protected operator. This function will have singularities, and we would like to understand how the singularities of this protected part is reflected into the non-protected operators. So that's the whole strategy. And actually, let me just go to this case here, where we have up VPS operator of dimension 4. So you see, this is what I just mentioned before. So at dimension 4, we have two operators. So we have one operator, which I denoted with SP, which means single particle. So you see that this is a linear combination of an object which is essentially a double trace, and an object which is a single trace, but this object is dual to a single particle state. And then there is another operator, which is actually genuinely dual to a multi-particle state that we denoted by dt. This is very nice that this actually happens for any p. So we studied the correlator of, okay, these two guys are orthogonal among themselves, and they actually, the 3-point function with all the single particle is 0, and with the double particle is different from 0. And then what we did, we used again supersymmetry, the same story that I told you before. So we studied this correlator here, where two operators are single trace and two of them are double trace. We computed the protected part, which looks like that. So here you see just n squared minus 1 because this is the central charge of the theory. So this we completely fixed. Again, I put a double trace just to remind ourselves. So what we found, this is not very special, but the intermediate operators that we are going to have in this case, they are all SU4 singlet. We computed the anomalous dimension and the correction to the OP coefficient of double trace and triple trace operators appearing in the OP. In particular, at twist 6, there are triple trace operators, as I mentioned before. The results are very long, so I didn't put it here because I don't think it makes much sense to show them to you, but there are explicit results for several twists. Then is some issues with mixing, meaning that there is more than one state which has the same quantum number, but at low enough twist, there is only one operator, in particular in the triple trace sector. Let me just, sorry, this is very important. Our results agree with the supergravity-based one that have been found in this paper here recently. Actually, by looking at the webpage, I saw that Rodolfo gave a talk in the last year, Eurostrings, about something related to that. So maybe for those of you who attended the last year, you can see the differences. Let me just quickly flash what happens for double traces. So what we did for double trace quarter BPS, we essentially studied this kind of correlators. For instance, 3 half BPS operators, single trace, and 1 quarter BPS. And actually, we show that this is protected, meaning that this does not depend on the coupling constant at all. Then we studied these correlators here, so 2 half BPS single trace and 2 double trace and 4 double traces. We reconstructed completely the protected part up to 1 over n squared. But now there are some difficulties that I would like to mention before ending, is that first of all, there is a proliferation of R-symmetry structure. For instance, in this O2 times O02, there are 10 R-symmetry structure, and here there are 42. But the main problem is the fact that the solution to the superconformal word identity is not known, meaning that essentially the form of superconformal block is not known. So we just worked at the level of conformal primary, which is much less powerful. Luckily, a month back, there was this paper here that we are trying to understand. This is like a lot of super space, so it requires a bit of time to digest. But it seems that now it is possible to study superconformal block also for quarter BPS operator. Also for this case, we computed the anomalous dimension and the OP coefficient of some classes of operators. Again, in this particular case, those are conformal primaries, up to twist 6. Let me just conclude because I think I'm out of time. But okay, what I wanted to show you today is essentially that we have some hope to be able to understand higher trace operators, so essentially to include in our study of the spectrum of n equal 4 even higher trace operators. So for double trace operator, a lot of information are known. For instance, we know that the dimension of double trace operators, for instance, for large spin goes in this particular way. So where this tau mean is essentially the operator which has the smallest twist in the spectrum, but we don't know anything of this form for higher trace operator. So this is actually what we would like to understand, try to understand if there is any way in which we are able to completely systematically understand the spectrum of higher trace. And in order to do that, we need to understand the superconformal block for quarter BPS operators. And what we are currently trying to understand is what happens when we include all this information together. So when we put all this information together, you remember there was scenario 1, 2, 3, and so on. So we are trying to understand, for instance, what happens when we put scenario 1 and scenario 2 together, and what we are able to say again about this object here. Notice that before I just glissed around the fact that there is this degeneracy and so on. So technically, this is a bit complicated to solve. And actually, if you put together all these correlators, so you study a kind of system of correlators, it's easier to solve this mixing and these degeneracies. So this is what we are currently trying to understand, and also together with this other thing of understanding the superconformal block. But this is all I wanted to say, so thank you very much.
Thank you. Question from
Hi. So I want to ask you, can you get information about the matrix elements of the non-planar dilatation operator between a single trace, double trace, using these techniques?
Yeah, so essentially, in order to construct our states, we used that object, because in order to define what is an operator, we had to do that. So when we talk about operator, we mean the eigenfunction of the dilation operator. That's the reason why I was writing these two operators with this n. But this is essentially what we did in order to define what is an operator. We just diagonalize essentially the dilation operator. We did, I understand what you maybe wanted to hint to, like just use more the matrix that we have, but we didn't do that.
Yeah. Can I?
Thanks for the nice talk. I want to ask that if I want to consider the setting like with the 1/2 BPS Wilson line inserted into the n=2 supermills, and I want to use this technique in your talk to study the, let's say, single trace and double trace or multi-trace operators on the defect. Do you think like I think that the technique shall apply, but can you like think of more difficulties in the defect case, or you think it's easier?
I think it's more difficult. The reason why it's more difficult, more difficult is because I know how to do this, so I think this is more difficult. But it should work. The issue with that is that you have less symmetry. So each time that you insert a defect, you reduce your symmetry. Yes. So by reducing your symmetry, the symmetry constraints are a bit less powerful. So I'm not 100% sure if you are able to work out exactly the same steps we did because of this reason, because you have less symmetry. So you are breaking your symmetry by including a defect. So for instance, you already have a one-point function which is not 0, or you start having 2-point function that will still have some kind of constraints. So, but I think it is possible. It's just that technically, I think it's a bit less known on how to deal with it.
Yeah, I see. Thank you.
Yeah, sorry. Sorry, I'm a bit ignorant about the superconformal block issue. So what do we know about them? We know them in terms of series, and you would like to have a more closed form expression?
We know what they, their definition, but we don't know their form.
At all? We don't know.
We know for half BPS, for instance, if you start with 2 half BPS, with quarter BPS, we don't know them at all. As far as I know, in this paper that I mentioned, there is some kind of, in principle, you can just build the super Casimir operator and find eigenfunctions. Yeah. But this is a complicated differential equation, because now it's not like having a half BPS operator, you have quarter BPS operator, the symmetry is a bit less, so you start having many more variables which appear, so it's more complicated. I'm not saying that it's impossible, it's just more complicated. We tried for a few months, but then we said, okay, let's... Sure, thank you.
Our next speaker is Bal van Ries from École Polytechnique, talking about Lycone and modular bootstraps. Thank you.
Okay, great. Thank you, Boris. So let me begin again by thanking the organizers for organizing a very nice conference and giving me the opportunity to entertain you for the next 40 minutes and make you all forget that you're very hungry and really want to go for lunch. So I'll talk about some rigorous, precise, mathematically precise results in the context of the light cone and the modular bootstrap based on so these two papers and some work in progress. So to get everybody on the same page, let's just recall what is the light cone bootstrap. Maybe some of you have not even seen this before. So we're going to look at conformal field theories. We're going to look at a 4-point function of some operators, some scalar operators, say phi. And of course, by conformal invariance, I put my points in the canonical configuration. Z bar are just complex coordinates on some two-plane. I'm in d greater than 2, but you put all the 4 points in one two-plane, of course. And then you get this expression, and Jeze had a similar expression on her slides. And this function g, which depends on z and z bar, has, of course, this famous conformal block decomposition with some coefficients lambda p, and for every conformal block, there's a scaling dimension delta and a spin j, and so on. So that's a bit too complicated for the purposes of this talk. So let me just replace this conformal block basically by its leading term. So we're just looking at monomial decomposition, again, for the purposes of this talk. So I call this a toy conformal block, just the monomial. And then I get the decomposition like this. Actually, this decomposition exists in any CFT because I can just decompose the block into monomials. I get the same. It works too. So what can I say in a general CFT? If I look at this monomial decomposition of a 4-point function, well, it's due to the operator product expansion, and the operator product expansion converges. So this thing is supposed to converge for at least in the product of the disk, where z and z bar have both modulus less than 1. There's unitarity. I'm going to assume unitarity. And so that means that all these coefficients c and these exponents h and h bar are strictly positive. H and h bar are related to the scaling dimension and the spin, of course, like so. Then there's locality. Spin should be integer. So in my language, that means that h bar minus h is also an integer. And of course, there's the famous equation of CFT, the whole starting point of the conformal bootstrap, this crossing equation, which says that, well, this is just symmetric on the permutations of the operator, and I have this funny prefactor here. So this crossing equation follows from just Bose's symmetry, basically. Okay, so this is my setup. Now let's take the light cone limit, right? I want to answer this question, what's the light cone bootstrap? So the light cone bootstrap is the following question. If I take the light cone limit, I see this behavior of my correlator, and then there's some subleading corrections, and I assume this lowest value h bar min is strictly positive. And you have this behavior, and you have this type of sum. And the question is then, well, what can I say about the coefficients of the sum just from this behavior? That, in a nutshell, is the light cone bootstrap. If you want to be fancy, you can take into account, if you have answered the question to leading order, you can try to see what happens at subleading order, and so on and so on. Right? So that's the thing we're trying to, that's the kind of game we're trying to play. So, okay, let's put on my physicist hat for a minute and say, well, what can we expect? Let's not be very precise. So here's the equation from the previous slide, and let's do an imprecise analysis. Well, I say, okay, I have the z bar to 1 behavior, so that corresponds to large h bar, right? So this is important because large h bar, right, here I wrote it again, j is h bar minus h. Large h bar, h finite means large spin. So we're going to say, by construction of this limit, something about the large spin limit of any CFT, because this is true in any CFT. Secondly, well, this right-hand side has its own expansion in monomials. It just looks like this, where this is some Pochhammer symbol, and there's some factorials, so the coefficients, the exponents completely known. So roughly speaking, the physicist would say, well, this green summand should roughly become this red summand in the large spin limit. That is the conjecture. So what does this look like pictorially? Well, here's a little example. So the red spectrum are these red crosses, right? So I plot here h vertically, and instead of h bar horizontally, I just put j because that's a nice integer, right? It's m minus n here. Of course, j also goes in the negative direction, but that's just the same thing. So these red summand has terms just at the crosses, and so we're expecting that in any CFT it looks a bit like the green dots, right? So here I've sketched 3 trajectories, but of course this goes up all the way. This should not be 2 delta phi. This should be delta phi plus 1, delta phi plus 2. But that's an error from. So you expect, right? I've sketched here 3 trajectories, but if you look closely, I've sketched 3 slightly different behaviors. So for example, for the first trajectory, you just have things as expect, right? You have an operator, a monomial for every spin, and then gradually, for larger and larger spin, things become more and more like what you expect the red crosses to be. But in the second trajectory, I've omitted the spin here. And okay, maybe at spin 6, yeah, there might not be an operator, right? This is some asymptotic statement. But maybe there's also something omitted at spin 9 and spin 12 and spin 17 and spin 10,000, right? There could be an infinite set of missing spins. Is that allowed? Is something like this allowed? Is it still consistent with this behavior or not? Or here in this third trajectory, I've sketched a little bit of a different thing where sort of on the average, there's an operator at the red point, but not exactly. There's some finite oscillations that maybe just go on forever. Is such a scenario allowed? Right? We don't really know this, and the physicists' level of analysis will never tell us what's really possible. So when I wrote the paper and when I've given other talks, people say, "Well, what are you not just making rigorous what we already know?" You'll see why people ask this. But I want to say, well, what do we really know? We have a very imprecise statement. You can find statements like this in the literature with various caveats in various ways, right? They'll have equal signs, and there will be tildes, and there will be arrows. There will be equal signs with a footnote, and so on. It's all a bit messy, and really that captures the fact that we're not really certain about what happens here. Okay, so what I want to ask is, can we make some mathematically precise statements and maybe exclude some of these scenarios in the process? Okay. Let me pause here for questions. People should just shout questions, because if this is not clear, then nothing will be clear. Okay. Let me stress that anybody, you can just raise your hand. It's fine. Just ask your questions. It'll derail my talk. It'll be fine. Your questions are more important than my talk. All right, so this should now be clear for everybody. So here's the outline for the rest of the talk. I gave the introductory part. I'll give you a bit of history and motivation. Why do I care about such mathematically precise things? Then I'll give the main results. That'll be the better part of the talk. And then at the end, there will be no time left, so I'll skip the modular bootstrap part. History and motivation. This is just one slide. It's this slide. So it starts about 13 years ago, where people did roughly the same analysis as I just did, like this physical level of rigor analysis, but they did it for conformal blocks. And that's why it's not a slide, it's an actual paper, because conformal blocks are harder than monomials. And that was done by these people, and also in parallel by this other group. And there are many follow-ups. These papers have each 500 citations or so. So it's important, probably for your general education, that you know what the Litecoin bootstrap is. But there were no precise results. Let me scrap the word results and say there are no precise mathematical theorems of this analysis until 2022. And that's when these guys, they proved a little theorem for conformal blocks. I'm not going to state the result. The methods are also not particularly useful for generalizations. I have a new method that I want to talk about instead. But for 10 years, like, this was just accepted in the community, but the precise statement was never clarified. So since these works are apparently important, it's probably one motivation is just to ask yourself, well, can we do better? Can we get some precise answers out there? And maybe we can compare these answers with some other methods. We have the numerics. Numerically, we know spin 50 scaling dimensions nowadays for the 3D easing model. Can we compare the large spin analysis with what if at spin 50, right, you have these nice trajectories, so the numerics looks a bit like this. And what if at spin 50, the operator was just not there? And then at 52 and 54 and 56, and so it would be there again. would that be a numerical mistake? Would you say, well, no, that's not compatible with the light cone bootstrap? Or is that still allowed, right? So it would be nice to see if you can make precise results and then compare them precisely with the numerics. Another thing is the analyticity in spin. Another motivation is a follow-up paper basically from this, which is the famous analyticity in spin paper by Simone Caronio that Agnès also mentioned. Again, many follow-ups cited about 400 times now, I think. But there's a little caveat in this Lorentzian inversion formula story, which is that it relies on some benign light cone limit on the second sheet of the CFT correlators. I won't go into the details, but there's a little bit, some results, not all, but some results in this literature rely on some unproven assumptions. I think it would be nice to make that precise. So there's this famous, so let me stress that it's kind of a famous-ish open problem in the rigorous CFT community, whether we can understand this light cone limit on the second sheet. And what I'll present, I'm not going to explain, but what I'll present is a first step in that direction. And then in 2022, I wrote this paper, QFT in ADS instead of LSZ. Not many follow-ups, not cited hundreds of times, but still it's nice, I think. And this was my original motivation Right, I talked about this last year. So I want to prove, for example, the Vassar bound from CFT axioms. And again, you can go to my talk from last year to see, I think the slides at least are online. You can see what I want to do. But the Vassar bound is something rigorously proven, right? You start from the Weidmann axioms. If you want, you start from the lattice. The lattice, you can prove that the Weidmann there are theories that obey the Weidmann axioms. You can prove that they have an S matrix. You can prove that this S matrix obeys the Vassar bound. It's super rigorous. And now I want to see if we can do something a little bit easier, which just take the flat space limit of a QFT in ADS. So then I have the boundary correlators, they obey the CFT axioms, and maybe I can then prove the Vassar bound. So I think this is a nice target to aim for, but I need rigorous control. I need this light cone limit on the second sheet to be benign. And so to get this rigorous control, I need to understand this light cone bootstrap. So that was my motivation. Okay, so there's a lot of context, even though the problem is very easy to formulate. Okay, that brings me to section 2, which will be the bulk of the talk, my main results, and it'll rely on 3 theorems, a Taberian theorem, Vitali's theorem in complex analysis, and the so-called dominated convergence theorem, which you've all seen. I'm sure you've all seen it. I'm not sure you all remember it, but you've certainly all seen it. And so this part of the talk will be fairly technical. You should interrupt me with questions, but it'll give me an opportunity to explain these 3 things. So if you don't know any of them, then hopefully at the end you will, and you'll have learned something, and you can go to lunch already a bit more fulfilled. And then, of course, the modular bootstrap part, yeah, that I'll skip. Well, maybe not, we'll see. So I have 3 classes of theorems to discuss, or 3 theorems, and I have to apply them, of course, to the toy light cone bootstrap. So that's the thing I want to do next. So Taberian theorems. What are Taberian theorems? It's a useful tool. You should add it to your toolkit. So I want to explain what they are. And Taberian theorems are very easy to explain. You all know the geometric sum, right? This is very, very easy. And so this is trivial, but there's also a theorem, and this is the simplest possible Taberian theorem. And it says that if you just modify the coefficients arbitrarily, subject to a constraint that they're bounded from below, let's say positive for simplicity, or non-negative. I modify them arbitrarily, but I still demand that as x goes to 1, this function, so this sum, I should demand that it converges, and that as x goes to 1, it behaves like this. And here I realized that I skipped something. I didn't include, I missed something in my slide. This is mathematical theorem. So there's a tilde, but it has a precise meaning. So the tilde a to b as c goes to d is really the statement that the ratio goes to 1. Okay? So that's what the tilde means. It means something mathematically precise. So okay, let's go back. The theorem says that if the limit is still like 1 over 1 minus x, then that rigorously implies that if I were to sum the coefficient just without the x, that's the same as just summing the 1. So that's of course lambda in the lambda to infinity limit. So it tells you that sort of the sum of the coefficients, or if you want the average of the coefficients, if you omit the factor 1 over lambda, is exactly the same as what you would get from the geometric series. Okay, so now you know what Taberian theorems are, or what a Taberian theorem is. So it's important so you cannot say that the individual coefficients asymptote to 1. Here's a very simple counterexample: 2 times x to the 2k. The coefficients are 2, 0, 2, 0, 2, 0. On average, that is 1. And you can also check, or you can, if you're very bored, you can you can work it out in your head. But as x goes to 1, this also goes like 1 over 1 minus x. So it's important that you don't get an asymptotic behavior. You don't just get the asymptotic behavior of the coefficients. You only get the average of the coefficients. I should also say that there exist estimate of the error terms. There are many, many generalizations. You can have more general power. You can have exponential growth as x goes to 1. You can say, well, what if this limit holds not just along the real axis, but along any segment in the complex plane or whatever, right? These are, there's a nice book by Jaap Korevaar, a Dutch professor who actually passed away earlier this year. Who wrote that contains lots and lots of these Taberian theorems, right? So, but it's a useful tool. The one theorem that I'll need is, of course, I don't have integer powers, right? I have something like this. I have dk x to the h bar k, where x is now, you should think of it as z bar from the previous slide. So I have a sum like this, and as x goes to 1, it doesn't behave like 1 over 1 minus x, but it does something like 1 over 1 minus x to the delta, with some coefficient that I'm not including in the theorem here, but that will be imported on the next slide. And so there's a Taberian theorem, and we're going to use it. So this is the theorem. It says that if you have this behavior, then the asymptotic form of the coefficients is again precisely the same as if you were to expand the right-hand side into monomials. So here I have to truncate h bar less than lambda, and that's the same as summing here k less than lambda. Well, this right-hand side sum is very easy to do, and asymptotically as lambda to infinity. It's just this term. And again, this holds under the condition that these coefficients are non-negative. Okay, so we have a theorem in our toolkit. We can apply it. So here's what we know. This is, again, the third time I write this equation, so you should all understand it now. And our Taberian theorem then says, well, I'm going to think of the ck z to the hk as the coefficients dk from the previous thing, right? There's dk here, and x should be z bar. So it's cz to the h is the asymptotic behavior, and then there's this 1 over 1 minus z bar to the delta phi. So that is the dominating term on the right-hand side as z bar goes to 1. So it says that if I sum the coefficients, which are cz to the h, then I get the right-hand side, z over 1 minus z to the delta phi. That's just a prefactor, and then this same lambda to the delta over gamma. And you can get this for every z for which these coefficients are positive. So you get this pointwise for every single z between 0 and 1, right? Because that's where these coefficients are positive. So this is Taberian theorems. Taberian theorems, I already wrote it on my previous slide. They were first used in this paper for CFTs. So they're known in the bootstrap community a little bit, but I think it's a useful thing to know in general. So we have a Taberian theorem, and what we did is we basically killed the z bar sum, and we just wrote it in terms of a sum over h bar with some cutoff lambda, right? Pictorially, we have this h j thing, and we have some cutoff lambda at some h bar, and we're just summing all the coefficients here, but there's still the z to the h. And that's a problem, right? Because we don't want the z to the h. We want to know something about the spectrum and the values of h that appear. We don't want the z to the h. So how do we trade the z for some h, right? That is the main problem of the Lightcon bootstrap. And that's why the Lightcon bootstrap is hard, because, well, for example, if you want to do, you can try to do a second Taberian theorem and send also z to 1, but that loses information. Then you get something about the large delta spectrum of the theory. That's fine. You get some information. But the light cone bootstrap, we want to keep Z finite. We want to say something about finite H and large J. And this is why the light cone bootstrap is hard and why there are no, very little has been proven for a very long time. And we also cannot expand around Z equals 0. It looks okay, right? Z to the H, here you get Z to the delta phi to the leading order, and then delta phi plus 1 and delta phi plus 2, and that was exactly the spectrum that I had. And so you would say, well, there must be operators with H equals delta phi, H equals delta phi plus 1, and so on. But that's not legal, right? If you have a pointwise limit, you cannot just start expanding and interchange limit. Z bar to 1 and Z to 0 are very different limits, and you cannot just freely interchange limits. Right, so this expansion around Z equals 0 is not something you can do rigorously mathematically. But there's one second theorem that comes to the rescue, which says, so in black, I basically had what I had on the previous slide. Sorry, this rho Z of H bar should be this CZ to the H. So I had what I have on the previous slide, and initially it's true that this is only true pointwise for Z between 0 and 1. But in fact, the same statement is true in a much bigger domain. It is actually really, really big. It covers many, many different sheets in the complex Z plane. If I take Z equals R e to the I theta, so Z to the H is R to the H e to the I theta H. So, right, I go to the universal cover of the complex Z plane with this cut. Then this result is also true for R between 0 and 1 and any theta in R. So I can, like I sketched here, I can start somewhere here in the unit disk and I can go through the cut and I'm on the second sheet and the result is still true. And this is remarkable because I didn't even know that this first equation was true on that sheet. Because this first equation uses the T-channel OPE and the T-channel OPE stops converging there. So I wasn't sure about this first equation, but the second equation actually holds in the, and by extension, actually also the first equation, but a priori it's completely it was non-trivial. And the proof uses basically just the fact that this thing is an analytic function in Z, and if I go onto the second sheet, it's not going to blow up suddenly because I just insert phases in the sum. If I add e to the I theta, it's not going to make the sum any bigger because these coefficients and exponents are all positive. So, and if analytic functions don't blow up, then basically the limit is okay. That is what Vitali's theorem in complex analysis tells you. I have a bonus slide, which you can probably find online after the talk, where I state Vitali's theorem. But roughly speaking, that is the idea. So it's great. So we actually have a much bigger domain. It's not just pointwise. It is, well, it is actually pointwise. It's slightly better. It's uniform on compact subsets, but that's not important. But it holds for any R between 0 and 1, not just, and any real theta, not just theta equals 0. So that's great. We have a better result, and this unlocks some opportunities for us because, and now we'll just get to the dominated convergence theorem part, which is straightforward, but the equations look a bit messy, so let's go slowly. So this is what we know, right? I substituted Z equals R to the I theta. I have this left-hand side, and as lambda goes to infinity, it looks like the right-hand side for all values of R between 0 and 1 and any real theta, right? This is completely fine, okay? And what I said, are there questions now? Okay, so what I said before is you cannot expand around Z equals 0. That's the same as saying, well, you cannot expand around R equals 0, right? So if I want to know the values of H that appear, a natural thing to do here would be to expand around R equals 0 and see which powers I have, but that was illegal. So now I can ask you a question. What is another way to extract the powers of H that appear here? Right? And if you think about it for 5 seconds, it's actually very easy. I'm not going to ask you seriously. Let me just give you the answer. How do I see the values of H that appear? Well, I just inverse Fourier transform with respect to theta, right? So I just do this. I Fourier transform with respect to theta. There's this factor R to the HK, but I just divide by R to the H. That'll do the job. And now I get a spectral density weighted with these OP coefficients. So that's great, right? So this Vitali's theorem, the fact allowed us to integrate all the way from -infinity to infinity. We're going on all the different sheets and so on. So without Vitali's theorem, we would never be able to do this. But now, because we have a result for all real theta, we can do the inverse Fourier transform. So, okay, great. Can we take the limit, right? So we say this, and then as lambda goes to infinity, this purple thing becomes the green thing. So we just plug it in. And, well, this integral is very easy. And this is the inverse Fourier transform of that. And that's just known. I basically wrote it on the previous slide. So is this true that this is now the result? And obviously it's not, right? Because I'm taking this is the limit of the integrand, but the limit of the integral and the integral of the limit are very different things. In general, limits and integrals do not commute. So oh, there's an E missing, sorry. But there's another important life lesson that integrals and limits do not necessarily commute. It may be a surprise to many people in the physics community, but it's definitely not always true. And here we see it very clearly because this is a very sharp spectrum, and you would not expect this average spectrum to this kind of thing to go exactly right. These are delta functions, and you wouldn't expect these delta functions to exactly become this at large lambda. So we're back to a few slides ago. We can take the inverse Fourier transform, but we don't know what the limit is of the integral because we only know the limit of the integrand. So we have to soften, right? To see what goes wrong, why can't you swap in this case? A good example to have in mind is, for example, if this guy would be some bump function in the theta plane, and the bump would go off to infinity in the limit. Right? If you have a bump function in the theta plane, it integrates to say 1, and then as you take it to it doesn't even matter where you position it, but as you take it to infinity, the integrand for every point becomes 0. So the integrand becomes 0 pointwise, but the integral remains 1 because it always finds the bump function at some point. Right? So that's a good intuition to see what one of the subtleties that can appear. It's the most important subtlety in this case. And so what we can do is just suppress the stuff at infinity, right? So so that the bump function becomes smaller and smaller, and that'll cure the problem for us. And that's what we're going to use. So what I'll do is, instead of taking this inverse Fourier transform, I just integrate both sides against some weight function, var phi of h, phi of h. Of course, here it was delta function, so it just picks up the delta function. That's just phi of h minus hk. And here there's phi of h on the left-hand side that I integrate against, on the right-hand side that I integrate against what I had. Right, and phi of h is, if it were a delta function, I would be back where I started. But if phi of h, you should think of it as some bump function, some smoothed out delta function. Right, so for any finite lambda, it is fine to move to swap these two integrals. So I move phi of h inside the integral under some very minor conditions for phi. So you move phi of h inside the integral, and now you can ask, well, at least now can I say something? Can I say something about the large lambda limit? Is this known, and for what class of weight functions is this known? And here, of course, this is the dominated convergence theorem. It says that if your integrand is bounded by some nice, continuous, absolutely integrable function, then everything is fine. And in our case, that boils down to this condition. It says that if I take the Fourier transform of phi of h up to this unimportant factor r to the h, that should be absolutely integrable. Right, so you see that phi of h cannot be a delta function because then this would be 1, that's not integrable. Phi of h cannot even be a step function because that would be the Fourier transform of a step function falls off like 1 over theta, so that's not integrable, but it should be some smoothed out step function and then we're good. So it's for these kind of test functions that I can swap the lambda to infinity limit with the integral. Right, so this is the kind of result we can now prove rigorously. So here's our conclusion. We use 3 theorems, the Tauberian theorem, Vitali's theorem, and dominated convergence theorem. And we obtain a theorem of our own, a theorem of sorts, or proposition if you want to be modest. It says that if we have this behavior, again, this is the fourth time I write it, so that you understand, then I have this result, right, for some class of test functions that obey this condition. So I have the OPE coefficients, I weigh the values of h with this test function, phi of h, I sum over all h bar or all j, say less than or equal to lambda, and then as lambda to infinity, this must diverge as lambda to the delta phi, and then it has the known behavior from the right-hand side. Right, so, and as I said before, the test functions are not allowed to be a delta function because they don't obey this condition, not a block function that doesn't obey this condition, but something smooth, supported on some very small intervals, say 2 epsilon, that's totally fine. So for these class of test functions, I have a result. And so we can go back to our, so this is our main result, and we can go back to our picture and see what we have proven. Well, these first two scenarios are not yet excluded. Well, the first scenario is probably what happens. The second scenario with infinitely many gaps has not been excluded because I can have infinitely many gaps, but the coefficients of the other terms can be a little bit bigger to reproduce still this behavior, including the divergence lambda to the delta phi. But this third scenario where you have finite oscillations, that is now excluded, right? Because I can take, so I'm in the h direction is where I have my test function. So I can pick my test function to be a smooth bump function, but supported in some very, very small interval around delta phi plus m. Sorry, again, this should be delta phi plus 2. And if these oscillations have some finite amplitude, they never touch my test function. So then I will get 0, roughly speaking, from the test function contribution. But I need to get not 0, I need to get infinity. I need to get this particular divergence. So I need infinitely many terms inside the window where my test function has support. And that's also what this statement says. It says that for any epsilon greater than 0, any integer, non-negative integer, there must exist infinitely many terms where h lies in this little interval. Right? Infinitely many because I need this divergence and every single term only contributes a finite number of terms. So this scenario is now excluded. This scenario, like I said, is not quite excluded, but in upcoming work we'll probably exclude it. And this is probably the right scenario. So now we have done the full analysis for monomials. It was actually fairly easy once you know the right theorems. In the paper, I do the same result for conformal blocks, or the equivalent result for conformal blocks. How do you say mutatis mutandis? The things, changing the things that have to be changed. But it's fairly obvious. Okay. So that's my main result, and now I have to go back to my motivation sheet and slide and say something about the Lightcon limit on the second sheet, the Lorentzian inversion formula, and so on, and how things can be improved. Of course, I don't have the time for that, so I'll skip that. But let me take a step back and ask what we are really doing and what kind of research direction follows from this way of thinking. So I guess you can call it more or less averaging. In a certain sense, right, what are we doing? We have this kind of decomposition, maybe with conformal blocks, maybe with monomials. We know what happens as z bar goes to 1. And then for certain test functions, we show that if you take this OPE density, right, which is just the density of, well, here it's a monomial density, but you can make it for conformal blocks, it would be density of operators. You take this density, the density itself, I don't know what happens, but if I average in this peculiar way, where I integrate over h bar to some lambda, and then integrate over h with some test function phi, then I know what happens in the large lambda limit. Right, this was my result. And now the natural question is, well, if you see this OPE density with some averaging is known, then it's natural to ask, well, what's the best? Is this the best thing we can do? Can we do better? How much of this averaging did we really need, right? This was me in 30 minutes explaining, well, 32 minutes, explaining to you exactly like the theorem in full detail. Can we work a little bit harder and get a better averaging? can we, right, there are three important directions here. Can we, for example, so here we have an integral over h bar, and like I said, h bar is roughly the spin, so you should roughly think of it as a sum over all spins up to some cut of lambda, and then we understand the lambda limit. But can we not just say, right, that, can we not just take a large J limit? That would exclude this second scenario, right? Because if this would be, if we would have a result for the large J limit, then we would say, well, no single spin can misbehave asymptotically. There cannot be asymptotically many gap because every spin has to fall in line eventually. Or another thing that would be nice is whether this phi of h can be J dependent, right? Phi of h cannot be a delta function. But it would be funny if phi of h would look more and more like a delta function as J increases. That would be a possibility, and you can ask, well, can we improve in that direction? And then, of course, I mean, I have a limit, so I can ask, well, what about subleading correction? How fast do I approach this limit? Can I understand some of that? Right. So this is the I think the main question. And you should ask this question every time people have these kind of, right, these wiggly equations with tildes and these imprecise equations. There's a whole range of possibilities of what these tildes really mean. And it's possible to make them precise and actually get interesting results. And so for the modular bootstrap, like, yeah, I don't have time, so I'll skip that. We answered all these questions in the affirmative way. We got some. We can we can replace the limits of the sum with just this limit. We can make test functions shrink in a particular J-dependent manner with the rate that you can find in the paper. We can say something about the rate of convergence and so on. So this I'll skip. For the modular bootstrap in this paper with Friedrich and Jashin and me, we have a proper theorem, and you see here the Virasoro primary density averaged with some J-dependent test function in the large J limit, no sum is known. And then, there's some, and I know there is something about the rate of convergence. So that's the main result of the modular bootstrap that we have. And we have some corollaries that I'm not going to talk about. So let me stop here. Thank you very much.
Yes, one question here.
So is there any test function dependence? Like if I take, say, two bumps that come together while they're also being thinned at the same time? Or like...
Yes, but my statement is, my theorem is just true for any test function, right? Of a particular, in a particular class, sorry, this was the wrong direction. Right? If you pick the test function, you pick whatever you want, right? This result is still true, right? If you have two bumps, you pick up two. Here on the right-hand side, right? You see that the right-hand side only depends on the support of the test function, the delta phi plus an integer. So it's at these points. So if you have two bumps, you pick up two terms. You just get two terms in the sum that contribute. If you pick a single term, you get a single bump. So you get the test function. If it obeys this, then my theorem is true.
I was just wondering because you couldn't replace it with a delta function. So maybe would the result depend in how you approach the delta function using different test functions?
Yes. So sorry, here the test function does not depend on J. Test function is given, it obeys this. If it does that, then the result holds. In the other, here I had a J-dependent test function, and you should look at the paper at the particular rate at which this becomes a delta function. It cannot be arbitrary. There's a power which is J to the 1/4, which enters here essentially. Yeah.
Hello, thank you for the talk. I was wondering, usually when you use Tauberian theorems, there is a problem in deriving rigorous asymptotics for the OP coefficients, which is given by the fact that you are always averaging over the OP density, spectral density. And you cannot really integrate on a small window because the rigorous result is always for the large, from 0 to infinity. But here you seem to have a lever, like a handle on the spectral density itself. So I was wondering if, like you are using a test function, not the delta, but is there any hope to find a rigorous asymptotics for large lambda? for the OP coefficients?
Yeah, I think so. If the talk had been longer, I would probably announce the death of Taberian theorems as a useful tool. But it's, as a first order, it's very good. It's very useful. But I think on the longer term, right, we know more, right? If I want to fish out what happens at particular spin J, here in the modular bootstrap, it's very easy. It's just an inverse Fourier transform of the partition function. So I have this modular invariant partition function. I do an inverse Fourier transform, right? And then as J goes to infinity, I pick things so that sort of there's a particular limit that dominates, and then everything is fine. But these Taberian theorems, their only assumption is that I know what happens. Well, let me just not go to the slide. Their only assumption is that you know what happens as x goes to 1. But for the CFT correlator, I know much more. I know the limit as z bar goes to 1, but if you want to give me an estimate that z bar equals e to the I theta, I can give it to you. It may not be great, or z bar equals -1, right? I use all my OPEs and everything at my disposal. I can give you those estimates. And so we should probably not be using Taberian theorems on the longer term, because we should just write these integrals directly that fish out, that project onto a particular spin J, and estimate those integrals using whatever S-channel, T-channel OP coefficients that we have at our disposal. And in this result, we do, in the modular bootstrap result, we use not just modular here on the right-hand side to get the results. We don't use the decomposition in the cross-channel of the modular invariant partition function. But for various terms that might potentially be dangerous here on the right-hand side, we actually go back. We use modular invariance again to estimate that they're small. And therefore, they don't show up here. But to show that they're small, we had to use modular invariance twice. Yeah. Yes. Well, thanks. These are my corollaries. So for the modular bootstrap, because here they come with coefficients 1. Of course, for the CFT bootstrap, right, you're not just counting states; they're weighted by OP coefficients. And if you have a coefficient of very, very 10 to the minus 100, I will never be able to fish that out, or have something decreasing with J. But here the coefficients are 1, and indeed we know that the spectrum becomes dense at very large spin because this right-hand side has a dense spectrum, and it becomes dense for every large spin in some sense, right? There's a proper limit. There's no spin where no spin can misbehave, and we know the rate at which it becomes dense because that's basically the inverse of this in the average, but because we have some convergence here, not just pointwise, but uniform in H space, uniform on compact subspace in H space. We actually can bound also the maximal gap between two operators. And we have a pretty weak estimate, but I think it can be improved by a lot, but we have a proper estimate on the maximal gap between two operators. So it's not just an average statement anymore.
Thanks. I don't see any further questions. So let's thank Bart again for the beautiful talk. And bon appétit, everyone.
I think so.
Okay. Let us start the afternoon session. Our first speaker is Marie Knisch from Brussels, and she'll speak about black hole Hilbert spaces and the gravity path integral.
Okay, so hi. Thank you very much for the opportunity to tell you something more today about an exciting new toolkit that is being developed that will allow us to explore properties of black hole Hilbert spaces using the gravity path integral. So this is work that I will present today in collaboration with Vijay, Ben, Juan, and Mikael. And Juan is in the audience, so if you have any questions, you can always approach us. Good. So, as usual in a presentation, one starts by formulating a question. And the question has been said in many ways this morning. So it starts by Bekenstein and Hawking realizing back in the day that black holes are thermodynamic objects, and in particular, they have an entropy. And the entropy is given by a very universal formula. It's area over 4g Newton. And you can compute it for any black hole, really. However, this formula doesn't tell us what this entropy is actually counting. So if you think back to your statistical mechanics course, you know that entropy is related to the number of microstates that are compatible with some macroscopic description. Think about a gas in a box. It's described by the number of particles, volume, pressure. And then the entropy is counting in how many ways the particles individually can be rearranged to give the same macroscopic observation. So quantum nature of things complicates matters a little bit, but the essence is very much the same. So the entropy is related to the log of the dimension of the underlying Hilbert space. In other words, it's counting the number of linearly independent microstates. Now, if you now apply this to a black hole, it would tell us that the dimension of the black hole Hilbert space is actually exponentially large. So there are exponentially many microstates that are compatible with the macroscopic description of a black hole that we know from GR, where a black hole is just fully described by its mass, charge, and angular momentum. But we don't really know how to think about these microstates. How do we construct them? How do we understand them? How do we count them? So for a long time, it was believed that you actually need to have full control of quantum gravity to do this counting correctly. And therefore, a path of resolution was the stringy approach that we heard of a little bit today also. So you start by a string theory, assume that that's your quantum gravity theory, and then you do a very particular calculation in some corner, and you actually can reproduce that indeed the dimension is this big. However, this is computationally very difficult, first of all, but second of all, it also doesn't capture the universality of this formula for the dimension at all. So another approach is to actually think of these microstates from a semi-classical perspective and try to construct semi-classical microstates that are under good control and then try to do the counting. So this is related to an old idea, bag of gold geometries. So what one can try to do is try to construct a black hole, but hide things behind the horizon, hide gold. And this way you can construct infinitely many states, seemingly. So if you would do the counting, then you would find that the dimension is infinite, which is also not right. So some innovation was required, and it had to wait until the end of 2022, where this set of authors actually said, well, yes, we can construct semi-classical black hole microstates, and we can count them in a correct way, reproducing the right dimension. And this will then give us a universal microscopic explanation for this black hole entropy. So this paper is doing the counting argument and the construction of these microstates in a simple setting of two-sided black holes in ADS that are just described by conserved charge being the mass or the energy. So no charge, no spin. And afterwards, there was actually a lot of innovation, generalizations, but also applications that use this construction and the counting argument. So what I will do today is I will actually tell you about the protagonist in all these stories, namely the specific construction of these microstates and how to do the counting in the simple setting of two-sided black holes in ADS. And then we will see how we can use this for an interesting question, namely the factorization puzzle, how we can actually use these constructions to solve it. Okay? Okay, good. So, as I said, the protagonist in these stories is a specific choice of microstates. Now, we will work for simplicity in ADS. This way we have a holographic crutch to rely on, and we can think about these states both from the CFD perspective as from gravity. So this is just for convenience, really, because you don't need holography to construct these states at all. But let me start with the boundary perspective and introduce these states there, just to give you an idea of what we are actually working with. So in gravity, we want to get two-sided black holes in ADS. So on the CFD side, our Hilbert space is that of a double copy of two identical CFDs. And states in general in this double copy, they look like this, where this is just the energy eigenbasis. Now we will focus on particular states that can be prepared using a Euclidean path integral. So these states, we will describe them by some operator O, that we will specify in a bit. And then we will evolve it to the left and to the right by some parameters beta bar left, beta bar right, using the Hamiltonian. That is the same for the two copies of the CFD. Good. So the states we work with are these, and they're always normalized for convenience. So that's what we work with in the CFD. In gravity, as I said, we want to get two-sided black holes. So these preparation inverse temperatures, beta bar left, beta bar right, they are not just random. We have to take them so that they're above the Hawking-Page transition. So we actually get black holes. So how do we construct the state in gravity in general? So what we will do is a la Hartle-Hawking construction. So we are going to construct the norm using the boundary that is given through the CFD Euclidean path integral, and we fill it in by all allowed geometries. And the saddle point we want to be a black hole. And then we can cut open the norm and evolve in Lorentzian time to see what the state actually is doing. Okay, so we already know that we want to get black holes. We already restricted to this end the preparation inverse temperatures. Now we just wonder what this operator O is sourcing in the bulk. And we are going to pick the operator O so that it sources a thin shell of matter of some mass m. So it's a choice because in this case, we actually have very good semi-classical control of the states that we are constructing in gravity. So there will be just black holes with a thin shell of matter. And for that, we can compute the on-shell actions. Now, depending on the mass of the shell can be either an internal shell, so it will be the first case. So this is the norm. And if you cut it open and evolve in Lorentzian time, you will see that the shell is always hidden behind the two horizons that you create. So it's a shell that you can't access by simple probes from the outside. So it's like our gold that we hide behind the horizon. If the shell is actually not heavy enough, what you get is this norm, and if you cut it open and evolve, you will see that it leads to a shell that falls inside of the black hole. So you can use it to model, for example, things like black hole creation or fluctuations. So these states are not useful for the microstate construction immediately. So what we will focus on is these very heavy shell states, okay? Good, so that's our family of states. Now, these states are still canonical, so they're described by a preparation temperature. What we want is actually microcanonical states because we are interested in the Hilbert space of a black hole of a certain energy or mass. So what we need as a last ingredient is a microcanonical projection. So to this end, we just assume that the Hilbert space is divided up in tiny energy windows to which we can project using a projection operator. And then we can also create microstates by just projecting our canonical state to an energy window. In practice, we use the saddle point approximation to the inverse Laplace transform. Okay, so these are all the ingredients we actually need. So now we can proceed to the counting argument. So the counting argument is based on a simple idea that we now created states that all look like a black hole, but they have different interiors. So say we take a span of omega of these states with all different massive shells behind the horizon. As soon as we hit a critical value, we expect that these states that we are starting to add to the span are actually not all linearly independent, but they become linearly dependent. And in the end, we should span the full black hole Hilbert space. So we are curious if we can actually find for which value of omega the states that we start to add to the span become linearly dependent. So this we do through the Gram matrix, whose entries are defined as an overlap of two different states. And then the dimension of this span just reduces to omega minus the dimension of this kernel of G. And the kernel of G we can find through the resolvent matrix, which is defined as 1 minus lambda over G. So you see, if you vary lambda, every time you hit an eigenvalue of G, the resolvent picks up a pole, develops a pole. So we are curious if the resolvent matrix develops a pole at lambda is 0. Then we know we are adding to this span linearly dependent states. Okay, so this 1 over lambda minus G can actually be written as follows using n powers of the overlap. And in fact, we can actually look at just a trace of this resolvent matrix. That's already enough to tell us about its pole structure. So we reduce the problem to finding just these n powers of G. If we have that, we can find whether the resolvent has a pole at lambda is 0, and whether then the dimension is just omega and increases indefinitely, and indeed all the states are linearly independent or not. Now, to compute this overlap, you would think you need full control of your quantum gravity theory, and that's true. But what we are going to do is we are going to draw a line, and we are going to use a semi-classical approximation. In other words, we are assuming that can integrate out UV degrees of freedom and end up with just gravity and use the gravity path integral to actually compute these quantities. So at this point, this equation can be schematically written as follows, where each circle is the inner product circle that you remember. So for each power of the Gram matrix, we draw a circle, and that's our boundary conditions that we have to fill in with all possibly allowed geometries, and then do the gravity path integral calculation. At this point, we are actually using a saddle point approximation to it, so we are just going to fill it in with leading saddles. And for higher powers of the Gram matrix, the saddles can be disconnected or connected, so wormholes start to contribute. Now, at this point, we can resum, and in the end, we can find that the semi-classical approximation to resolvent can be fully written in terms of connected contributions to this overlap matrix, which we can compute. So we can write the on-shell action for the wormhole contributions for these semi-classical states that we have under full control. However, even though you can write it in principle, you still have to resum and then find what R actually is and whether it develops poles. So we need to find a way to have a nice expression for this G to the power n that we can resum and actually compute. So to this end, we are going to make use of something we call a pinching limit. It's a limit in which we take these internal shells that we insert to be very, very heavy. Because when you take them very heavy, such a 3-boundary wormhole, for example, reduces to this diagram. And you already see that in the end, diagrammatically, what you get is thermal partition functions of Euclidean ADS black holes of some temperature, n times beta left and n times beta right, where n is the number of boundaries you had for your wormhole. And the shells just contribute a universal term. So n times a universal term, how many shells you inserted. But because we're working with normalized states, this contribution just cancels out. So the shells actually never mattered in the first place. And then if you do a microcanonical projection, the partition functions will lead to the entropy of a left black hole and a right black hole. Okay, so this expression we can plug back into the resolvent equation. We get something like this after resummation, which we can solve, and we can find what the trace of the resolvent looks like. There are two solutions to this equation. One is physical, one is not. And I'm already showing you the solution expanded around lambda is 0. And you see that indeed, as expected, when omega is large enough, larger than this quantity, this resolvent develops poles around lambda is 0. And the number of 0 eigenvalues is given by the numerator here. So we can plug that in, since we now know what the dimension of the kernel of G is, and find that the dimension, as soon as you put enough of these states into your span, is exactly what you would expect. Okay, so this is the counting argument. Now, what can we actually do with it, apart from just showing that the dimension is indeed what we wanted? Well, we can think back to the factorization puzzle, which is a puzzle that's stood for a long time. So what does it say? Well, the states in the CFT, we obviously have constructed states in a Hilbert space of that is factorized into a left CFT and a right CFT. But in gravity, once we started doing calculations, wormholes started to pop up. So from gravity, it was not clear at all. And also, we don't really want to rely on holography to give arguments. So we want to have a gravity argument as to why the Hilbert space here is factorized into a product of left and right. So if the Hilbert space is factorized, we should for sure see it at the level of a trace. So say you take the trace over the bulk Hilbert space of two quantities that depend on the left and the right Hamiltonian, we should see it's factorized. Now, because we work microcanonically, these functions, they factor out anyway. So what we need to see is that the dimension of the bulk Hilbert space factorizes. And thanks to the counting argument, we definitely know that for sure coarse-grained, it does factorize when omega is large enough and you actually span the black hole Hilbert space. But this is not very satisfactory because it only tells us something about the average of the dimension. We really want to know that the dimension itself is factorized into a product of left and right. And actually, we also would like to know what the Hilbert space is factoring in, like what are the two different terms. So we want to have a fine-grained argument. In other words, we want to show that the variance is also zero. So the answer to this is actually 4 papers. So the first paper gives an argument as to why the trace is factorized into DJT gravity, where you do have full control of the perturbative and non-perturbative corrections that depend on G Newton, and you can show that indeed this variance is zero. In the second paper, we generalized these arguments to general dimensions, and we also provided a proof as to why, if the trace is factorized, the Hilbert space actually is. However, it's still not fully solved at this point because we only could show that the variance is zero, but to a leading order approximation, because at that time we didn't have the tools to actually have full control over perturbative and non-perturbative corrections in terms of G Newton in general dimensions. So this is where the third paper comes in, where the authors, Tom and Vijay, they actually developed a new way to show equality between two quantities that are described through the Euclidean path integral by means of just cutting and pasting geometries. So with their results, you actually can show that the dimension indeed factorizes even when you include perturbative and non-perturbative corrections, actually completing the proof. The last paper I include here is a further step actually telling us that the factors of the Hilbert space in which it factorizes are not random, but exactly what you expect. They are the non-perturbative Hilbert spaces they're the non-perturbative single boundary Hilbert spaces. So exactly what you thought from the CFT. So together, they actually solve the factorization puzzle. Now, we cannot go into detail in 20 minutes to tell you what they're actually doing in all these different papers. But what I can tell you is that every single paper relies on this microstate construction and the counting argument. And moreover, it very much relies on actually having an infinitely overcomplete basis. So we don't take omega to be just enough to span the Hilbert space. We actually take this parameter omega to infinity, which is on its own a very curious thing to do working with overcomplete bases. So if you are curious, you can have a look. Okay, so my last slide I would like to show is just further investigations that work with these microstates, which I think are interesting. So the first one is a generalization. They construct microstates for also charged and spinning black holes, so you know you can generalize. The second paper is an application rather. It uses these infalling shells to construct out of equilibrium black holes, and then we count the dimension. The last one is also curious. It's in 2D JT gravity, but it uses the same idea. So the microstates now get an observer added to them, and then you can start to count the dimension of a Hilbert space with an observer, which is very relevant when you think about these closed universes with and without observers and what their dimension is. So there are many more. And also for Outlook, these are just a few things one can try to answer now. But in general, these toolboxes, these tools are developed to understand statistics. So we can do statistics now and understand properties through statistics of Hilbert spaces of black holes. So with that, I would like to thank you.
Thank you very much. questions?
Yeah, I can.
So how much does this like rely on ADS-CFT, or in other words, for like a double-sided Schwarzschild black hole, asymptotically flat, does this also hold?
So there is actually a generalization by this set of authors that I think came out the same day or a day later for flat black holes and fast spacetime. So yeah, it doesn't really. So the only reason why I wanted to have holography is just to understand better what we're working with, because sometimes it's useful to look at it from two perspectives. But yeah, no, it doesn't.
Other questions? If there's not, let's thank Maria.
Can you hear me? So I guess this. Yeah. Right. Yes, very good. Thank you. Yeah, I guess so. Yes.
Okay, our next speaker is Yixian Li from the University of Padua. We'll speak about the statistics of BPS chaos.
Well, thank you, Henning. So before I begin, let me thank the organizers for organizing this wonderful conference and give me the opportunity to present my work. So today I'm going to talk about the statistics of BPS chaos, and this is work in progress with Nate Cheplak, Stefano Masai, and Masaki Shigemori. This talk is about supersymmetric black hole microstates. And as we have learned from this morning, we know how to count them, and we also know how to describe them from the physics of intersecting branes. But today, we are also interested into the collective properties of those microstates, in particular, the late-time quantum chaos properties. We will start with a question: how does quantum chaos emerge out of supersymmetric black hole microstates? So what is late-time chaos, by the way? Well, late-time chaos is a set of properties of quantum states taken collectively. A prime example of such properties is eigenvalue repulsion. So consider a system, whether it is integral or chaotic. You list all of the energy levels of that system and consider the adjacent levels. So En plus 1 minus En, and you look at the statistics of this. What you will find is a different behavior, but depending on whether your system is integrable or chaotic. For chaotic systems, you will have zero probability for degenerate levels, and you will find a maximum for your function, the red curve, which means that there exists a strong correlation between neighboring energy levels. So they will have some kind of energy eigenvalue repulsion at this scale delta. Another piece of data of late-time chaos is the Thouless time. So 1 over Thouless time is the Thouless energy. This is an energy scale at which all of the energies inside this energy scale have some correlation. Therefore, the Thouless time characterizes how strongly chaotic a quantum system is. If I decide to rescale my microcanonical window to be of order 1 in energy scale, if the Thouless time is order 1, it means that there exists some correlation between all of the energy levels in the whole microcanonical window. On the contrary, if the Thouless time is of order n to the power alpha, it means that the correlation is only between some smaller groups. And so, therefore, I would have weak chaos. In practice, in order to determine the Thouless time, what one does is to draw the spectral form factor, and the Thouless time corresponds to the start of the ramp in the spectral form factor. Now, supersymmetric black holes are also expected to have properties of chaos. And it is possible to define chaos for BPS systems. Well, how do we do this? Well, we can replace the Hamiltonian by the BPS projection of any simple operator. So if O is a simple operator, whatever it means, then O hat is the BPS projection, the projection onto the BPS space of O. And one can evolve this, time evolve this with O hat instead of the Hamiltonian, and compute the Thouless time out of the spectrum form factor. Suppose now that in the basis of microstates, this O hat here is written in that form, such that there are zeros in the off-diagonal parts, and the non-zero parts lie only in a band next to the diagonal. What it means is that, suppose that you are one of the microstates here, it means that you can only interact with your nearest neighbors through this O hat. In that situation, the Thouless time is of order of the diffusion time of that problem, which is the size of the matrix divided by the size of the band squared. Now we are at the Eurostring conference, and we kind of know string theory, and we definitely all love string theory. And the question is, can one estimate the Thouless time for the Schrödinger-Vafa-like black holes, for the black hole microstates? For example, the D1-D5P system. Well, what is the D1-D5P system? Consider a space-time of geometry of topology time R4, S1, and T4. Consider some D1 branes that are extended along time, the S1, some D5 branes along time, S1 and T4, and the momentum wave in one of the null-like directions of the S1, such that you have a supersymmetric system. At strong Toved coupling, the brane system backreacts into a black hole solution. Whereas for weak Toved coupling, the open strings on the branes describe a super Yang-Milch gauge theory. The low energy limit of that gauge theory at finite GS is a two-dimensional CFT that is complicated to describe, but one can understand it as a deformation of the D1-D5 CFT at the free Oberthal point. What is this D1-D5 CFT of the free Oberthal point? Well, this is a two-dimensional sigma model on T4 power n modded out by Sn, where n is n1 and 5 is the number of copies of fields on S1. So if x1, x2, xn are the fields on the S1, then the action of Sn, the symmetric group, is to specify the boundary conditions to how to glue the copies together as one goes around the circle. So consider an element G of the symmetric group Sn. Then what the boundary condition tells you is that whenever you go from a copy to another one, when you go around the circle, then you are going to another copy. So you go from a copy to another copy to another copy, and at some point you come back to the copy, your initial copy. This defines you a strand. Therefore, you can have strands of length 1, length 2, and length 3, and etc., etc. So I can call mu, let's say mu I, to be the number of microstates in the number of strands of length 1. I think here they're supposed to have like 3 dots, and 3 dots here, and I think that it disappeared from the PDF. So in the BPS sector has 2 charge and 3 charge states. The 2 charge states are quarter BPS with respect to the 32 supercharges of type 2b string theory, the type 2b vacuum. So it has 8 supersymmetries, and the 3 charge states have 4 supersymmetries, and they correspond to the D1, D5, P states. So if I think about 2 charge states, then essentially I have two steps to do. The first step is to specify how the n copies combine into strands. I have to distribute the winding number n into strands of different lengths. And as a second step, I have to choose a polarization on each of the strands. And I have 16 choices for on each of the strands. Now I can organize the microstates. I can fix n, and I can regroup the microstates according to the number of strands. So on the left, I put all of the longest strands, so a single strand of length n, and on the right, I put the microstates that are composed of smaller strands, so n strands of length 1. So what Shen, Lin, and Schenker have shown is that there exists a simple operator, which is the twist operator, that acts on the 2 charge states in the following fashion. This means that each group only interacts with its nearest neighbor, which means that we have a banded matrix, and the relative size of the band is equal to the size of the biggest group divided by the total number of microstates, and scales like 1 over square root of n. As n goes to infinity, the band becomes smaller and smaller and smaller. So it means that microstates have lesser and lesser pairs to interact with. And so the Thouless time is going to become bigger and bigger. And therefore, they show that this should correspond to a weak chaos system. This is also in line with the fact that the mean value of the strands is proportional to square root of n log n, which means that the most typical microstate sits somewhere in between, between 1 and n. So it has this amount of length of, well, it's somewhere in the middle of 1 and n. But what about 3 charge states? Can you get strong chaos out of them? So for the 2 charge states, the longest string sector contains only 16 states. That's not much. But the idea is that now if you consider 3 charge states, then you have to consider the momentum in addition to this, right? And we know that adding the momentum should favor long string states. And perhaps that now, thanks to the addition of momentum, then the shape of this sigma 2 hat is going to be distorted in the 3 charge case. And what we would like to have actually is that this longest string sector for 3 charge, perhaps it's going to account for order 1 of the total matrix instead of something that scales like 1 over square root of n. So is that possible? Well, if you think about it, we know that on the longest string, there is the effect of momentum fractionation. So all of the momenta on the longest string have units of 1 over n1 and 5. So it means that you have a lot of choice to put on the longest string. And the longest string carries a huge entropy, and the entropy is actually 2 pi square root of n1 and 5 and p. This is the same as the leading order of the black hole. And for simplicity, let me just call n1 and 5 as n and np as p. Okay, so we have a huge entropy, but is that enough for strong chaos? The answer is no, because in principle, you could have that for all of the strands. So the degeneracy for k strands could be exactly equal to, let's say, exponential of 2 pi square root of np for all k, in which case the total degeneracy of the system would be n times this number. In that situation, one would have still the banded matrix, and we will still find that the Thouless time is bigger than something of order n squared. So what we need to do is actually to compute the logarithmic corrections to the entropy as well. And then we can maybe conclude. And in particular, remember that for the two charge states, the mean value of the strands was somewhere in the middle, around square root of n. So now, if we want to have something that looks like this, is it possible to show that the mean value of strands is closer to 1, or log of n, or something like this? Right. So what are the three charge microstates? Well, this time we have to distribute among the strands not only the winding number n, but also the momentum number p and angular momentum j. So on the strands we have, okay, this winding number, this momentum number p, and angular momentum j, which means that on the strands we will have also the winding number n, momentum number n, m, and angular momentum l. And let me call mu the number of such strands. So the number of strands of such strands. And this time the microstates, it consists of decomposing n, p, and j into these factors that depend on mu. How many microstates do I have? Well, this is a counting problem in the microcanonical ensemble. A single strand will carry a degeneracy of, let's say, C. Then mu, so if this is my strand, right, it carries a degeneracy of C. But mu of them is going to carry a binomial factor that depends, well, whose exact expression depends on whether this strand behaves as a boson or as a fermion. And I can repackage all of this into a partition function. So this is what happens for bosons, but I could write the same for fermions. And the idea is to compare the partition function with its developed form. What I can do is that I can look at, for example, the powers. The powers, comparing the powers below and up, will give me the constraints that I talked to you about before. And if I compare the coefficients, then this would tell me that the black hole degeneracy is the number of ways to distribute the charges while accounting for the symmetrization, like the bosonic or fermionic symmetrization. But what we're interested in here is not only this degeneracy, but also to track down the number of strands within the degeneracy. So we have another constraint on the number of strands S. So that's one approach. And the second approach is to go to the grand canonical ensemble. So we can write P, Q, and Y as the fugacities and introduce inverse temperatures. The system thermalizes, and the mean values of mu's is going to depend on the occupation factor and the density of states. The unknowns in this problem are the inverse temperatures, but what we know are actually the black hole charges that we can measure, let's say in supergravity. So N, P, and J, they are known. We can invert these equations and write beta N, beta J, and beta P in terms of N, P, and J. And then the mean value of strands will be given by this expression, and we can deduce also the higher moments as well, and such that the end result will tell us whether we are into a situation that looks more like a weak chaos situation or a strong chaos situation. I could also play the same game, but with the index as the partition function. And if I do that, things get simpler, and they get in a more compact form, such that I can use the modular properties for the automorphic forms and solve for beta n, beta j, and beta p with the index replacing the degeneracy. So writing some fields in terms of N, P, and J, might be familiar to you. This is actually the attractor equations for the axial dilaton. So somehow, to say that the thermalization of the microstates in the ground canonical ensemble with the index as the partition function, this leads to the attractor equations. But what we are interested in is the thermalization with the degeneracy as the partition function. And this will tell us about the statistics of microstates into groups, of how they organize themselves according to groups of different strand lengths. And this, in turn, will tell us about the potential of black hole microstates to exhibit strong chaos or not. So all of this is still a work in progress, but I can already tell you that there is a caveat. This analysis is at the free overflow point. And of course, the strength of chaos can differ whenever I go to higher values of GS. However, we do believe that the analysis is still important because I started with this question: how does quantum chaos emerge out of supersymmetric black hole microstates? And imagine that we find that, I don't know, like there is already strong chaos at free orbital point, or on the contrary, that we find that there is not strong chaos at free orbital point, then this will tell us something, right? It can tell us about whether strong chaos can only emerge as a gravitational effect or not. And by the way, if the answer to this question is yes, then another question that is still very relevant is how far away from strong chaos is the free orbital point? So I think I can conclude. So we have looked at the possibility of strong or weak chaos for D1, D5P systems. We have shown that this is related to how the microstates organize themselves into groups. And this is related to the logarithmic corrections of groups of different strands. All of this is related to, gives us a statistical physics problem encoded in the density of states at the free orbital point. And it has two aspects. The first as a counting problem in the microcanonical ensemble, and the second as a thermalization problem in the ground canonical ensemble. And as an outlook, the statistics of BPS chaos can teach us several things. First, it can teach us about the lifting problem, about the statistics of the states that become non-BPS when one tunes GS to be non-zero values, depending, let's say, on the value, on the number of strands that decompose the microstates. Secondly, it would be interesting to go and talk to the fortuity community. So if you think about fortuity, usually it's something that depends on only n, whereas here this analysis of chaos seems to depend on n and p, and above all the formulas are actually almost symmetric between n and p. So is it possible to define a notion of fortuity that depends on n and p and see that there is a symmetry between n and p? And to end this talk, I'll go a little bit speculative. Perhaps you could tell us about the swampland. So we don't know what is the origin of the distance conjecture, well, what if the principle behind the distance conjecture was that the minimal black hole in an EFT should have strong chaos? Thank you very much.
Thank you. Questions?
Thanks for the nice talk. So in this index example that you mentioned,
yeah,
one might expect that there is no strong chaos. Does that bear out?
So we are still doing the...
Because that should be easier to do than what you eventually want to do, right?
We are still doing the computation.
Even for the index? I see.
Yeah. There's something that I would like to talk to you. It's about the lifting problem. So we are finding that there is a number of states. So in the degeneracy of the longest strands, we find that there is more states in the longest strand sector at the free orbital point than the black hole at like the black hole solution at non-zero. So I wanted to have a chat with you on, because that would mean, if we are not mistaken, that even on the longest strand, most of the states are going to become to lift, and well, this is a surprise for me. So yeah.
Another question. So one thing you said was very interesting, that if this chaos doesn't arise at the free point, we expect it at the gravitational point,
right,
then you can try to estimate where it comes. So you said at what distance will it appear?
Uh-huh.
How are you thinking of calculating that?
Well, okay, maybe this is related to my PhD, where I did my PhD. But usually we think of those kind of black hole microstates as some kind of fuzzball solution, so with a very deep throat and with a smooth cap. I mean, even if it's not, well, the idea is that between the asymptotics and the smooth cap, there is a huge blue shift, right? So if you think about this sigma 2 operator in the gravity sense, then the equivalent would be that, okay, so suppose that you start with some Lewin-Method geometry, and you Fourier decomposed its shape. And so the idea of the sigma 2 is that you would change one of the coefficients of this of this shape. Now, if that's your operator from your very far away from infinity, then there's a chance that whenever this action goes to the deep into the throat, then actually it talks to all of the different modes. So this could be one of the possibilities. Yeah.
Okay, there's no further question. Let's thank Yixan again.
Yes.
So it is, yeah.
Okay, next speaker is Viktor Misnyavkov from Nordita, and he'll talk about the Coulomb branch of n=4 and integrability.
Okay, thanks for the introduction. I'd like to thank the organizers for putting up this conference and giving me the opportunity to present my work. So I'm going to talk about some work that is based on this paper and related to the Coulomb branch of n=4 super Young-Mills theory. So let me start with a few introductory comments. So super Young-Mills theory has many nice features, some of which were highlighted and will be highlighted at this conference as well. So such as integrability, holography, and many others. And these are reasonably well understood at the conformal point, or in other words, super Young-Mills theory as a conformal field theory. What we are interested in is to study this theory in a symmetry breaking vacuum, so in scenarios where conformal symmetry is broken. And well, there are actually many examples of such scenarios, and quite often they lead to defect CFTs, which we also heard about. In our case, the symmetry breaking pattern is going to be a bit different. It's not going to lead to any specific defect theory. So let me just explain the setup straight away. So in the gauge theory, we have the scalar fields of super Young-Mills theory, which can be given a vacuum expectation value based on the shape of the potential. And a very simple way to give a VAV to the scalar fields is to choose the following classical solution, where we only have one non-zero matrix element for these fields. And well, while, of course, everything is rotationally invariant, it's sometimes useful to just choose this vector to stick in one specific direction. So some of the formulas will use this. Oh. Okay, so, well, by giving this expectation value to the scalar fields, we break conformal symmetry, but conformal symmetry is broken in a sort of homogeneous way. So it's broken to Poincare symmetry. So there's, contrary to the defect scenarios, there's no residual symmetry in any direction, but there's also no preferred direction. And then the gauge symmetry is Higgsed, of course. where this gives us a bunch of massive fields from the fields with indices 1j. So, but for j not equal to 1, because this 1, 1 slot actually is responsible for this u1 factor over here. So in the holographic picture, in the dual picture, this scenario corresponds to taking one of the D3 branes in the stack and moving it away at a certain distance. And well, it's going to be positioned in the ADS space, a coordinate that is related to the vacuum expectation value, which we can sort of compute by equating the tension of the strings that can now extend from the brane stack to this probe brane to the mass of the W boson, so to the massive particles. So this scenario is interesting for a few reasons. One is, of course, just to study holography and integrability beyond conformal symmetry. So it's broken here. This is the same motivation, for example, that appears in the study of the defect scenarios. Also, this theory is kind of closer to realistic ones because it has massive particles, broken conformal symmetry, and has nice properties in terms of its spectrum and the S matrix. And then the most natural objects to study in such scenarios are one-point functions of operators or condensates, and these are also important objects in QCD, for instance. So although, of course, this scenario will not give any immediate consequences for QCD sum rules, it's still interesting to study. So one of the main things to do is to compute one-point functions of operators, and that's what I'm going to talk about partially. So there are two kind of distinct cases. So first are the protected operators, for example, the scalar chiral primaries. So these are not particularly interesting in a sense. They are tree-level exact. Well, they are protected, so they don't renormalize, but also their one-point functions turn out to not have any loop corrections. And well, they also coincide with the holographic computation, which I don't present here, but it's pretty standard. It's pretty similar to the standard holographic computation, except that the gravitational action is modified by adding the D3 brane action, the probe brane action. So since it doesn't receive any loop corrections, it means that basically the one-point function corresponds to substituting the field with its vacuum expectation value. So other operators that are non-protected, they receive loop corrections, which is kind of richer. So I'll present everything using the example of the Konishi operator, this one. And so since we know that these operators are renormalized by themselves, it's important to include the normalization factor. And when we compute their one-point functions, we need to deal with this renormalization. And there are two, I guess, most important things to consider. So first of all is the question of the finiteness of these one-point functions. And interestingly enough, it happens so that there's no extra renormalization coming from the vacuum coming from the one-point function. All the divergences can be accounted for by renormalizing the operator at the conformal point. This is, well, I don't know if this is a theorem, but I guess, well, at least in this case it's true, but probably also in other scenarios with spontaneously broken conformal symmetries, contrary to, for example, breaking conformal symmetry by just adding mass explicitly. So the other question is scheme dependence. Since we want to extract the finite parts of these loop corrections, and these are often scheme dependent since we will renormalize things. And we want to extend these loop computations to such things as integrability, for example. And of course, therefore we want a scheme independent result. And it turns out that to deal with all these problems, it's useful to define the renormalized one-point function in the following way, where we compute the vacuum expectation value on the Coulomb branch of the Baire operator, And then we divide by this factor, which is computed, as you can see here, there's no v subscript. So it's computed at a conformal point, which means that the x dependence is canceled by this prefactor here. And this expression turns out to be finite, but also it's explicitly scheme independent. Because, well, at least within multiplicative renormalization, whatever renormalization factor you add is going to cancel here. So we compute this, and, well, this is the result we get at one loop. And it's better to present it in the following way, where we kind of take into account the dimensions of this operator. So we have v to the delta k, where delta k is the anomalous dimension to one loop, and then ck is kind of the kinematic data here. So this is just the result of a one loop computation. Interestingly enough, there is this Euler gamma factor over here, which kind of typically appears as a scheme-dependent contribution in loop computations. But this, as I said, this result is scheme-independent, and in fact, this gamma factor is later reproduced by integrability. So the first hint of integrability at loop level is that, well, now in general, expectation values of operators to one loop can be presented as an overlap of the in the spin chain language, it can be represented as an overlap of the state corresponding to the operator with a boundary state, and this boundary state turns out to be integrable. So it's annihilated by an infinite number of conserved charges. So, well, one-point functions are not the only interesting object, and we also did study two-point functions a little bit, and the two questions that one can address here is the short and long distance expansions. So for the short distance expansions, it's interesting to study the OPE and the relation between the OPE and the vacuum expectation values. So if we take, for example, this simple BPS operator, z squared, and then consider the following OPE expansion, then we expect to see contributions of the following operator, well, the identity, this O tilde is another BPS operator, and then the Konishi. So interestingly enough, for example, so now we're going to take the expectation value of this expression, and since we're in a Coulomb branch, this left-hand side will not be trivial. It will contain all the one-point functions of all these operators. And interestingly enough, we have parts here that correspond to operators that are not renormalized and to those that are renormalized. Well, obviously, the two-point functions have loop corrections, even though the operators are not renormalized. But anyway, it's an interesting interplay. So when we take the expectation value at the leading order, we compute the following diagrams. Well, something which is not drawn here is that in this middle diagram, due to the way counting works in this vacuum, this diagram over here contains a massless propagator, but this contains the massive propagators. So this is the kind of interesting part, which is, well, specific to the Coulomb branch. So when we do this simple computation, well, we expand the massive propagator to a few first orders. We need also the structure constants, which I did not write explicitly here. We need them to one loop order. And then if we write out the result of computing this two-point functions and contrast that to the OPE, we find that the consistency of this expression requires that the following equation holds. So here I specifically wrote it in a way as if we don't know these quantities to kind of illustrate that the consistency conditions require that the one-point function of the Coulomb branch requires well, a specific value. So it can be thought of as an equation where we compute some of the quantities and then determine the rest via this consistency. And funnily enough, actually, to find the anomalous dimension, we don't even need the structure constants to one loop. We just need the massive propagator, since this diagram is just a square of the massive propagator. So we kind of compute something that is one loop without computing any loop integrals. But this is an interesting observation. So by analyzing these expressions, we find that one loop corrections do not spoil the convergence of the OPE. Well, at least in this sense where we evaluate the OPE in this vacuum. And this motivates to, well, to think about this idea of a kind of Coulomb branch bootstrap, or maybe called something else, where we can consider two regimes of our two-point functions. One is the short distance expansion, which gives the OP, and then we can sort of predict the structure of the long distance expansion, something that will also appear in the next slide. And then comparing this expression, equating them, we can set up equations on this OP, on the CFT data. So we can kind of figure out what conditions on the CFT data can allow Coulomb branches. And so one exercise that we did is a crude estimation of how the OP data should grow. And then in this paper, it was shown more specific examples were considered, and what they got was actually in agreement with this estimation. So at large distance, well, something that we can check in this scenario is something called the Dilaton word identity. So, well, since we have spontaneously broken conformal symmetry, we expect a dilaton. And in fact, we can predict on general grounds what the contribution of the dilaton should look like. So it's this part over here. So the power law behavior at large distances can be predicted. And well, this should hold in principle at any loop. And something that we managed to see that this constant over here, which is kind of the characteristic of this dilaton decay constant, it's not renormalized at one loop at least. So this can be in principle kind of further studied in this scenario. So going back to integrability, well, integrability of super-Yang-Mills itself has different incarnations. It can be shown that, well, there's a spin chain description at the loop order, which can be extended to any value of the coupling via such approaches as the quantum spectral curve. Then there's the string sigma model, which is also integrable. And, well, to show integrability on the Coulomb branch, one has to kind of show one has to go through all of these. And so these were actually shown in a few subsequent papers by some of my co-authors and their co-authors. So integrability at, it was shown that this overlap formula with integrable boundary state can be extended to generic coupling up to Sankavitz by Coronado, Komatsu, and Zarembo. And then the string sigma model with this bulk D3 brane was shown to be also integrable in this paper. And then something that I didn't mention yet is that one can study amplitudes or deformation of super-Yang-Mills amplitudes to the Coulomb branch. And it turns out that these also have some integral properties. Mainly, they retain some of the dual conformal and Youngian symmetry of the super-Yang-Mills amplitudes. So just to recap, so it's safe to say that this Coulomb branch configuration is integrable. It has many interesting implications. So it would be interesting to study other observables. And in particular, it would be interesting to address this other question that I highlighted about the relation of OPE and condensates, and maybe within this integrable framework. And then something that I did not talk about, but well, it's in the paper, is the relation of this Coulomb branch configuration to large charge operators. So this is something that I'm not going to touch. Yes, thank you.
Thank you. Questions? There's one. Yeah.
So the coefficient for the 1-point function that you had, the CK, this
yes, sorry,
the one loop. Do you know what's the behavior of that coefficient, that strong coupling? You know, from a string theory argument, do you know? Is it lambda to some power or?
I couldn't say at the moment, I think, but yeah, I can look it up and yeah, let you know.
Well, going back to the 2-point function that you showed expanded in OPE, like, are there any properties of the 2-point functions that are not enjoyed manifestly by the OPE, which could then be leveraged for Bootstrap?
Properties of the 2-point function, which
For
are
example, at finite temperature, the 2-point function would be periodic. The OP itself is not, every term is not periodic, but you can use this as a consistency condition.
Well, I would say, for example, the statement about the convergence of the OP can be studied by looking at the properties of the, because you have a kind of exact result, and you know, well, in this case, it's just like Bessel functions squared, and you know that they have an infinite radius of convergence, for example, and you also know the structure of their large X behavior, for example. So you can, from the short distance expansion, you wouldn't be able to tell immediately, and that's basically how you can set up this kind of bootstrap equations.
Okay, thank you.
Can you say more about the holographic computation, which you can check the full protected sector?
Well, we checked the chiral primary operators, and well, the computation goes pretty straightforward. So you simply modify the gravitational action by adding a D3 brane action, and then you do the same computation you would do for the conformal point. And so, well, yeah. The only difference being that now you are computing a 1-point function, which in principle you wouldn't do on the conformal point because it would be 0. Yeah.
Okay, if there's no more question, let's thank Victor again. And we resume at 3:50, 10 to 4. Okay, let's start the final session of today. Our speaker is Romuald Janik from Krakow, and he'll speak about the Ising model, gravity, and the black hole information paradox.
Okay, thank you very much. So first I'd like to thank the organizers for allowing me to present this work. So of course, the main topic of my talk is the Ising model, which is arguably the most famous exactly solvable system in statistical physics. And of course, the corresponding conformal field theory is also exactly solvable, and it's basically the simplest possible CFT that we have at our disposal. So one could think that if it would have a holographic dual, then one could imagine that this holographic dual would be extremely quantum because it's equal to 1/2, as fast from C infinity as possible. So it would be like a kind of quantum soup and so on, so very difficult to interpret. So what I would like to try to convince you during this talk is that if one looks at a specific observable in this theory, then one can really extract some insights into quantum gravity with matter in this context, which might be relevant for the black hole information paradox. Okay, so the outline is as follows. First, I'll give some motivation. So here I would like to define what I mean by gravity and also motivate the setup that I will be using. Then, of course, I will have to address the question, do we have holography for various minimum models at all? And of course, here by holography, I do not mean classical holography, but on a fully quantum level. So it's a dual description, which may be completely quantum a priori. Then I will discuss this particular Ising model observable, which to some extent agrees very nicely with black holes and black hole physics, but also it exhibits some completely strange properties. And then I would like to try to give an interpretation, bulk gravity interpretation of both of these properties and give some conclusions. So, of course, the main point is to use holography, use ADS-CFT as a tool to learn about gravity. So we are using the equivalence from QFT on the boundary to the bulk theory with gravity. So here, first of all, I have to specify what do I mean by gravity here. So here, gravity, if one follows this route, means that it's really a subsector of bulk theory, which is dual to the energy momentum tensor. So this gives us really a definition that what holography means by gravity. So at this stage, therefore, I will not take any presuppositions about what gravity should look like, but just try to extract from the QFT, from the CFT, what properties will appear. So one consequence of using this route is, in fact, that generically this is not pure gravity, but always it's a gravity with matter, with a specific matter system. And ADS-CFT provides, in principle, a fully quantum definition of the specific gravity plus matter system. And as you will see later, it turns out that, in fact, the matter sector will turn out to be extremely important and extremely surprising, perhaps in contrast to the gravity sector. So, what will turn out to be the most interesting is how gravity and matter together interact within ADS-CFT and following the constraints of ADS-CFT. Okay, so why is this difficult? Typically, we have like dichotomy because we have to need good control of a CFT to have computations, and also we need semi-classical gravity regime for good interpretations. So the reason for that is not really that we really need semi-classical gravity, but we need to understand what we are computing. In particular, if we could, for example, do perturbative computations at low NC in n equal to 4 sperm-mills, we get some answers, but we have no clue what they mean on the bulk side. So the semi-classical regime is for interpretation, and once we know that, of course, the main interest is to go as far from classicality as possible and to really have the deeply quantum regime of gravity and matter. And in fact, this is the motivation for this is, in fact, to look at the Ising model CFT because it seems to be as far as possible from ordinary holography as possible. So let's look at those points which I mentioned earlier. So first, it's exactly solvable. It's clear, but it's very far from C going to infinity. So it would seem that we are in this quantum soup-like setup. However, if we consider the theory at large temperatures in units set by the cylinder size, then in fact it turns out that it's approximately semi-classical. So I will later describe it, say it a bit more precisely in what sense. So we can recover at least some semi-classicality and some geometrical interpretation in the large temperature limit. Okay, so what about holography? So here, 3D gravity, I consider like a pair of SL2R Chern-Simons theory. And now one can give a very fast heuristic argument why we expect to have a dual to the Ising model or to other Virasoro models. So first of all, if we impose asymptotically ADS boundary conditions on the Chern-Simons, then on the boundary side, this corresponds to taking the Westerminer-Witten and setting the current J plus to equal to 1. And now we can move back like 35 years ago to the paper of Bershatsky and Oguri, who exactly considered setting SL2R Westerminer-Witten with J plus equal to 1. And then they showed completely on the quantum level that this is equivalent to a Virasoro minimal CFT. Moreover, it is also extended not only to the vacuum representation, but also for the matter representations. And then the matter representations here correspond in a standard way on the Chern-Simons side to Wilson lines, sorry. So in this sense, we may expect to have really a dual to Ising model to Virasoro models. But of course, the cause is that this Chern-Simons is quantum. So we should somehow deal with quantized SL2R Chern-Simons. So this is, of course, complicated, difficult, and so on, but we can, it's not to take a shortcut, and let's take a holographic quantization of Chern-Simons. Namely, we can represent the gauge fields of the Chern-Simons as concrete operators in the boundary CFT, where although this B is some gauge function, here we have the energy bound tensor of the CFT. So now this expression is really as good in holography as it gets because it's just an operator in the CFT. So now since it's an operator in the CFT, we can, for example, evaluate the thermal average of this expression. If we evaluate the thermal average, we will get exactly the BTZ answer. So we see that the state on the average is a BTZ black hole, right, with the metric which can be obtained in the following way. Now, of course, this may be widely fluctuating BTZ around this average. However, we can see that this approximates semi-classicality at high temperatures. Namely, if we take the expectation value at finite temperature of the product of T's, it factorizes up to exponentially small terms. So for distances which are like of order 1, therefore, basically, it's just like semi-classical. So it's a bit weaker than C going to infinity, but it's still quite good. Okay, so the bottom line from here is that we expect, if we are dealing with high temperatures, to have a dual black hole, which is approximately, to some extent, like semi-classical. So if we have a black hole, how we can probe it? So on the gravity side, the most natural way to probe a black hole is just to throw matter into it and see what happens. Now on the CFT side, this corresponds to perturbing the thermal density matrix by some delta rho, which we construct in terms of some primary operator of the CFT. And then we study its temporal evolution. So we let it evolve and measure, for example, expectation value of epsilon of t as a probe of what happens. And here in this talk, I focus on just linearized quasi-normal mode dynamics. So I don't look at back reaction and things like that. Just linearized perturbation, linearized on the linearized level. Okay, so now let's specialize to the Ising model, and let's look at this observable. So the Ising model is very nice because this observable, in fact, can be computed analytically. So I will show a formula on the following 2 slides. But first, let me just describe the pictures. What happens? So here we have time. So here we have our starting point. The red line is our analytical formula. And here we are looking at the expectation value of this boundary operator epsilon of t. So first we see that we have like an exponential decay, which is as one we would expect from a quasi-normal mode, where something just exponentially gets absorbed by a black hole. Yes? Energy operator, so 1/2, 1/2, yeah. So then it turns out that it does not go down to 0, but there's a very small plateau. So there's like a quantum halo, which will have some interesting interpretation later. So for the moment, everything is kind of what one would expect. But then some strange things happen. So first there's some kind of burst. But then if we go to 2 pi, suddenly we see the whole signal reemerges again completely. So this is very strange because here we see that it behaves like it would be absorbed by the black hole completely. But then suddenly we have the intact signal reemerging again. And moreover, it's very strange because it's not really kind of encoded in a complicated way, entangled and so on, but it just comes out just right on the nose in exactly the same form as we started from. So the main question here is to understand what happens. Can we understand this on gravity? So both the absorption from a black hole and its reemergence of this intact signal. So first, before I come to that, let me just comment on what is the CFT origin of this periodicity. And because this is something which is very easy to understand and it's obvious. So this is just the formula which we can get, which is obviously periodic. But looking closer, we call that if we are on a circle of 2 pi, of radius 2 pi, then the level spacing is just 1. Therefore, if you take an evolution with respect to 2 pi, it's just identity, right? So therefore, this time of periodicity is just the inverse level spacing. And of course, it also corresponds to the boundary graviton. So therefore, this is like quantum gravity-like effect, which depends on the spacing, quantized spacing of the levels of the graviton, where we have a recovery of the whole signal again. T is real. It's physical time. So it's not Q. So it's theta function. So it's a theta function. The Q modular parameter is related to the temperature. Well, this is just the argument. Yeah, so T is just it's a theta function. It's not a theta value, but it's a theta function. Yeah. Okay. And in the case for minimum models, we have exact periodicity because we have a finite set of deltas, which are rational numbers. So therefore, we always have a periodicity, irrespective of what states we are evolving. So this is really a generic feature in all minimum models. Okay, so now, so from here it's kind of obvious, but of course, we have this black hole information paradox. Like pure state collapses, evaporates, this mixed state, and the question is how this information can be obtained here if the causal structure is kind of with complete with a complete evaporation of this black hole. Here we are not really looking at that, but there's a variant which was discussed by Maldacena in this eternal black hole paper, where we have a thermal falls into a black hole and then it emerges intact. So again, we have like a mismatch between periodic unitary evolution and a complete kind of recovery, therefore the complete recovery of information from the black hole and the black hole causal structure. So how to reconcile these two features? So let me now move on to the gravity interpretation. So recall that gravity would be the A and A bar Chern-Simons gauge fields, which involves this energy momentum tensor of the CFT. While the matter fields are Wilson line networks. So they are Wilson lines which are charged under both A and A bar, which appropriate conformal weights. And also we have trivalent junctions which correspond to the OP of the CFT. So this was studied a couple of years back, this type of approaches. But it was not used for finite temperatures. It was usually used in the C going to infinity limit. So here, instead, we are just using the same kind of formalism, but at finite temperature and low central charge. Okay, so if we look at the quasi-normal mode regime, then basically the answer can be obtained from a two-point function of epsilon operator. So this is the boundary. This is the singularity of the Chern-Simons solution. And here we have the Wilson line of A, the similar one of A bar, the Hermitian conjugate, going like that. And now if we evaluate it by exponentiation of in the thermal density matrix, we get this type of answer, which behaves like an exponential e to minus 2 pi temperature times T. time. And of course, it agrees with the quasi-normal mode of the appropriate BTZ black hole. So we have in this way this complete absorption of the signal as we would expect. Now, the plateau is more interesting because it is no longer universal. Because here we use the fusion rules, namely that epsilon can split into sigma and sigma, and then sigma can, this loop can encircle the singularity in order for it to be non-contactable, and then go here again and go down. And here one can evaluate the magnitude of the sigma loop, and it turns out to be like E2 minus pi squared over 2 times temperature. And this, of course, agrees with the CFT answer exactly. So the per factor here is a bit more complicated. Now, the sigma loop is really reminiscent of a scalar loop around the horizon, which was evaluated by Krauss and Maloney, which is given by this formula. And if you plug in delta equal to 1/8, one gets exactly the same answer. So again, here we see that both the quasi-normal regime and the plateau in the Ising CFT can be understood very well in the gravitational black hole interpretation. And sigma loop is a quantum matter effect in the BTZ black hole. Okay, so now the periodicity, which is the main puzzle. So here, of course, we should include now windings and sum over the windings. If we incorporate anti-holomorphic part, we get this type of formula. And this, in fact, agrees with the scalar Green's function from the BTZ black hole to methods of images, but it doesn't reproduce periodicity. This is natural because if we have a scalar field, it gets absorbed into the black hole and it doesn't reemerge again. So something is wrong. But now recall that we have an exact solution, for exact formula for the two-point function in the Ising model. So we can just look at this solution and see what is its high temperature limit. And it turns out that it's something like that. So you see that here we have exactly similar kind of formulas, but we have different independent windings. So from this answer, we can read off what are the allowed windings of the holomorphic and anti-holomorphic Wilson lines. And in fact, in terms of Wilson line networks, what it shows us that they are independent. So instead of what I showed you before for scalar field, we have independent windings of holomorphic and anti-holomorphic gauge fields. And in fact, CFT forces us to pick this choice. And this gives for us the recovery of information from the black hole. So now what does this mean? What are its consequences? So first of all, we call that these Wilson lines are really something like first quantized matter. So what this really shows us is that the matter field, which is dual to epsilon, is not a single scalar field, but rather it's a pair of fields. One of them interacts only with A and the other with A bar, because they can just wind independently. Now, this looks technical, but it has a clear consequence. Namely, recall that in Chern-Simons gravity, the metric and the horizon, the causal structure, is encoded only in both A and A bar. So if we have a field which couples only to one component, one gauge field, it just ignores, it does not know about the horizons. Right? So this is extremely surprising. So somehow we see that the CFT forces us to have this type of very strange matter field coupling. So basically this black hole information paradox is no longer a paradox because somehow this causal structure is not like a crucial ingredient of the formulation. However, for small times and zero windings, right, if there would be no singularity here, of course we could just deform this line to this situation, and the system would just evolve like with an ordinary scalar field. So just like ordinary gravity that we would expect. Okay, so some further comments. So perhaps the very strange surprise which came from this computation is that evading this paradox is not due to some mechanism within gravity, but rather with the specific properties of coupling of matter to gravity. Secondly, so the role of the Chern-Simons gravity, in fact, makes this possible because the metric is not a fundamental object in its formulation. Right, so one can imagine if you have a pair of Chern-Simons to have a coupling of a field to one Chern-Simons and a coupling of a field to another Chern-Simons. And it's very natural if we forget about this interpretation of metrics. finally, I gave here the argument using this Ising model, which is extremely quantum, but one can argue that this should hold for any two-dimensional CFT, also for large central charge. And one can argue that from properties of like torus blocks. Namely, there's always like a universal pair of torus blocks which would contribute to a two-point function at finite temperature. And each of the holomorphic parts is individually quasi-periodic, so periodic up to some simple phase factor. So therefore, the only way to ensure this independent periodicity is to ensure independent windings of the holomorphic Wilson lines and the anti-holomorphic Wilson lines. So therefore, we could see it in the Ising model because we had an exact formula, but it seems that this formulation of matter fields should hold for any theory, two-dimensional CFT. Okay, so let me summarize. So first of all, like I argued that one can use the Ising model to get some insight into quantum gravity with matter. And what turns out to be crucial here is that this metric is not a fundamental concept of Chern-Simons gravity. So I always thought that this is just like an accident, so it doesn't really matter. But here somehow this feature seems to be extremely crucial because the CFT dynamics seems to really require the coupling of matter, which somehow ignores the metric at first sight. So gravity does not really behave like gravity that we would expect. However, for trivial topologies or zero windings, right, or small times with respect to the inverse level spacing, everything is as we would expect from conventional gravity. So this is like the main kind of observation that we have, that something which looks like gravity on so small times, like at long scales here, seems to have completely different properties, and the mechanism of reemerging information is completely kind of encoded in this strange coupling of matter. So there are lots of open questions in fast directions. For example, other CFTs, breaking conformality. Here there may be a very interesting link with integrability because one knows if one takes minimum models, breaks conformality, there are also integrable deformations. So there should be some TBA description. So it will be very interesting to understand what this corresponds to on the dual side. Now it's extremely interesting to look at high dimensionality because one can look at ask the same question for n equal to 4 supermills on a sphere. So now if we add weak coupling, we know that the levels are also equidistanced. Therefore, at high temperatures, we will also have periodicity. And we know also that there's a Hagedorn transition here, even at weak coupling. So also it's an extremely intriguing question, what happens here? But of course, we do not really have a gravitational description, right, which will be valid at weak coupling. So this is but it's a very interesting problem to try to follow it in high number of dimensions. And there are, of course, lots of technical issues which would be nice to look at in this 2D CFT, on the 2D CFT level, like space-time interpretation, perhaps have some exact proofs or exact evaluation of Wilson lines, including all the contractions which T, so to be able, for example, to prove really that one exactly reproduces the full quantum answer of the Ising model from the Wilson line networks. So there seems to be lots of interesting questions to investigate. So thank you.
Thanks, question.
I have two questions. You indicated that in the case of the Ising model, you get this periodicity because the spectrum is rational.
Yes.
What would happen if the CFT is not rational? That's one question.
Yeah.
And the other is, it has to do with specialties of three-dimensional gravity, because as you know, if you try to couple a minimally a point particle, you cannot do it in the formulation that you have.
Yes. Mm-hmm.
So how important is this in the story?
Okay, so I would say that, so in general, like, I don't expect to have periodicity, but I expect to have like this type of behavior. So there will be some contribution which will be periodic, but on top of it, there will be lots of other contributing torus blocks, right? Which would break this periodicity. However, the conclusion that there should be independent windings would hold. So for me, the main conclusion is this independent windings. For the Ising model, it's like an accident that this exactly coincides with periodicity. But I think so. This will be the main point here. Now for high dimensions. So for me, it's fascinating. So I don't know what would happen. That's why I would like to look at n equal to 4 super mills. So at least on the QFT side, at recoupling, there's a Haganon transition. So there will be something like black hole in quartz. And there's periodicity also at zero coupling. But whether one can use some higher spin version variant there, it's very interesting, but I don't know how it would look.
Yes, thanks. It was really beautiful and enlightening. We do have a few calculations of correlators in high dimensions in the Owen model and some sort of toy model of super young mills, or just scalars. And some of the features that you describe, of course, appear there too. But we don't have the same nice interpretation, but maybe you can help us with that.
It's
Flowers and collaborators.
Okay. Yeah, thanks.
Thanks. It was a very provoking talk. This independent winding that you're discussing, if you have a 2D CFT with a large central charge, will that be suppressed by 1/c? And if so, how?
I don't think it will be suppressed.
You think it won't be suppressed?
It won't be suppressed. But so because I think like this, right? Of course, I don't know what is the magnitude of those conformal blocks, because I never saw the computation of those.
The reason I ask is at large C, you do expect a gravitational interpretation. Things could become closer and closer to a notion of a metric.
Well, but I guess that here, I would say that, so my suspicion would be that like this would still kind of hold, but this would be swarmed by lots of other interactions between lots of other primaries, because there are lots of primaries and so on with lots of non-zero OP coefficients. And all of those will kind of swamp this contribution.
If you can average, this thing will be suppressed.
It will be smaller, yes. It will be smaller than, yeah.
So what is your interpretation of the burst after half the period? Of this burst that you showed after half the period?
So in fact, it seems to, it would come from this graph. However, from this graph,
this is the plateau.
Yes, so this is the plateau, but the plateau, so here I couldn't compute the prefactor, the coefficient. To get the coefficient, one would definitely have contributions from contractions here, along those different lines, but they are kind of localized. So to get the burst, one would have, I think, contractions between those lines here, definitely. So it will be very interesting to get, but so they should follow from here, but one really needs to go beyond the classical evaluation.
Thanks for the talk. I got confused in the beginning. So when you mentioned Bershadzky-Oguri, when you do the Hamiltonian reduction, you actually land in the irrational range of central charges. So central charge is bigger than 25. So you never land on a Virasoro minimum model. To land on it, you have to start with SU2 at admissible level. So I'm wondering what the motivation is. I mean, we can study Ising model, that's fine, but I don't understand the motivation why that's connected to SU2 Archer and Simon's theory.
Well, so as far as I remember, like in Bershadzky-Oguri, they made on a completely algebraic level, right? They made computations that the Virasoro representation of the minimum model with C smaller than 1 can be mapped to some particular representation with some I don't remember the parameters.
That's right.
So they may be a bit bizarre, those parameters on the level of the Simonowitten, but still they exist. And then one has exact matching between the homology of BST and this one. So it is the claim of, I would say that like the claim of Bershadzky-Oguri was that there's a hidden SL2 symmetry in a conformal field theories. In fact, a posteriori, I would say that this hidden SL2 symmetry is just kind of dual gravity, like holographic gravity. So like it's kind of presupposes or precedes IDS CFT in a beautiful way.
Thanks.
Okay, I think we have to postpone the rest of the discussion to later. Thanks a lot.
Perfect. Yeah.
Okay, our next speaker is Jackson Fliss from University of Cambridge, who'll talk about minimal areas from entangled matrices.
Okay, yes, thank you. And thank you everyone for being here. I'm very excited to be here and to tell you about this work, which really has at its heart a question that drives the iframe-cubic community, which is how does geometry emerge from information? And of course, we've heard a lot that this really has roots in Bekenstein-Hawking, who told us that black holes are thermodynamic and they have an entropy that scales like the horizon area. Of course, this question is more foundational than just black holes. And sort of the centerpiece of this is in the ADS-CFT correspondence with the Ryu-Takayama formula, which tells us that a microscopic entanglement entropy, namely the entanglement entropy of a region in a CFT, is given by some geometric quantity in the bulk. It's given by an area of a minimal surface that extends from this region into the bulk. And I think what's a very interesting fact about this formula is that this surface is not determined a priori, or at least in any obvious way from the CFT, but it's really picked out dynamically by bulk effective field theory, e.g. using a semi-classical gravitational path integral, a la Lukowitz and Malsena. And so I would like to look underneath the hood of this mechanism a little bit. So I think to have a proper understanding of Ryu-Takayama, we should really account for several features of this formula. The first is this area as state counting. It'd be nice to have sort of the same level of rigor that we have for black hole horizon microstate counting. And thank you, Samir, for the very inspiring review on this morning. I would also like to have an understanding of the appearance of this inverse coupling as opposed to, say, a UV cutoff that we are often seeing in entanglement entropies in quantum field theory. And of course, this stems from the fact that we're really counting a finite number of degrees of freedom in this entropy, but it's reorganized in a way that is tells us something about the bulk effective field theory. Somehow all these degrees of freedom are organized into some bulk effective field theory, and that's why it appears as a coupling. And lastly, and importantly, I would like to understand the appearance of this minimization problem, why it picks out a minimal area. And of course, if we think about this, this has something to do with diffeomorphism invariance, right? We can't pick some fixed fiducial surface. We have to pick a surface that sort of minimizes things. But this is subject to some gauge invariant condition. And here in ADS-CFT, of course, the gauge invariant condition is that we fix a boundary region of the CFT. So in this talk, I am going to try to explain how these features can arise in certain theories of matrix quantum mechanics. And since this is a strings conference, I should also mention that, of course, matrix quantum mechanics has a rich history in string theory. And in particular, there's a rich history of finding emergent spaces in the quantum mechanics of large N matrices. The models I'll be thinking about all have a very similar structure that can be arrived at from dimensionally reducing super Yang mills. They have some collection of n by n matrices they'll call X. The Lagrangian has a kinetic term, and then some potential terms which will usually include a commutator square. And we can really think that these models describe the dynamics of emergent D-brane world volumes. So if you're not familiar with this story, a very, very quick rundown of how this works is that we can view the eigenvalues of these matrices as the locations of n D0 branes. Now, these matrices don't commute because there might be strings that are attached to the D0 branes and stretch in between them. And these D0 branes and these strings can then coalesce into higher dimensional membranes, a la the Myers blow-up. So it's worth pointing out that also these models are not necessarily quantum gravity and not necessarily holographic, yet they're interesting in their own right. Often they are tractable, and also they'll display key features that I want to explore here. So I'm going to try to talk very generally and establish some principles in which we can find this minimal area formula, but it's also useful to have a grounding example in mind. And one such easy example is what's called the fuzzy sphere state. So we might have 3 different matrices and a potential for these matrices that is minimized when they satisfy an SU2 commutation relation. And so this fuzzy sphere state is one that's sharply peaked on a classical configuration of the matrices, such that they span an n-dimensional irreducible representation of SU2. And as this irrep of SU2, that means if I sum the squares of these matrices up, I get the Casimir, and this is just some fixed number. And so this is the radius of the sphere. But these matrices also don't commute, so it is a non-commutative sphere, and it has a radius that scales like n, which we will take to be very large. Also central to the story is a gauge redundancy, which I'm going to try to explain plays the role of diffeomorphism invariance that we were talking about in the Ryu-Takayama context. So in particular, it has a UN gauge redundancy, which acts on the matrices by conjugation. And at large n, this is going to act on the membrane theory as volume-preserving diffeomorphisms. So one way to think about this is that there exists a Moyal map that maps matrix functions to non-commutative functions on the membrane. And underneath this map, the trace over those matrix functions corresponds to an integral over the non-commutative functions. And since this conjugation by UN preserves this trace, that means whatever is acting on the membrane theory is going to preserve this integral for any polynomial function, and so it has to preserve the volume form itself. And so these are volume-preserving diffeomorphisms. And so another way of thinking of what this talk is about defining volume-preserving diffeomorphism invariant entanglement entropies for D-branes. Okay. So let's give a summary of the result, and then I will try to explain how we arrive at the features of this result. So the result is going to be a minimal area formula. So we have an area here. And the minimization problem is over all possible subregions, subject to the condition that the volume of that subregion is fixed. And along the way, we're going to explain, or we're going to account for this area as a state counting. And the way this is going to rise is that this area will be a dimension of some edge modes under which gauge transformations will act at the edge of a system, a given system. We'll explain why there's an inverse coupling there. Of course, since these matrices are finite, the entropy is already going to be finite at large but finite n. So it's regulated by that. But then there's often a effective coupling describing the non-commutative field theory that describes the fluctuations around a fixed classical background. And in particular, for the fuzzy sphere state, the fluctuations are described by a non-commutative Maxwell theory, and we can replace n with this coupling G max. And then lastly, I'm going to describe the appearance of this minimization problem, which, as I said, there are volume-preserving diffeomorphisms that want to move around subregions, and this is going to arise as a saddle point in the average over those volume-preserving diffeomorphisms. Okay, so this is the results that I think I just would very much like for you to take away, but I'm going to now try to explain how we arrive at this result. So to do so, I want to first pick out what I mean by a subsystem. And I'm going to start with initial partition of my matrix elements into an m by m block. So here I have the top left block of this matrix, or of all the matrices. And for instance, in the fuzzy sphere example, we could think about doing this in a basis where X3 is diagonal and ordered. And so what this does is it picks out the top m latitudes of this fuzzy sphere. And so this is actually a fuzzy cap sitting on top of the fuzzy sphere. That's our initial subregion. And to compute this entanglement entropy, we're going to want to embed this into some factorizable Hilbert space, which is usually called an extended Hilbert space. And here it's going to be just spanned by all possible matrix elements. And it's obvious that this is going to factorize into this block and all the other blocks. And therefore, we can just declare this to be the in region and everything else in pink to be the out region. But as is often common and a feature or maybe a bug, I don't know, of these extended Hilbert spaces, is it's not gauge invariant, right? And the gauge symmetries act on these states, and so we have to isolate the physical states here. And here in particular, it's not invariant underneath UN. And the UN acts on states in this extended Hilbert space in sort of two distinct ways. Firstly, there's the subgroup UM cross UN minus M, which only moves things within a given matrix block. And we can think in terms of volume preserving diffeomorphisms. These are diffeomorphisms that move within a given subregion or the complement, but don't actually change the boundary of the subregion itself. And then there's also the gauge transformations in the quotient, which I'll denote as F, which actually move elements from one block to another. And in terms of our fuzzy sphere, this will be something that, say, wiggles the edge of the subregion, or even may pick out pockets of the subregion and move it to the complement, which I haven't drawn here, and so drastically change the subsystem itself. So we're going to then try to define an entanglement entropy that is invariant underneath this. So I just explained that a partition of matrix entries corresponds to a subregion on the emergent geometry. And this UN that moves the matrix blocks around are like VPDs that mix around the subregions. And so this leads us to the gauge invariant question. What is the entropy of any M by M block on the matrix theory, or on the membrane theory, what is the entropy of any region of fixed volume? Okay, so that is the question we're going to try to answer here. And to do so, we're first going to start with a gauge fixed state in this extended Hilbert space, and then make it gauge invariant. And we make it gauge invariant by just averaging over the orbit of gauge transformations, right? So we just act on it with some element of UN, then we integrate over all UN. And it's going to be useful to sort of glom the UM cross UN minus M into the state itself and pull out the integral over V. And so in particular, this psi V that I've written here is invariant under a UM action, and it's a particular UM action that acts on an M by M block, the M by M block in the basis that has been transformed by V. Okay, so that's why it's labeled by this V here. And this UM action is actually very familiar to us from the story of entanglement and lattice gauge theories. In particular, it is going to maximally entangle things at the edge of our system. In the matrix theory, these will be guys that live at the corners of these matrix blocks. It will maximally entangle the degrees of freedom at the edge with the things at the edge in a complement, and to irreps of UM. But it's the guys that live in F that have no analog in local gauge theory. And this is because, as I said before, they actually change the subregion that we are now tracing out. So these are going to be the guys that'll be more difficult to deal with. But first, let's look at the consequences of this UM invariant and argue that it leads to area laws in the entanglement. So as I said, this is a bit more familiar to us from lattice gauge theory, and there we know that the UM invariance leads to reduced density matrices for physical states that break up into representations of UM, and moreover, these are singlets on these representations of UN. So that means that they're maximally entangled edge modes. And so here, there's some probabilities, and these guys are maximally entangled, and D is the dimension of that representation. And what is interesting about states in matrix quantum mechanics that are strongly peaked on classical geometries is that actually if you compute the quantum Casimir, the quantum variance of the UM Casimir in these states, you'll find that there's a dominating irrep. That is an irrep with a probability that's very, very close to 1 and an exponentially large dimension. And so we'd like to know what the dimension of this irrep is. So we can read that off by, say, computing the expectation value of the Casimir itself. And the features that we need to take note of in this Casimir come from the Young diagram of the corresponding representation, which has some rows and has some lengths to each row. And the other very interesting feature of these states in matrix quantum mechanics that are peaked around classical geometries, that in fact, under the Moyal map, each row corresponds to different connected component of the entangling region. And moreover, each row length is then proportional to the area of that entangling region. And if this intrigues you, I recommend reading this paper by Alex Frankel, who explained this, I think, fairly clearly. But as a result of this, when we compute the log dimension of the dominating representation, we're going to see that it breaks up into sum over row lengths times the log correction, which then underneath the Moyal map means that we get a sum over area laws for each connected component of the entangling surface times a log correction. Okay, so we're going to take this and we're going to stick it into our pocket. And then we are going to now move along and say, how do we now calculate the entanglement entropy of any m by m block? So we're going to now incorporate this quotient f. So I'm going to make an assumption, it's a pretty key assumption, that reduced states of different subregions are distinguishable, at least to leading order in N. And this means that the reduced density matrix, the full reduced density matrix breaks up into a block integral over all the V's of reduced density matrix for each V. Now, this is a genuine assumption that I'm going to make, but it's an assumption that you can say, corroborate in your model of interest. So for instance, you can corroborate it in this fuzzy sphere model by looking at Haar random sampling over these V's and commit yourself that this is true. But this assumption is going to lead to a replica symmetry. So when I take trace rho to the n, I get a single integral over this now quotient, and I have this dominating representation to the 1 minus n power. And this integral has an interesting structure. So it's sharply peaked at a saddle point, and then has this very small one loop width. I've exaggerated actually the width in this plot, and then also has some typical values that it oscillates about very erratically away from the saddle point. And these oscillations are actually very well approximated by looking at Haar average integrals. And so by using these Haar average integrals, we can actually estimate each one of these terms. And by doing these estimations, we can then establish that there's a dominance of the saddle point. And so we have this trace rho to the n as this integral, and the dominance of the saddle point means we can approximate it by the minimizer of this. So the minimum over all V, the log of the dominating representation at that V. And this is what gives us our entanglement entropy. We have it as a minimal, as a dominating log dimension of a dominating representation over all V. And given the interpretation of V as being VPDs that move subregions around, but they preserve volume. This is a minimum over all possible subregions with a volume fixed, and then the answer is given by the area of that minimizing subregion. And I went ahead and replaced factors of n with this Maxwell coupling, and there's also a log correction. So the physical picture that we can have in mind is that we started with a state that really looked like it could have been just a decoherent sum over all possible subregions with a fixed volume, but somehow at large n, it really wants to glom on to a very particular subregion, namely the one that has a minimal area, which is this cap with some one loop wiggles. Okay, so a brief recap. I've told you a story of how geometry emerges from entanglement and matrix quantum mechanics. What fuels this is this notion of gauge invariant entanglement, and the interpretation is volume preserving diffeomorphisms. And then we saw that when this gauge orbit emits a saddle point, this is what leads to minimal area formula. So lots of natural outlooks. One would be to revisit this assumption of replica symmetry, which is of course enough to get the entanglement entropy when we're very close to 1. But replica symmetry breaking effects, just like in ADS-C, CFT, are important for Renyi entropies. Essentially, what we've done is we've pretended that the bulk could be filled in with a conical defect instead of looking at back reactions. So it'd be nice to revisit this. And be also, of course, very interesting to incorporate Lorentz symmetry and supersymmetry, obviously with an eye for the matrix quantum mechanics that are relevant for flat space supergravity, such as BFSS and BMN. Of course, there's also more matrices there, so that's a technical hurdle that we'll also have to get over. And lastly, and more speculatively, but it's always fun to speculate, is towards Ryuta-Kayanagi outside of the normal domains of holography. So I've presented a story where we gauge fixed this RT surface, not to some fixed feature or some fixed boundary, but to a more abstract notion of the entanglement question itself, which is namely, what is the volume of a subregion? And this is the thing that anchored our RT surface. So this opens up possibly new technologies for discussing more general notions of RT, and gauge invariant entanglements in quantum gravity. And I imagine there's some sort of sympathy here with maybe some of the technology that's been developed in the quantum reference frame community as well. So it'll be interesting to explore that. With that, of course, thank you for your attention.
Thank you. Questions? Comments?
Thank you for the talk. How should I understand you make correspondence between the fixing volume diffeomorphism with the gauge transformation? That's because gauge transformation mess up everything seems badly, but diffeomorphism is very smooth.
No. You're making a good point. It's something that I've a little bit swept underneath the rug. Of course, UN, even at n goes to infinity, is actually much more violent than volume preserving diffeomorphism. In fact, it eschews the whole diffeo or even connectedness of it, right? There's obviously UN transformations that take a single matrix element and moves it, which is in the geometric side, like taking a unit of Planck area and then moving that. And so, yes, there are many more of these guys in this map. And in fact, this tends to proliferate this integral. So there is actually a notion of coarse graining the diffeomorphisms that we are actually using here, which is a bit technical, but is, in essence, we're looking at the orbit over things that act geometrically on our subregion. So we're actually trying to pick out the actual volume preserving diffeomorphisms on the matrix side.
Considering a subset of the gauge.
Yes, that's right.
Okay, thank you.
More questions? If there's not, let's thank Jackson again.
Yeah, please.
20 minutes. I think it's the last talk. Okay, and our final speaker for today, Bo Sundborg from Stockholm University, who'll talk about black holes in higher spin ADS-50.
Okay, now you can hear me? Yeah. First, I'd like to thank the organizers for this great meeting and for my chance to present this work here. Black holes in higher spin ADS for CFT3. The reason I wanted to talk about this now is that it's a problem. So I'm going to try to address that problem. And you'll see, I'll show you what it is. But there's also an opportunity in that duals of this strange gravity theory, higher spin theory, are very simple conformal field theories, which may give us the opportunity to look at black holes and understand them in a simple model, not only extremal black holes, but sort of general neutral black holes and perhaps their microstates. So that's the idea. Let's see if I can move this forward. Yeah, you may have heard lots of misgivings about high spin theory, Vasiljev high spin theory, whether it makes sense or so in the bulk. My attitude is that since there are partial results, at least, on holographic duality, we can use those to define sensible bulk quantities, even if we don't really know how to handle the bulk
formulation. I certainly don't. There are high spin experts that know much more, but I find it very difficult. But I'm not going to use it directly. Right? I don't think it's necessary for everything, at least. All right. So since this is an ancient subject, I thought I would have to review a little bit of the background. For me, this history starts with symmetry, high energy symmetries of string theory, actually. As Lawrence mentioned yesterday, that high energy scattering was studied by Gross and Mende a long time ago. And after that, Gross extracted some ideas about short distance symmetries. Now, a much more simpler way to approach it became available with the idea that you could have strings in ADS where you have an intrinsic length scale. Then it makes sense to take the tensionless limit, comparing the string length to the ADS scale. And then if you do that in holography, oops, that was this, is this? Yeah, it's a very weak one, but here. If you do that in holography, you will have a theory of free fields in the boundary. And free fields in the boundary means that there are higher spin conserved currents like this. Conserved just because of the free equations of motion. Those higher spin currents in the boundary correspond to massless higher spin fields in the bulk, which then would be a sort of higher spin sub-theory in tensionless string theory. So that's the context where it started for me. Now, the actual higher spin theory was formulated long before that, in the late 80s, and only includes one higher spin, a single spin 2, a single spin 3, etc. So it's a very, very simple spectrum compared to the spectrum of full string theory. And to find the conformal field theory corresponding to that is actually much simpler than a matrix theory, which is what Young-Mills theory is. In essence, it's an ON or UN vector model. Very simple. And that is sort of part of the hope of this model. You can make use of that simplicity. Now, 3-point interactions were also matched eventually a bit later than the conjecture of the duality. And they were matched between the Owen model in the boundary and the bulk high spin theory. All right. It's just symmetrization. And there are you can determine the coefficients so that these things are actually, traceless and conserved, etc. It's just the formal expression. All right. Now, to discuss black holes, in holography, it is customary to Yeah, because the history is that Witten proposed this duality between ADS black holes and the deconfinement transition. And we'll see where it sort of comes from thermodynamics. The transition was known already in ADS by Hawking and Page. And what connects this thermodynamic story to the higher spin or models or tensionless string theory was that it's kind of easy. This is the kind of expressions you get to find the deconfinement transition in free matrix, free models on the sphere. And these are the kinds of expressions that are involved. I will not go into details of these expressions today, it's late. But the same kind of technology was then used by Schenker and Yin in a beautiful and very annoying paper. Now, note that in this case, the phase transition for vector models is not constant. It scales as a square root of n, which is sort of the cause of all of the trouble. Right. So what can we do? Well, we can quite easily find the high temperature regime on the sphere. It's simply a black body gas, a free gas on the sphere. At very high temperatures, it's the same. It's the same as in flat space, and famously, importantly, in everything, it matches the behavior of the asymptotic high temperature behavior of black holes in ADS, Schwarzschild ADS black holes. They have automatically this holographic form. So you could think of ADS black holes as sort of the precursors of holography. Yeah, and there is this slight difference here in the n dependence, which indicates, suggests that what you should compare the Newton's constant with in the dual dictionary. Right. Okay. Now, what's annoying about the Schenker and Yin paper? The paper is technically beautiful, but what is annoying is that it's more or less the results. I don't like them. They can still be true, of course, even if I don't like them. But I think there's what they essentially say, there's a lot of text here. What they essentially say is that higher spin duality does not really work as we expect duality to work, which could be a problem with the actual theory, or could be a problem with holography. Or it could be perhaps a problem of the interpretation. I will try to take that latter perspective, but it's not easy. So let's try to squeeze things into an interpretational problem. All right, and then you get maybe different results. But I admit it will not be totally convincing. However, there are still lots of things to say about this system, which I think will be important, whatever the eventual conclusion is about the interpretation. All right, so another important but not very well advertised result of Schenker's engines is that they find and they discuss composite operators, invariance operators that are very, very massive. The dimension will be of this scale. And the reason that they are massive is that you need to contract the fields, which are n vectors, n component vectors, with the Levi-Civita symbol. So you need n of them. And this antisymmetrics, you need to have a number of derivatives on the fields in order to get something non-zero. Schenker engine also very nicely gave the partition function for these interesting, very heavy, and very many states. But then they didn't do so much more with them. I'm going to repair that now and tell you more about them. All right, so we'll come back to this. And then I will explain to you why I'm so annoyed by the results of Schenker engine. Because the results notwithstanding, we tried to extract physics, or maybe to sort of probe the results, try to extract physics out of these systems. Free field theory in the Owen model, free fields in the boundary, which would correspond to high spin symmetric gravity in the bulk. How do you probe it? Well, you just calculate correlators and investigate their properties, try to interpret them in terms of gravity. And so this is in spirit similar to what Romuald was talking about. And there are a number of observations that we made, and they all seem to be fairly consistent with the idea that this is actually something very much like black holes in the bulk. So we have two statements. The high temperature phase of higher spin theory is different from that of string theory or gravity. And the high temperature phase of higher spin theory is similar to that of string theory and gravity. Oops, time passes. Okay, there's time dilation. So takeaways here. I was expecting this. All right, so first, there are these interesting states, numerous and super heavy, and they signal the confinement transition. There is, and that I will not have any time to say anything about, possibly a new interpretation of the units to use, how you should look at the ADS scale. All right, the thermodynamics of these states. Quickly, here they are. Because of this antisymmetrization, you effectively have a gas of n free fermions, in quotes, which means that these are actually like white dwarfs or these states they are fermion gases. They are like white dwarfs or neutron stars, only that the fields, the particles, are massless particles on the sphere, on the two-sphere. So it's like a hologram. It is like a surface of one of these objects. Anyways, the ground state is very, very heavy, growing rapidly with n. And in this case, I've drawn here, it happens to be scalar, but in general, depending on n, whether it's a square or not, they are very highly degenerate and have extreme degeneracy. So they are like thermodynamic objects suitable for that. They are also kind of intriguing from the perspective of bulk higher spin theory, because you can calculate 3-point functions, and in general they are non-zero with the higher spin currents, means that they couple to massless higher spin fields in the bulk. And this is just like the boundary corresponding duals to Didenko-Vasiljev higher spin black holes, how they should behave. So this you can probably match to that in some way. All right, you can do standard thermodynamics. It's nice when you have fermions to use the grand canonical ensemble. And here it is, quite unremarkable. Entropy, internal energy, and free energy. There's something interesting here in the free energy, which is what? It has a zero at a certain temperature, which is very, very close to the critical temperature of the full gas. This is just, remember, this is just one state. It's just of a very complicated object, like a star or a black hole or something in the higher spin theory. That the free energy vanishes is analogous to what happens in the Hawking-Page transition at the transition temperature, when free energy of the bigger black holes vanishes, and in principle can dominate thermal ensemble. This could happen here as well, obviously, depending on the processes. So the picture is that this is actually like the Hawking-Page transition, but this temperature is slightly below the deconfinement transition. So that's why I would call these vector baryons like condensation nuclei for black hole formation. Eventually, as you increase temperature, first these objects are favored thermodynamically, and just after the slightly higher temperature, you reach the deconfinement transition, and black holes or something like that would be able to condense. Well, this is the story of finding units. I have 1 minute. All right, I can tell you one more thing then. All right, so the idea is you can, assuming that the largest black holes are ADS Schwarzschild, like at leading energy, next to leading energy when you increase temperature. And also that the largest high spin black holes are yeah, no, this one. also that the largest high-spin blacks are dual to the high-temperature equilibrium of vector models. A simple, very natural assumption if it weren't for Schenker and Jin. Well, if you then calculate the leading order mass and the next to leading order mass when at high temperature, you can see that they depend on Newton's constant and the ADS scale. So in principle, you can use these values to observe, compute Newton's constant and the ADS scale. So let's calculate them in the boundary and then compute G and L. Okay. That's a non-trivial calculation involving all of these integrals over eigenvalues that I showed you in the beginning, but it gives you something. And what it gives matches perfectly what I wanted. I didn't know this, but it matches what I wanted, namely that the critical temperature is actually at the ADS scale. If you observe the ADS scale and Newton's constant by this way of looking at the sort of semi-classical limit of black holes, assuming that they are black holes. Unfortunately, perhaps, it gives a very strange result for Newton's constant. So this is why I'm not quite happy with this yet, even if on all other accounts it satisfies my wishes. All right, I think I must have covered everything and got a bit over time, so thank you for your attention.
Thank you. Questions?
A possibly naive question, but you said that the ground state scaling dimension scales with n like n to the 3 halves for this heavy baryons. But from a very naive analysis, I would have thought they would have gone like n square because the number of derivatives on let's say this scalar quarks can never be equal. So they would be at least like 1 plus 2 plus because of the derivatives. It should go like n square.
No, I mean that's the first estimate you would do. I agree completely. The reason that you can go a bit lower is that you have several directions to so you don't necessarily have. You can have momenta in all the directions, so you fill the levels more slowly.
I see. Thank you very much.
More questions? Is there a similar story for ADS5?
Is there a similar? Yeah. I realized that the other day. Just so I had to quickly sort of do the same computation for the sort of tensionless limit, which would correspond to this story for matrices, which is the appropriate for ADS5. Then you have the Young-Mills. I could only do the scalar toy model of this, and I couldn't completely do it, but because the contributions from to the corrections next to leading order in temperature are quite complicated, actually. So, but it looks like the result there is the expected one, that the ADS scale does not change with n. And the coupling is 1 over n squared. Newton's constant is 1 over n squared, as you'd expect in a matrix model. So, I mean, a sort of a test of this crazy way of measuring the cosmological constant. It seems to work.
Okay, if there's no further question, let's thank Bo again. And close the afternoon session.
Ja, maar ik probeer toch wel op tijd te beginnen. Please do.
That would be great.
Jij krijgt een wire op en dan kun je staan waar je wil. Dus ik vind het heel leuk dat het zo...
leesgestoelte, als je, wat zeg je? Er is ook eventueel zo'n leesgestoelte of zo'n pedestal. Ja, dan rijden we dat.
Jij weet waar die staat? Oké, nou, maar dat is dan... Oké.
Papier opleggen.
En waar wil je die dan graag hebben? Ja, laten we die hier centraal doen. Ja, oké. Ja, oké. It's 30 right there. Okay. It's always good to be punctual. It's 17:30. Great to see so many faces. Welcome to the outreach event of Eurostrings 2025 and the yearly meeting of the cost action. I will make it very short, but I just want to tell you what to expect. We start with 3 presentations of differing length. It will be, you'll notice how long they are, but they will be all really interesting. We start with the presentation on the topic, well, the general topic of this meeting here is the role of science in times of geopolitical uncertainty. That's a mouthful, but yeah, so I think it has not been tried before as an outreach event, and we're really looking forward to see what kind of feedback this gets. But so we start with some words on this topic by the director of Nordita, Mikael Vogelström. Then very honored to have the director of Cost, big action that makes this in part all possible, together with Nordita and many other funders. Ronald de Bruin, who flew in especially for this event. And then Robert Dijkgraaf, I kind of dare to say our own Robert Dijkgraaf, will give a presentation. We all know Robert. In fact, I thought it was very interesting that during the first talk yesterday, the Dijkgraaf, of course, now I'm saying because there's so many things after, but I highlight one, the Dijkgraaf-Witten model was invoked. And like that, I could go on, but I will not. But I will say that Robert has a big track record in fundamental science and science policy, having been director of the IAS, having been president of the Royal Society for Arts and Sciences in Holland, having been the Minister for Science, Education and Culture in Holland from 2022 to 2024, and recently being president-elect of ISC. And also, and I find that particularly very fitting with the topic of today, since the 1st of April, university professor at the University of Amsterdam in a special chair of science and society and their relation to international affairs. This is very fitting. Simultaneously, Robert is also a professor of mathematical physics. But after this introduction, I'll give the word to Mikael Vogelström, director of Nordita. And then I can also meanwhile say that after these presentations, as you can maybe already guess, with the 3 chairs there will be what's meant to be a lively panel debate. So when questions come up during these presentations, please remember them or write them down, and you'll get the chance to ask them and see reactions of the panel. Please.
Thank you, Niels. So I'm very happy to to welcome you all to Stockholm and Nordita Albanova University Center for this outreach event. And it's part of an ongoing, rather large, reoccurring series of conferences called Eurostrings. Given the topic of this evening event, I think Nordita, with its history, is actually a very suitable host and a suitable venue to host this talks and the discussion to come. I'll try to motivate this, and it's sort of a historical looking back, and Nordita's first director was actually Niels Bohr. And I imagine with his personality, I never met him, I'm too young for that, but you read about and you get the feeling of a quite big personality with very nice personal traits. And I think Nordita has carried on, or is built very much on the spirit. And his deeds, in a sense, I feel very important. We all know that he was sort of the father. There are many fathers, of course, but to modern physics, and particularly bringing a lot of bright young scientists to Copenhagen to forge and discuss new quantum mechanics and lay the foundations of what to come. Interacting, of course, with the bright minds of the time. And this was an activity, so if you go to the lecture halls in Copenhagen, you see all these nice photographs, and it's basically every big name of the time were there and they were interacting. And it must have been a very fruitful environment because many of the attendees actually had to go to Stockholm in December. So I think this is a very important part in scientific collaboration to be able to explore and build new things. And of course, a conference like this is an essential part of that. Nordita itself is sort of a post-World War II child. And of course, we know pre-World War II, there was a large brain drain for the wrong reasons from Europe. And building an institute like Nordita is, of course, to get a brain gain and stop and reverse the flow. And it was also very important at that time to secure knowledge and expertise in the new field of atomic physics. And Nordita is actually an abbreviation, so it's the Nordic Institute for Theoretical Atomic Physics. But it's turned very quickly over to theoretical physics. And the hearsay is that they even made a bid to be the CERN part of theory department at the point, but they failed. It was put in Switzerland on the border to France. That's fine. And of course, together with politicians, Niels Bohr was a champion for this because he was very much for open science and not keeping secrets because secrets become dangerous in this field. And that was very typical for the weapons that came out of atomic physics. And there are also peaceful means. And in Sweden, there was a very big drive for nuclear power at that time, which was in its early stages. But that initiated, and there's a good track record. So we brag always with Nordita actually placing like, I think it's 132, but I guess the numbers should be changed, professors in the Nordic countries. So it has been really working well when it's been attracting with the brain gain, I would say, and also with education and population of science in our community. After that, when Nordita moved on, it also took another role, and sort of the topic of today is when we are in troubled times and how should we act. And in half a century ago, we had the Cold War and we had an Iron Curtain, and there were very little exchange between scientists. But a place like Nordita in a small country, Denmark was part of NATO, but considered more or less neutral. This is a place where scientists from the East and the West Bloc could meet and exchange ideas and understand what was going on in either places. And for peace and development of everything, this is crucial. Here, science is so important that that we have a good understanding of what is going on in our different countries, in our different labs. And it also a joint development. It's quite interesting if you're a little bit into history of science. There are many parallel developments that went on in these locked countries. And there are many famous mesoscopic physicists who in Europe discovered things, and they found out that that was published a long time ago in somewhere in Russia at that time. So that is how it was. But when you meet, then you can start exploring and building knowledge together. And I think that's extremely important, perhaps not for countries, but for mankind. Well, the Cold War ended, the Iron Curtain fell, and we went into a long spell of disarmament and so peace. And we have actually been in that phase for such a long time that we think that is normal. But if you think about history, that is actually not normal. It's actually an anomaly that you can spend such long time in peace. Given Europe, we are good at many things, but we have been very good at fighting each other. But now we have had a long time of peace. And this means also that we sort of forget sometimes what is important, because we get it for free. And now I would say there are multifaceted dark clouds on the international arena. And I think we'll get some input on that in the talks to come. And I think it's important to look back and perhaps reinvent and get inspired to work together again, and within this kind of institutes like Nordita's, and there are others in the world. With this, I would like to welcome you to this open event of Eurostrings from the behalf of Nordita. Thank you.
Not. Then it's my great pleasure to give the floor to Ronald de Bruin, Director of Cost.
Thank you so much. Good evening. Good evening. Oh, it's not bedtime yet. It's a pleasure to be here. What I would like to offer you as a contribution to the debate is some practical examples on how politics, or geopolitics, if you like, influences, let's say, a funding agency like Cost. And before doing that, of course, I have to explain a little bit about Cost, what Cost is. Is there anyone here who has ever participated in a Cost program, Cost networks? That feels very good. That feels very good. Okay. Now, for those of you who are not so much aware about Cost, it was more or less incubated when I was incubated as a human being. I'm of a cohort 1969. Cost was given birth at the occasion of 1971. And the purpose has always remained the same. The idea is to create networks, bottom-up, excellence-driven, inclusive, in order to tackle European-wide challenges. That basically has been the mission since the very beginning. Now, over time, we have found ourselves in a position to also give more support, more empowerment, not just funding, support, and even training to build capacity across, let's say, the networks that we have. Now, we do this, let's say, on a European scale or a pan-European scale. We have excellence, of course, as one of our key values. We promote very much interdisciplinarity. When disciplines come together, you get breakthroughs. The idea is that, of course, breakthroughs will lead ultimately to innovation. Just before the lecture here, we had, I think, a good discussion about the challenges to shift from research to actual innovation and impact. And last but not least, the empowerment of young researchers and to retain young researchers in Europe. So those are our, let's say, more recent strategic goals. European map of cost. And here you see a color-coded map. These are all the members. We have 41. We also have South Africa as a partner member. They are not part of our, let's say, normal constituency, but they put some money aside to also facilitate their researchers to join the cost networks. We have Israel as a cooperating member. No voting rights, but in the end, all the benefits of the cost program are equally applicable. Now, I say color-coded map because we have a specific policy to promote inclusiveness, and that means that we want to include also less research-intensive countries. So those are colored in green, whereas the other ones are colored in purple. Looking at the bigger map, and I think this is as big as the map can be, at least on this planet, we see the membership of cost in purple, and then a green, let's say, ring around cost. We call them the near neighbor countries. I will give you a specific case on what happened as a consequence of the geopolitical shifts. And then we have the rest of the world in quotation mark in orange. It basically means that if you are a participant from an institute in, let's say, a European country or in one of those green countries, you can participate and receive funding. You get your travel, and overnight stays and so forth reimbursed. The rest of the world can also participate, but they have to bear their own expenditure. So cost is truly open to the world. And I would have to immediately add that part of the mission of cost is also to focus on peaceful purposes only. Now, that said, as a, let's say, an intro, to make it concrete, how does it work? Of course, it works with an excellent idea from a researcher, in this case, a Portuguese one, that rallies around the flag and make sure that there are some mates to act as a secondary proposer to join in submitting a proposal to our open call. So far, so good. This is what normally happens. The distinction with cost is that this is not necessarily the group that is going to do it. The group is going to be larger. And so we say that if you submit an excellent proposal, we help you to build a network around it. We have national contact points in all the countries that are member of COST. And so we are asking those people to nominate researchers from their communities to join the COST action where they've never been in the proposal in the first place, but they can get funded. So that's how you start building a network, let's say, by creating the right framework conditions for bottom-up, let's say, initiatives to prosper. So this is how it works. Just a few numbers. We have around 300 of those networks. In total, we have around 60,000 active participants in those networks. What they typically do, apart from organizing conferences, is short-term mobility. So this is at the individual participant level, but they also organize training schools, for example. An estimated budget, it's an annual budget of roughly 170,000. And then you say, hey, if you do the mathematics, 60,000 divided by 300, roughly 200 per network on average. So there's not a lot of money. And that is exactly because we do not fund research. We fund the networking. So we fund the travels, the training schools and so forth. We assume that the participants are involved in their own projects, whether at national level or European level, and then come together, exchange in a peer network, and then move on from there. Our own total budget for the last 5 years has been roughly 270 million, and we get a bit of money for the remainder of this framework program from the European Commission. So that's very practical. Now, what I sometimes do is to give a talk about cost and the benefits and go into much more detail than I've just done a moment ago. This is an example of a conference that was organized in Cairo in February this year. And we used that occasion to, at the same time, invite people from countries that are in the Northern African green zone, so to speak, of course. So they are our near neighbor countries. And on the top, you see a picture of this meeting, with people from Egypt, Azerbaijan, Jordan, Morocco, Libya even, Palestine, and who else is that? That must be Algeria. Yes, Algeria was there. And an attaché from the European Commission who was stationed in Addis Ababa. And there you can truly see that there is more than just going to training schools. There are people in those parts of the world that do have talent, but have no clue how to get into a European program. And because they do not even have to submit a proposal to join, for them this is the first step, the way in. To join a peer network and to submit proposals maybe with some people they meet, or to publish with people that they meet, and so forth. They are able to, let's say, join the European collaborative research, let's say, game. And that opens up a world for them. This is the only window that they currently have. So there's more to, let's say, science than just, you know, organizing network meetings. Also at that level, the governments are really trying to make their pitch for being associated with the European Framework Program, for example, and Egypt recently joined. Obviously, this was Cairo. Ramses II, I also weaved in, but I'm going to move on. So, just one example of how politics can affect the cost program. You may remember 2016. At the other side of the channel, there was a referendum. Shall we join or not? And guess what? In the morning, we could read in the paper that the coin flipped in an unexpected way. And ultimately, about a year later, there was an official notification that the UK would withdraw, indeed, from the EU, with the prospect to leave then in 2 years' time. So there was a kind of a transition period. However, I think there was not a lot of agreement in the UK back then, and the Parliament in 2017 was then, of course, renewed. There was a general election, and nobody knew exactly what the status would be. Because at that time, Theresa May was replaced by Boris Johnson, and what would Boris do? Would he go for a, let's say, hard or negotiated Brexit? And so there was another election to try to force the situation towards clarity. And so in December, we had in the UK again elections, and finally there was this agreement, a negotiated agreement, last moment, between the UK and the EU. So that was then leading to an exit officially on the 30th of January 2022. Now, why is this relevant to cost? The networks have grant holders, and we give them a grant on an annual basis. Upfront, we pay 80% of the grant. And if the UK would leave without any negotiated, let's say, agreement, but also the participants would no longer be eligible to receive funding. And this is what we typically have at hand in the period of September, October, which is September, October, just before the general elections on the 12th of December 2019. So in this case, and I dare to say I, but of course in close consultation with my governance, I had to make a decision. Because we have 21 grant holders in the UK that together, when they receive 80% pre-financing, can increase, let's say, the amount altogether to an extent that it becomes an existential threat to cost, because we didn't have the reserves to back it up. Try to get your money back. So based on this risk analysis, there was a decision not to conclude a new grant agreement again with the UK-based institute, but to ask the network to find an institute outside the UK to act as a grant holder. I can assure you it was not received very well, but that was basically the situation. So in this case, we were affected by, let's say, politics. We took a risk-based decision and we imposed that the grant holder function had to be removed. Just to give you an impression of what the impact was, here you see the percentage of main proposers. So when we collect all the proposals, the UK traditionally was in the top 3, but often number 1 in the proposers, let's say, group. And in 2016, you immediately see a drop. And it was, in that sense, a bit remarkable because in the end, there was a negotiated, let's say, agreement. So the participants were still eligible to receive funding. But in the meantime, the word was going out and the EU framework program participation was also put to a halt. So the whole notion was we cannot participate. So you see there's an immediate impact. Now, since 2020, we have, of course, clarified this. And that actually led to a situation where with a lot of promotion, targeted promotion in the UK, look, you can still participate in cost, led to a gradual uptake. So this is a direct, let's say, result of geopolitics. Now, completely different situation, of course. We are witnessing the atrocities on a daily basis. We can follow this very closely in the newspapers, on the media. So Russia invades Ukraine. So the first thing we did was to make sure that Ukraine becomes a member because they're part in the European sphere. And I ended up actually making a telephone call to the director of a national funding agency who was the intermediary between us and cost. And when calling her, I found her in a bunker sheltering from bombs. And she said, well, I'm so happy that you are calling, you know, because then we know that somebody outside of Ukraine is thinking about us. And so ultimately, we were able to reconnect and make, let's say, Ukraine a member. And of course, we waived the contribution fees. Now, the other side of the coin is that we received guidance from the European Commission, because we are paid 100% by the European Commission, to no longer allow funding of participants who are affiliated to institutes either in Russia or in Belarus, but not on basis of nationality. So if you're an Italian and are affiliated to, let's say, University of Moscow, you're out. But if you are a Russian affiliated to, let's say, the University of Trento, you're still eligible. I think that's an important nuance there. So that is what we did. So institutions in Russia can no longer receive funding, but researchers are not discriminated on the basis of their nationality. Now, what is the impact? The blue line represents Ukraine in terms of participation. So in how many actions of the 300 are you involved? We see Ukraine going up. And of course, we see Russia and Belarus going down. So this is an immediate impact of geopolitics on cost. Another one, and it's the last one that I will go into together with you. The EU sanctions against Hungary. Why were sanctions imposed on the first place? Because there was an act adopted that would give, without going into a lot of detail, a lot of interfering power in the governance of a number of institutes in Hungary, threatening the independence of these institutes. And that is not, quite frankly, in line with European values and also European, let's say, rule of law. And so the EU decides to implement sanctions in 2022. The Council with all the member states come together. And sometime later, we got specific guidance from the European Commission, said, look, you know, until further notice, individuals from these universities, and there's a list, are no longer able to receive funding. By the way, these institutes themselves cannot also act as a grant holder. but they are allowed to participate. And then later the Hungarian government basically responded to this by putting aside a national fund. They call this the guarantee fund. So they pay the participants directly. So here you see a different type of modality that is a result of, let's say, politics that we are exposed to. Now, long story short, what do we see? In green, the number of leadership positions, like a chair or a working group leader, they go down slightly, but the participation overall, the purple line, is still increasing. And that is due to the fact that, yes, you can still participate, but the government of Hungary will pay you and not us. So, in short, indeed, cost is bottom-up, inclusive, excellence-driven. We also, I would say, act as a science diplomat wherever we can. Because if, and we will talk about that later, I'm sure, if everything's break down, scientists still want to talk to one another. That is, let's say, the experience that we have. We are not a political body, obviously, but we are subject to policy making. And we are not, let's say, a private entity. We are not, let's say, a Wallenberg Foundation. We are paid with public money. And because we are paid with public money, there are some policy, let's say, aspects that are to be observed. So I'd like to keep it here, to keep it practical, and to offer this as a contribution for this evening. Thank you.
Thanks a lot. Thanks a lot, Ronald, for this inspiring talk that I'm sure we'll get back to. So then the third speaker, we're rolling the lectern. Professor Robert Dijkgraaf, University Professor and President-elect of ISC, who is going to talk about science at the crossroads, promises and perils.
Great, thank you. So it's wonderful to be here, and actually for perhaps one of the first times in my life, not giving a presentation while speaking. So I hope I will actually hope you can imagine the images that I want to project. To start with one image. So I joined the Dutch government 3.5 years ago. And there was a cartoon in the newspaper, and you saw me descending from a small ivory tower on a planet called Princeton into a big black hole called politics. So I'm very happy I'm outside the black hole again and share some of my experiences. And for those who understand it, you know, science and politics are a little bit complementary fields, and but they are very much interacting. So I hope you enjoyed some of the lessons that I want to share with you. And I think it's good to have this opportunity to discuss basically what the state of science is, how world politics and national politics is impacting our lives, and perhaps also in the discussion what we can do. Now, what is the state of science? So there is this anecdote that Leonid Brezhnev, was then the leader of the Soviet Union, was asked to assess in a single word what the state of the Soviet Union was. And his answer was good. And then the follow-up question, what would be his answer if you could use 2 words? And he said, not good. So I think that's my summary of science. So in one word, it's good. And I think it better be good, because I think there are unprecedented research opportunities. The way I like to frame it is that, you know, the big picture would be in the 20th century, we discovered the building blocks of matter, atoms, particles, of life, genes, DNA, of information, bits and algorithms. And now we are at the stage where we can actually, in principle, build anything we want out of those building blocks. So we are entering this area of artificial materials, of synthetic life, of rightly say, that a fraction of natural phenomena that have been discovered is like 0, because I have this image that science has been traveling on this nice river, and now we're in the open ocean, an open ocean of infinite possibilities, but also I would say crashing waves and geopolitical currents, and also the pace of discovery accelerating. I'm not sure whether we have to believe everything that people are selling us about AI, but there are serious predictions that the rate of scientific discovery might increase tenfold, which means that all of us can live to the end, I hope, of the 21st century, perhaps the next century, which is extremely exciting. And my own experience is that there's really no policy issue where science doesn't make an impact. In the Dutch government that I was part of, I had a minister of nitrogen, because it's a big issue in high intensity agriculture. We had I like to say, a minister of carbon, which was the minister for climate. So and I said, I was the minister of education, so I was the minister of oxygen. But just to have ministers with their own molecules, that shows that it really makes an impact. And on top of that, there's of course an unprecedented talent pool. I think no time ever in science so many, particularly young people, were about and ready to join this adventure. And modern communication techniques allow us to really build a community. And I think we have a much greater diversity from different perspectives. One thing I like to say is that what science should, one of the quality of science is that not fitting into the system should also fit into the system. We are very expansive in the sense that we allow many different perspectives. So I think we should be optimistic. I think science is one of the most reliable source of optimism. We can discover new things, etc. So our lives should be terrific. So that's the one-word summary. But the two-word summary, of course, it's not good. Because if you just see what's happening in the world, we see unprecedented attacks on science, on academic freedom, on key institutions. By the way, not only in the United States, we see them around the world, also here in Europe. We saw some examples of self-destructive behavior, and the very pillars of knowledge are being attacked. So if we discuss the shrinking academic freedom, it's good to keep in mind a distinction that was catched by the British philosopher Isaiah Berlin. He spoke about negative and positive freedom. So negative freedom is the freedom of threats, and positive freedom is the freedom to act. So what may you do and what can you do? And in terms of negative freedom, we see many scholars face growing physical and online attacks. Half of all the climate scientists, half of all the virologists claim that they have been feel pressure, they've been threatened. And of course, we just mentioned the war in Ukraine, where research laboratories and universities are explicitly targeted as very vulnerable parts. We see in countries like the US that sensitive research topics like climate and vaccine and diversity, both biodiversity and human diversity, gender and social inequalities are being banned. We see universities being portrayed by populists as disconnected elitist institution that face attacks because they are allegedly calling on excess political correctness. We see worrisome cases of self-censorship. If you all these pressures, you start to adapt to it, and cancel culture. And of course, we see these waves of alternative facts that, and fake science. There are a lot of sources of so-called science that really copy the peer review and the scientific journals that we are part of legitimate science. And on top of that, I think we see in many countries that science is increasingly seen through this kind of lens of economic benefit, which is really focusing on the short term instead of the long term. I wrote a short book with the title "The Usefulness of Useless Knowledge," and I think we, as basic scientists, know how important it is to set the human imagination free. On top of that, in terms of our worries, I would say that we see increasingly a lot of research drifting into from the public into the private sphere. If you see, by the way, also in spending patterns, if you take the top 5 US tech companies, they spent a total last year, 250 billion, which is twice the total public expenditure in Europe. You see infrastructure requirements, the next generation data centers at the order of 100 billion and asking, the power of a city of 1 million inhabitants. So, and on top of that, also we are here mostly among physicists, but humanities and social science are particularly under pressure. They're being marginalized, and of course, they are absolutely crucial in understanding how all this technology will be brought. And around the topics that we are discussing here, we increasingly see kind of a zero-sum worldview where international scientific collaboration faces serious pressures and it becomes a threat to national security, to economic interest, and makes it more difficult to work, particularly with researchers from third member countries. So that all makes it really, really difficult. And by the way, we might discuss this more, this issue of research security, to which extent can we be open in science? And I love this image that actually a very high-level member shared with me of the US Department of Defense, who said, we are very worried about knowledge leaking out. But it's like she had the image of a leaking bucket. But she said it's also very important how wide we open the faucet. How much are we able to attract talent? In fact, a veteran researcher recently told me that who worked through the worst time of the Cold War. He said, the current atmosphere and lack of collaboration is worse than in the 1950s and 1960s. There are not only, and I would say, and this in contrast to the pressing challenges that we have, whether it's the planetary health, whether it's climate change or technical governance, that really needs next level of global cooperation. And we see much less sharing of data, particularly in crucial areas like the poles and the oceans. It used to be that scholars are at risk, but I think these days also data are at risk. And I think it's really ironic that in certain circles, these kind of need for worldwide guidelines, so as, for instance, the UN Sustainability Development Goals, they generate fierce backlash. So there are groups, particularly in certain tech circles, that see this demand from scientific voices to take care together of our planet as a threat to unconstrained industrial and technological developments, and some kind of a call of world government, which is, I think, really interesting. That certainly science is seen as the enemy, so to say, ideologically, of economic growth, while of course, science is actually underpinning much of those technologies. So anyhow, this is the not good part of the story. So what are some of the underlying causes? Because I think we have to dig deeper. And ironically, I think a lot of backlash that I see against science is a result of the success of science, of the impact that science makes. It presents uncomfortable truths to whether it's the environment or public health or social inequalities. And it's science pushing society, and I think partly society is pushing back. So it's an application of Newton's third law. Action is reaction, which is a good thing. But I think there's a second thing that really worries me, is that we see in our societies increased polarization. The polarization often is along educational fault lines. So it's the university-educated people and those who are more practically educated. And we see that the traditional broad support for science as a public good that benefits everyone is under pressure. And there are some groups which actually look at in a very critical way at the scientific enterprise. And And so this is, I think, a challenge. And I think, it's an easy prediction that it will not go away automatically. Particularly, I think, this complicated interaction between science and politics. So there's a nice saying that if you mix science with politics, you get politics. But I think that's kind of too easy, because I think we all would like to see politics really supported by facts, by research. So we would like to scientifically, to scientize, so to say, politics. But of course, the reverse effect is that, scientists are being accused of being politicized. So how do you navigate these two different worlds? I said, when I jump into the black hole, we have some kind of case of black hole complementarity. If you think of what's the world of politics, it's largely it's short term. But just saying the average lifetime of a European science minister or any minister, I think, is 22 months. Shorter than a typical postdoc, I would say. It's emotional, it's ambiguous. As a politician, you never want to be very precise in what you say. It's national, it's zero-sum, because the total number of seats in parliaments is fixed. And interestingly, it's negative. Now, social scientists have found if politicians talk about a certain topic, people start to think more negative about it. That's why it's so productive to talk about topics like immigration, etc. It feeds it. The world of science, of course, is long-term. It's rational. We try to be as precise as possible. It's international. That's why we have this debate. We truly feel it's win-win. And as I said in the beginning, it's optimistic. So I think there's a real challenge how to navigate that interface with the given fact that the impact of science on society will only increase. That's unstoppable because we will learn more about the world and we'll address more issues. But I think there's something that has to be done. And I like to kind of misquote Steven Weinberg. Weinberg had this wonderful quote where he says, in science, we usually learn about nature, but sometimes in science, we learn about science. He used it actually in the context of the anthropic principle, But sometimes in science, you learn what the right questions are. And I think here there is a moment where we have to think about how science has to be oriented in this new world with all these pressures and things going on into society. And I truly feel that there has been kind of a social contract between science and society for, I would say, the past 8 years. After all the institutions, the research institutions, the research councils were funded after World War II. There was this very impactful report by the science advisor to President Roosevelt, Vannevar Bush, Science, the Endless Frontier. And it basically said, science has been so productive for us in winning the World War II. How can it be of impact in times of peace? And it gave us, all the institutions gave us the whole framework. And I think that social contract where citizens spend tax money and to science, and we researchers give them the benefits of our insights, whether it's new medicines, whether it's new technology, or a new understanding of the world and the universe. I think that contract has to be renewed. So the question is, what can we do? What should science do? And the good thing is, by the way, and we'll have a discussion, but and I always like to say this when I was a Minister of Science with any questions, that's a good question because scientists can, or scholars can investigate this. So there's a lot of knowledge about how we as a scientific community operate and how we deal with these interfaces. But we need our colleagues in the social science and humanities to inform us. They have studied us and they can give important information about how we communicate, how we engage, and how we can navigate that complicated landscape. And so I think there are many things we can do. The first, actually, I think, perhaps the most important one, and I was in another panel discussion, and one of my American colleagues was in the panel discussion, and he was very much involved in the past in the whole civil rights movement in the US. And he said, there's this wonderful saying of Martin Luther King, who said, we need to organize the forces for good as well as as the organizers for bad, are being organized. And so we should push back against the pushback. I think, we see these kind of attacks on science. It's very important that the scientific community organizes itself and actually, stand tall and pushes back. But I think there are also certain things that we can do in science itself. The first, I would say, is really work across the disciplines, because this is something that, is addressing the full wide spectrum of science. So, there's this kind of nice saying that, the world has problems, the university has departments. That's a little bit nasty remark to the university, but it's true. I think, if you see the big issues that we claim that we can solve and that we can address, we need the various disciplines to come together. I think, we have built this wonderful architecture of the research infrastructure, but there are a lot of interior walls that I think need not be there. And also, I think we have to work not only among the various scientific disciplines, but what's called transdisciplinary research. We should also involve people who in the end will be impacted by our research. Perhaps not so much in string theory, but in many other fields. I think it's very important to engage communities. And so open science sharing, as long as, if you can do it safely, the outcomes of research and data sets is incredibly important. It's important to build connections to our own communities in our countries, but actually also something that really worries me, which is the North-South divide that's coming up. So if you see actually, from a global perspective, those countries that have to make the most difficult decisions, which are often the poorest countries, they have the least access to scientific knowledge. So that's incredibly unfair. And I think, that's a good reason why we need global collaboration and help, those countries which do not have the wonderful research infrastructures that we, for instance, here can cherish in Europe. I think also, there are many reasons for us to have this kind of stronger engagement with society. It's self-serving in the sense we would like to be funded. But I think, we want to attract new talent. We also know it's a fertile ground for innovation, for new companies. But I think it's also very important that citizens are well informed, because they have to make difficult decisions. They do it at the ballot box, the way they think about crucial issues. And I think also, and I think that's most fundamental, that we feel that the culture of science, the respect for facts, of uncertainties, of having different kind of perspectives are not just scientific values, they're values that are incredibly important also for society as a whole. So what can we also do from the geopolitical framework? So what we see, science is under attack, but I think, international collaboration itself is under attack. You see in many countries, we've seen it in the Netherlands, we see it in the US, we see it in the Netherlands, you see it in Sweden, it's in many countries, that development aid is the first thing to go. So international collaboration is under threat. Of course, the way it's being addressed in the US now really catches the headlines. But I think it's also a moment where a large part of the world realizes that, we have been in some sense living under the umbrella of American generosity. If you think of certain important research initiatives, whether it's, infectious diseases in Africa or climate research, etc., some countries have been extremely generous. And I think, this is something to realize and to see, how other countries can kind of step up. So the multilateral system is a fancy word to describe the UN and all its affiliated organizations. Is under pressure too. They're seeing funding cuts. There are, undermined by many, many different countries. So the formal, I would say, the first ring of international collaboration, the political one, is under pressure. And I think that's why we, as a scientific community, being in the second ring, play a very important role. We already saw some already saw good examples in the past how the scientific community has kind of stepped up where in some sense the political one didn't dare to. So I think as scientists, we're not in the splash zone, which the politicians are, but that means that kind of the second ring can play a very important role. The International Science Council, which I'm kind of elected to lead, is kind of an interesting organization. If it had many, many iterations, but started in the late 19th century, when the academies of some large countries had the brilliant idea that perhaps international collaboration is a natural thing for science. It was interesting. It's like not only the major European countries, but both Russia and the US were part of it. And I was looking at some of the notes of that first meeting in 1900, and then they write, well, scientific contact often predates political and economic collaboration. And I think it was true in 1900. It's even more true in this time. And in fact, they were quite ambitious. I love the fact, there's just one little anecdote. One of the first initiatives was to study brain. And they were sent a letter to all the countries saying, well, we want to study the brain, but the brain is as complicated as the stars in heaven. And so each country should pick a part of the brain, create an institute, and they should form a network. And in the Netherlands, we did this. Now we created, and the oldest independent research institute is this Neurosciences Institute that still exists. So we need also, I think, imaginative and brave initiatives. We have seen the Science Council, for instance, during the Cold War started the Polar Year, which was really a way in which adversaries were collaborating on Arctic research, etc. So I think there are many, many, many examples. And finally, let me say, I think there's a special role for Europe, because this is a conference of Eurostrings. So why does Europe have a special role? I think there's a historic one. If you see how modern science developed in the 16th, 17th century, it was this very strange mix of collaboration and competition in the many European countries, like this famous Republic of Letters, of course, using the input of many other cultures and countries. And so I think, this kind of very fertile mix was extremely productive in the past. And I think, we have a tradition there. I think there are two kind of elements of strength of Europe. The first, I would say, is the fact that the European collaborative model is very open. We saw a beautiful presentation of cost, and you saw the various rings in which kind of countries can collaborate. I think this actually is a very productive model, almost like a scale model for the world. You find like-minded countries, you form various kinds of collaborations. And in a time where there are kind of superpowers in the world, I think this kind of collaborative model is a good third kind of form of alternative. So I think Europe should do this. But the second element is our values, and that might, I think, be Europe's unique selling point. I think it's not only about structure, it's also about culture. I think academic freedom, research integrity, transparency, open data, given particular young researchers a lot of responsibility. There's a very strong program, perhaps you know of this, in Europe to have different ways to assess research, this kind of, and also to think of the various roles in the scientific enterprise. So the distinction between more what used to be between research and support roles or academic or technical careers. I think there are a lot of ways in which Europe can innovate and make the scientific climate more attractive. And I think this is something that, is incredibly important. But finally, I would say that, and it's wonderful to have many young scientists here. It's good to see that you're part of this tradition, in particular, I think as particle physicist, a theoretical physicist, part of a long tradition where our community has stepped up and formed these international collaborations. And I think, we need audacious initiatives, we need fresh thinking. It would be good if all of us spent all of our time, of course, thinking about the latest development of string theory, but if you can use 1% of your energy and time in thinking about how we can address these tensions, and what role the scientific community can play, I think that will be incredibly important, and we're counting on you. Thank you very much.
A lot for a very inspiring talk, Robert. Yes, then we turn to the panel debate. We have to make some space for it. So you as the panelist to sit.
Okay. Then I will wait for Robert. Huh?
Yeah, so the intention is that this should become a good and interactive discussion. Primarily between the audience and the panel members, but of course the panel members are also really invited to challenge each other a little bit. Just to get so I will very soon throw the floor open. I think also, especially, I really invite especially the young people, and it's very nice you highlighted this at the end, Robert, to engage in this because, well, it's a platitude, but yeah, the future is yours. So I think we need precisely good ideas and remarks from the young generation. But they shouldn't dissuade the wise, slightly more mature people in the audience to also make comments. Yeah, so I will not repeat the talks, but I think there are some really interesting points raised about governance and neutrality, about openness versus security, about mobility and collaboration. Like I said, I will throw open the floor soon, but I just wanted to do a little quick round of each panel member. Because when we think about science and geopolitics, we think about that science could play different roles. And one that comes to mind is, well, just we should produce more knowledge because then we are better. There's some sort of competition. A second one is maybe more defensive, but we should use science to become more resilient and sort of shield ourselves from the rest of the world. And a third, that was also mentioned by many, is more like we should use science as a tool in diplomacy. Now, it's always a very tricky question to say what's the most important, but just to challenge you a little bit, starting with Robert and then Ronald and Mieke. Can you say something about the prioritization of these?
Well, I would say the most important thing that science does is really, improve our lives. I think that, it delivers the results. And, it's interesting looking backwards. We see this kind of tremendous examples. There are many things in the world that are less successful than they claim to be. But I think science is really an exception. I think we have over-delivered in many, many ways. People haven't been able to imagine the kind of breakthroughs and insights that we have had. So I think part of this, what I call the social contract with society, is of course that science actually delivers on its promises. And I think that should drive us, and we should also seriously think, are you doing the right things? I think, we have a real question, how can we optimize science to do all those things? It's not only, economic benefit. I think it's also like cultural benefit. It's, it's making our lives more meaningful. And all of the above, I would say. And I think that is in the end where you find support. And in my experience also, also from politics, there are many issues that divide, but science typically does not. And again, it's win-win. And if you, for instance, ask about science diplomacy, it's exactly that what makes it such an interesting tool in diplomacy. And because you can benefit in many ways in collaborating because you clearly have more brain power, but also often the issues that you're addressing, whether it's a pandemic or understanding the atmosphere or the ocean, obviously, you want to do that on a planetary scale. But I would say, we should be very proud that we can actually have truth in advertising.
Perfect. What's your take on this?
Yeah, it's all three, true at the same time. obviously. But if you ask me, of course, because I represent cost. First of all, I fully agree. You mentioned oxygen. I think that is really, the catchword to describe, how much we need science. In our experience, to see people coming together in these networks, young, old, occasionally a Nobel Prize winner, although often in retrospect, because I've been in a cost issue with somebody who 20 years later got a Nobel Prize. But yeah, that to see the spark in people's eyes. So this is truly unique because this is a network of peers, and I would never have been able to make the connection. And what is it actually that binds them? They're all seeking the truth, right? So that is I think very fascinating. Apart from that, making the connections, let's say, between scientists is one thing, but it's also something that can open, let's say, collaboration levels, between governments, between administrations. I just showed a picture from one of the missions I did to Egypt, and then people from Palestine also. Don't ask the itinerary of this person because they don't have their own airport. He has to go through Israel, then to the West Bank, and then they can go out. But at one occasion, it was the year before, I had, if you look at that map, I had the club of full members and I had the near neighbor countries. So in one single room, I had Azerbaijani and Armenian, where we know there's a history of conflict. I had a Serbian and a Kosovo representative, and I had an Israeli and a Palestinian in one room. But we were talking about science, not politics. And I think those are the moments that I say, yeah, this gives me at least a fulfillment to say, yeah, we are fulfilling our mission, maybe even more profoundly than we realize. And science is so important in this.
Beautifully said. Mickey, what is your take?
Yeah, it's a very big question, and I think my take on this is that when you start thinking about science and you realize that this is it sort of stems from our curiosity in the beginning, and then science at some point it develops into technology because our curiosity gives us means to improve our situation, our society situation. And if it would stay at that, science alone would be a very, very, very good thing. But since there's always competition, as soon as you make an invention, either your situation will become better, or you make an invention to make the other guy's situation become worse. And that's very delicate because, of course, it's just curiosity. I break this stone or whatever I'm doing. I'm starting on very basic science here. But very quickly it escalates, and the impact of science goes beyond the curiosity and sort of, let's call it the big grand goals. We had a good example here that Einstein sitting down and writing his equations and doing quite academic studies. But today, our GPS systems wouldn't work without that. There was no intention at all. I don't think he sat down first, I want to build a GPS system. How does that work? No, this evolves. And the problem with the science is this, that the curiosity brings you something at hand, but then what you do with it is the important thing. And this is hard because perhaps it's not only up to the scientists, because then you start interacting with society. And we are talking about the 20th century being fantastic for science, but you should also remember a lot of it was driven about the disasters in the early part, where we really pushed together to make sure that we could win over the other side. Not taking sides here, but this is what was the brain. But coming out of that was also the initiatives that came after the war to build the peace. So it's really hard to give a good, simple answer to this. And well, I'll end there because I can, you can spin on forever because this is such a big question, and it's a very interesting and important question to always think and look at different facets and twist and turn, because in our everyday life as scientists, we will face times where we have to make choices about what you're doing. And this is also, then you go down to also the ethics of science. So it's extremely broad question that you asked us to summarize in a minute. You're not fair.
No, well,
it's not a fair world, is it?
It's not a fair world.
I think it really drew out some very great nuances, and yeah, well, it highlighted that it's a big question with many angles. But so yeah, the floor is open to people in the audience to ask a question. If you want to address it to a particular person in the panel, you're also very welcome to do that. Yes.
So I had a question also coming back to the observation of the advantage of having different people in the same room from different countries that may not be in good terms with each other. So what are good examples where actual scientific collaborations could help reduce geopolitical tensions? And how can we ensure this in the future, especially in these times?
So if I think that is a question addressed to me. Yeah, that is of course a very big leap. So there is a meeting, and how does this link to solving a major conflict between countries? That's a big step. Okay, so I don't pretend necessarily to give you a concrete example. If I had one, it would be in the newspapers already. But what I see is that let me put it the other way around. I take the negative one. We once had a high-level representative at the European Commission, Mrs. Mogherini. And she had to go on a, let's say, a mission to Morocco. Yeah, what do we do with Morocco? Not too much, actually. We only talk about how can we block as many people coming in from Morocco to Europe. That's basically the main thing. And so how do you break the ice? How do you not go with the negative only to Morocco? How do you build a connection to bring something along? And the only thing that she could find was science. It's good that I have science in my bag because I have something to offer. And so that illustrates something that, in my opinion, science or scientific collaboration has a value that could, in the end, also contribute, even in a tiny way, to fostering good relations and a peaceful coexistence. I can give you a few other examples, but it's just one of those things, one of those anecdotes where I say, yeah, there is a value in science more than just the science. I hope that is an answer to your question.
If I can add something to it, there are many examples during the Cold War, for instance, where US and Soviet scientists, particularly I think on nuclear issues, were in close contact, and this helped a lot with the disarmament talks. Another good example is actually the relation between West German and East German scientists also during the Cold War. So these contacts were already there. So when the Iron Curtain fell, they already had those collaborations, and they could start, building from that, more deeper ways to integrate the two countries. So I think there are many examples where, there are these kind of scientific contacts that are already there. And often I think, scientists meet each other and then go up and do other things. They might go into another roles, might go into industry and politics, whatever. And then they keep the contacts, etc. So I think there are not that many areas where there are some safe spaces for scientists, for people to meet from countries that have a very difficult relationship.
Yeah.
You want to add something to it, or?
No, I'm fine.
That's good, because then I have a really tough question for you just in between. Like, you lead an institute, Nordita. So what are sort of your threshold conditions? Because I think, well, maybe the first part of the question is, to what extent should institutes be neutral? The second part is, what are sort of threshold conditions to terminate collaborations, MOUs? I mean, it's a very concrete question, but you actually gave some examples of cost handling this in different ways, in different sanctions.
So it's a very difficult question, and it's also an everyday question that we have to address. And I think when we have an institute which has a mission, in this case theoretical physics, we need to look at the individual first and see how the individuals can prosper and grow and contribute as individuals to society. Because if we look at science, one would like to have the standing point that science is something for mankind. It's not for countries or organizations. It's really something for everyone's benefit. You mentioned there are so many challenges that we can actually resolve if we are rational and work scientifically. So it's extremely important to be open in that sense. On the other hand, one cannot be naive because not everyone is kind out there. So you have to have this very subtle balance. And as if you lead an institute from the outside, the decisions you have to make might look a bit funny or hard to explain because you have sometimes some information or some things that you have to adjust to, and there's no way around. Because they are then politics enter, and of course we have to make ethical standpoints against aggressors and so on, and that would exclude a lot of institutes to work with. So I think it's called a Janus face everything, that you have two sides of of everything, and this is every day. It's everywhere in the world that you have to face. There are good things and bad things, and you have to make the right priorities based, hopefully, on having the right compass.
Thanks a lot.
Can I add something to it? Because I think it's really, it's one of these issues where I would say neither the politics nor the scientists really want to take up the responsibility. So I think setting the guidelines, with whom can we collaborate, under which conditions. Often scientists or universities say to ministries or politicians, you make the decision. But I would actually say from my own experience, they cannot, because it's too coarse-grained. It's too much of a caricature. And even the intelligence services, they worry about various things, but I don't think they have the in-depth knowledge to make these kind of decisions. And it should be fine surgery. You shouldn't bring an axe to it. And so I think my experience is, in the end, this comes back to the scientific community, because I think details matter. And to make the decision, is this something which is really crucial piece of technology that we don't want to share, or is this something which is very generic and everybody could do it? I think only the specialists who know this. So I think this will be something that will be on the plate of the scientists from the scientific community, and it should be there.
Yeah, in general terms, the red line for cost is that we are only funding networks for peaceful purposes, right? But at very high level, to make it more concrete, and I didn't want to go in my talk into the situation that we are currently witnessing in Israel and Gaza. But I can share with you, and then something that, of course, you would expect. I'm getting mails from action chairs from Belgian institutes, for example, that said, well, we decide in our action that there's no Israeli researcher anymore. And then, because my university has adopted a policy that we are no longer allowed to cooperate with Israeli researchers. And then I send a polite message back, said, well, you're receiving a grant from COST, bound to an action grant agreement, where we have certain rules of cooperation. In a polite way, better less saying, well, either you like it or you leave it, yeah, basically. So what I have not seen so far is that the collective of the members that constitute our governance, including Israel, by the way, is part of that, has unilaterally decided to exclude people from other countries. In the case of Brexit, it was more a management decision. So look, we have too much risk. So of course, I work with our governance, but okay, just to back myself. But in the case of Hungary, there was no, let's say, initiative from the members. In the case of Ukraine, to cancel out Belarus and Russia was not coming from the members. So the intrinsic, let's say, attitude is, sure, we collaborate, right? And so yeah, what we will now see in the situation what I was just referring to with Gaza and Israel, of course. Recently, the Dutch government faction of one party stepped down because of that. Will there be consequences at the European level? For example, whether there indeed will be a decision by the European Council of Ministers to take sanctions, to, for example, stop the association agreement or to freeze it, or maybe partly with the framework program. This was all mentioned. We could all read it in the newspaper. Costa has not taken the initiative. Can you imagine you have Israel in your board and then you discuss this? This is very, very, very sensitive. So if there will be a decision that says, okay, then the Commission will say, well, we now give you guidance, as it is called. So we will follow the same path as with the other examples. But we're not there yet. But it's, yeah, this is simply what is happening around us. We cannot affect it, but we have to deal with it.
Yes.
Ronald, thanks. I was going to ask you, but exactly, you answered a question I was going to ask. But let me just follow up. So in the case of the sanctions against scientists with Russian affiliations, you said it did not, this decision did not come from the members. Where did it come from then?
From the European Commission. And that was because the European Council decided to impose sanctions on Hungarian institutes where there was, let's say, an interference of government on the government side, compromising the independence of these organizations. That is the rationale that was followed. And so we receive our funding 100% from one single grant that we conclude with the European Commission. So as a matter of consistency, this translates then at the level of cost in, well, you cannot allow any more institutes that we have put on our blacklist to benefit. So any researcher that is related or affiliated to this, irrespective of their nationality or so, can no longer receive, let's say, funding. They can participate, but no longer funding. And so in that particular case, and this applies until further notice.
And do the members and researchers have a say in this at all?
No.
Okay, thank you.
No. That is the debate, of course, because the researchers, they want to collaborate. Right, so like I said, also our members, these are also countries, do not have an intrinsic motivation to start, you know, this kind of discussions leading to sanctions.
Do panel members want to follow up, or should we go? Let me go to the next question.
Right. So thanks for your interesting talks. So the title, this is on, right? Yeah. The title is the role of science in times of what was it? Geopolitical uncertainties. So I want to ask a question about the role of scientists in these times, and in particular to Robert, actually. So you said, okay, we have to, there's a social contract that there used to be that is being torn apart, and you say we should renew it. So I would like to ask you what we can do as scientists. What should we do? And of course, you're going to say, well, we should talk to the social scientists because they have expertise. But you're also kind of an expert. You have a long expertise. So I was wondering what you think we should do and where we can start.
I think actually there are many things you can do, you know, in terms of like building the trust of science. I think, you know, individual scientists can do a lot. In fact, it's interesting that, you know, research shows that if there is lack of trust, it's often in institutions particular institutions that have been much in the news, you know, making recommendations, etc., whether it's on vaccines or, you know, climate, much less on individual scientists. So I think that's really interesting starting point, you know, that science is something different than the institutions. So it's a big collective. So I think as individual scientists, you can do a lot of reaching out. I think actually, you know, there's quite a wealth of initiatives in various countries of, you know, engagement in locally and in schools, etc. So I think that this is something that we can do, that each of us can do. There are many roles to play. You know, you can write about science, show things, etc. You can be engaged in a lot of activities. I think that actually brings science much closer to people. You know, political parties often, you know, to be perhaps a bit too frank, but, you know, sometimes I feel scientists also feel they're above politics, you know, because it's like this messy thing, etc. But of course, politics cannot be above the facts. So, you know, there is, I think, also a role to engage with politicians, and particularly with politicians, I would say, of the wrong political party, you know, who are perhaps, you know, not embracing the scientific consensus. So I think, you know, I like to say we start to feel comfortable being not comfortable. And I think this is what all of us can do. We can do it in a much more organized way. And I think that's a lot of initiatives that you can take. And I think this is something that I see as an expanded role of science. It's not only that we do a terrific in research, but we also play an important role, I think, in building the support that in the end then gives the research. So, and I think you can do this also as an individual scientist, each of us in their own way. And by the way, not all of us have to do this. I think it's very important. There are those who enjoy it. And so often I say, you know, and also not be afraid to, you know, do public service. You know, I often feel that, you know, there's a real lack of scientists in circles of policies and politics because, you know, it's very messy, etc. But if one of us now and then wants to jump in, I think it would be good. In the black hole, you can survive. You can come out.
You came out on the other end, Robert.
Totally scrambled, you know, that's Hawking radiation.
Thank you.
This is a little bit off topic, but it does relate to the topic of the decreasing trust in science. So you've talked a lot about the general public, but there's also sometimes a sort of threat within. I think an example close to home for string theorists is people that came from the community that then, you know, say that string theory might not be a real science, and I think there's more examples like that, maybe in social sciences where people might not appreciate science for the sake of science so much. I know that there's a GPS example, but it's a well-used one. How do you think about mending those fractures within the scientific community of people that have fallen out and attack science from the outside, but that came from within?
Yeah, I think that's really an important question because often those, I would say, you know, in the most positive light, very fierce discussion within the scientific community are perceived from the outside as being that we don't know what we're doing. And, you know, again, you know, it's a big mess. I don't think that, you know, one strategy be to have a united front, etc. But I think that wouldn't be fair because, you know, we want to some sense be honest in the way we present science, and that there is a certain amount of discussion around topics, I think is a good thing. But I do feel sometimes, you know, sometimes you see a family, you know, on holidays that are fighting among themselves, not realizing that the whole restaurant is enjoying the conversation. And sometimes I feel we're a little bit like this. So we should, I think, you know, we should be aware in some sense that we are part of that image. And it's interesting if you see the research about trust in science. So the first thing important thing is we are still among the most trusted part in society. You know, scientists are trusted much more than journalists or politicians, in particular. And if you ask why do people trust science, it's not because they fully understand, you know, the difference between string theory and loop quantum gravity or something. It's because they see a large community agreeing at some point on things which are very difficult. So the fact that there are very difficult things that, you know, there's some sense of agreement, particularly, by the way, the fact that these are scientists from various different countries and like they build, if people are enthusiastic about the Higgs particle, it's not, I think, because they understand what the Higgs particle is. But you have 10,000 people working at CERN and they all are excited, you know, and celebrate. And that image, you know, that there is some truth and it has been discovered and it's done collectively, I think that's a very powerful image. So I think in communicating what science is, it's also very important that we communicate the scientific method, which there isn't really a scientific method, but our methods, you know. And it's also important for us to communicate that our strength is not that I think we are better human beings or something, but I think our strength, and this is actually something that the social scientists tell us, is in our collective. No, it's the way we have peer review, how we debate, how we come to a consensus on certain topics, and perhaps not a consensus on others. And I think communicating that, some sense the culture of science, is an important part, I think, of doing outreach. You know, but I think, you know, you are right that, you know, if you have very intense debates, we have to be aware that the rest of the world is looking at us.
Yeah. Any of you have?
Yeah, I was thinking a little, it's very interesting discussion and a question indeed. I mean, in the field of physics, one have different stages of the scientific development, but at the core, it's empirical, right? So we can always fall back on experiments and some kind of understanding and confirmation of theory in this case. And on the way there might be various ways. And then you have this internal debate, which actually is quite developing because you can understand and see the different angles and so on. Where it becomes difficult, where I see, or I think we all see it, is today when we have certain facts about climate, which are scientific, which are being debated and revoked because, one, they are uncomfortable. And here, then scientists can come in a very different, and science can come in a very different perspective, because if you deny climate change, for instance, or how do you work with this? You can have different interpretations, and they can be driven not only by empirical facts, but also by personal conviction. And then this is also part, because the question is much larger than let's call physics science, but the whole field of science, because that's so complex and there are so many ingredients. And when the debate comes there, then that could be dangerous for the scientists, because when do we pass over to opinions, to facts? Yeah. And this is where we're now. And I mean, there are also, you know, fake news and all this, that you can debate anything. Anything is suddenly volatile, right? You can question anything, and that has come from somewhere. And that can also come from a public distrust in an elite or a scientific community, a know-it-all community imposing things. And so what you propose there, this in the previous question, actually, I'm a little bit of a slow thinker, so I'm catching up now. But there, the point of being a part in the current debate and taking that uncomfortable step is quite important. And as you say, not everyone should do it, but those who are well posed to do it should be more open there, because we need to introduce more scientific thinking into the debate and do it in the right way, not trying to, you know, point a finger, but really get it settled into the mindset. And we have to recapture that, because suddenly it has been so questioned.
I fully agree, and I think that's what I said. You know, you you have to push back against the pushback. You know, it's a second order effect. You know, we think science is terrific and everybody is agreeing, and then you get pushback, and then perhaps you're perhaps a bit naive. So how can people push back science? You know, because isn't that the most wonderful thing there is? Well, no, we have to defend it. So we have to organize ourselves and push back against the pushback.
Question in the back, then here and then there. So yeah, we have an order now.
Thank you for your insight. I have a maybe more broad strokes question, which is you indicated a little bit the relation between science and inequality in a sort of broader sense. So you talked about this north-south divide, for instance. And I would like to, let's say, posit, I mean, certainly historically, I think we all accept that participating in science has been a matter of privilege in some sense, like very much, you know, Isaac Newton was a wealthy aristocrat, I don't remember. And even today, I would like to posit this is still the case, that there is some distinction in socioeconomic background and gender and whatever else you might have, even in wealthy countries. And that maybe actually also same with politics, incidentally. And that part of this is maybe responsible for the stigmatization and antagonization of the scientific community. And I would like to ask if you have any suggestions as to strategies as to how we can make science, not just the consumption of science, but also the participation in science more accessible, such that it becomes more of a publicly accepted good and part of ordinary life.
I think if I can start, you know, it's a very good question. And, you know, if you look at, you know, I mentioned this kind of influential report of Vannevar Bush, you know, in 1945, and it set up, you know, the modern development of science. There was one thing really missing in that report, which was that it was inclusive, you know, that everybody could join the scientific adventure. It was still a very elitist point of view. And I think, you know, one thing we have learned in science is that it's to our benefit to be inclusive. I like to say not inclusive, expansive. You know, science has to, it's not about you fitting into the system, it's the system expanding so that you can fit in. And there are many underrepresented groups, I think, in all of our societies, whether it's gender, whether it's race, whether it's ethnicity. Often the most invisible one is social economic. You know, there are many students who are first-generation students, you know, have a much more difficult time. So I think there's more insights now, I think, within universities, colleges, research institutes that we should pay a special attention to, that everybody is welcome. But I think it would go further. I mean, if we think that like research is something that only takes place at elite universities, you know, it's a wrong role of what research is. I think, you know, if you are very practical vocational training, there can still be a research component to it or something. So, you know, traditionally, you know, you mentioned, you know, some of the famous scientists in the past who become very privileged, etc. Newton, by the way, wasn't, you know, although, well, his mother, I think, you know, had some money, but it's, you know, he certainly was not an aristocrat. And traditionally, science has also been a social engine, something. And one thing that you see, for instance, very clearly in the United States, that the top universities stopped being that, right? They're very kind of self-affirming, elitist institutions. And I think this is something that's undercutting in that country, but in other countries too. The image that people have of universities, you know, it's no longer, they're no longer open for everything. And this plays a role in the dynamics in our society. But as you said, you know, at a global scale, this is happening, you know, in a much more dramatic way. So I think it's very important as a scientific community, we are aware of that. And there are many ways you can address this. You know, I always like, and of course it's now much under attack in the US and elsewhere, but this difference between equality and equity, you know, it's not about the door is open for everyone. Because if you're very far away with lots of barriers, the fact that the door is open, you know, is of very little use. Equity is to make sure that you have the same kind of opportunities to actually enter the door. And so you have to do more for those who are coming from further away. And actually, you know, some of that is set by the policies of governments, etc. But I think a lot of it is also set by ourselves. The scientific community can do a lot, whether, targeting scholarships, make sure that if you have a conference, and people have, say, young families, etc. Are you taking care of childcare? There are lots of things you can do to avoid making it a very exclusive thing. And I think the good news is over the past decades that we at least become more sensitive to it. But I think still there's a lot of things that we can improve. And I think, again, if we talked about the geopolitical tensions between the big power blocks, but I think the tension that's between North and South, is as important. We haven't discussed a lot about it, but like international aid is being cut across the world. It's the least popular thing in political parties, and it makes a tremendous impact on the world. And I think, as a scientific community, you should be very open to this and see what we can do. And with a very little money, you can do a lot.
Yeah, just because this is about this equality and inclusiveness, and how do you actually, counter this? And I can share with you that with cost, we have a specific policy, an excellence and inclusiveness policy. I just earlier on showed you a picture of the map with the full members with more research intense and less research intense countries, even with 2 color codes. We have a requirement that comes with the grant that we receive from the commission that at least 50% of the money that is given to researchers lands in the pocket of less research intensive countries. So we have specific mechanisms, let's say, by setting certain criteria at the proposal stage or also in the evaluation stage with some extra supporting measures to achieve that. And the bulk, let's say, it's about 70-30, so 70% comes from the research intense countries. So you have to really find a mechanism without, and that's what we have always tried and maintained successfully, without interfering in the freedom for the action to organize itself. So we don't tell a specific action, you have to do this, but we organize it in such a way that these people can contribute, that they are invited, because it is a misconception, but now I'm riding the horse a little bit of cost, that there's no excellence in those so-called, less research-intensive countries. There's excellence everywhere, pockets of excellence. The thing is, how do you connect them? How do you bring them together? And once, at least in cost, they are in a network, they have the same opportunities, but also the same equity. And that is, I think, one of the ways to do it, to make sure that we have, let's say, a capitalization on all the talents that are available in Europe. And that not just as in the wider framework program of the European Union, there's always a specific club of institutions or research organizations and universities, that know how to play the game. They have the money to invest into putting proposals forward, that they always are amongst the winners. That is a little bit, of course, what we need to counter in that sense. So yeah, that's a different angle, but it's also alluding to inclusiveness.
Okay, I'll try to be quick. I know there are other questions. I just would like to ask. So you talked a lot about the conflicts and the mistrust, what actually the situation is at the moment, and a lot of blame is usually posed on the political environment, policies, and people in power. But is there anything that you think the community itself should look back and perhaps recognize that could have contributed to actually this situation, and actually recognize it in order to avoid it in the future? Is there anything that we have done wrong?
Well, if I can start, I think perhaps, as I said, we have become a little bit not spoiled, but demanding this kind of support without feeling that we have to do anything in return. And so I think this is something that I feel this a little bit like a wake-up moment. I think it's good for science in the end, but that you have lost contact with part of society, or whether it's the political circles or just public in general, it's just a fact. And I think in retrospect, we could have perhaps done more in kind of doing this kind of public engagement. And of course, it's a very difficult question, but probably there are lots of missed opportunities right now. So I think it's a really good question. And one thing I noticed that we saw some good examples of really, I would say, very imaginative initiatives in the past, bridging, in a very complicated world. It's not that the world, in the 1950s or 60s was all easy, etc. It was all high tension, etc. And people were able to think not only about their research, but also how the research was organized, I think. And I feel we should perhaps haven't thought enough about the architecture of the whole research enterprise. And I think this is kind of a moment that you look at the building and say, wait a moment, we can do it in a smarter way. And I think there are many ideas. But I feel there is some kind of maintenance that we didn't do and that we now have to do.
Yeah, there is some risk in public engagement, of course, because during the time of COVID, in the end, it were politicians, of course, that had to make very difficult decisions on what measures to take. And more often than not, gradually, we have seen, of course, scientists being put to the forefront to basically explain the situation and how bad things were or not, and how much risk. But that was immediately then connected to decisions that could be arbitrary, but not necessarily, let's say, scientific, but of course policy driven. And that was, of course, something that led to situations of lockdowns. And the risk that you actually introduced there is that indirectly, lockdowns are associated with scientists. So there has been a big backlash. And at the same time, and that's the paradox, science has helped us to get out of this pandemic. Yeah, with these RNA vaccines. So it's I think no option not to engage. We should engage. We should push back. Robert, I think also in your words. But it comes with a risk. So where is the policy engagement and where does it stop? Because we've also seen, I live in Belgium now for the last years, with a very, let's say, communicative scientist who was at the forefront, but at a huge personal cost of threats and law cases against this person personally. So suffered a lot because of that. So this is a bit of an extreme example. That's the society that apparently we are living at the moment.
If I can just say one word about it, because I think COVID is a wonderful example, where on the one hand, as you said, delivery of vaccines was tremendous success. So I thought that actually was the Sputnik moment of our days, that people would all say, well, we see the value of science. But I think you're quite right to saying that, at some point, science can show various paths and see what are the results if you choose a certain path. But the decision which path to take is a political decision. And so another lesson, I think, would be don't get framed by politicians as being responsible for certain choices. I think because that's just what happened. And at some point also be careful where you cross this divide. You go into the black hole horizon, I think. And that's where, because the decisions are actually political decisions and they have to be taken democratically, and this is not something that science can do.
Yeah.
In some sense, I think you alluded to that in your presentation, is we are a bit a victim of our own success, and in particular after post-World War II, because the delivery from science to society has been enormous in new technologies, new discoveries that have been very quickly put into use with enormous, and this has, with the growth of population in science, this speed has grown. But of course, it's a political decision what to fund and so on. And perhaps this has been seen a little bit like a possibility that we put down some money there and we know what we get back and so on. So the policies perhaps have been driven on wrong expectation and a mismatch of timescales. Now I'm becoming scientific, right? Because science doesn't have a clear timescale in a sense. Now, the vaccine was special. There was a very urgent and there was a very strong thrust, and probably a lot of the ideas were half mature already, right? But in the long term, we are looking, so the EU put this flagship notion, and I was a little bit involved in that, and we have a 2D material, and what happens? The scientists and we start promising a lot of technology and okay, let's put $1 billion into it. Let's see what we get back. And of course, then it's written, not that a lot got it back in form of technology, but the evolvement of quantum materials and what we can do with this material has grown fantastic. And it's just an enormous explosion, but there's no cashback yet. And being part of actually the administration and running of the flagship, I realized that we were actually lab rats in the EU's way of thinking on how to fund science. So we had weekly meetings and okay, we changed that, what happens there? It was quite interesting. So there is a funny reaction with the politics wondering, okay, how do we make as much bang for the buck? So they have mostly an honest goal. It's sometimes you polarize it with the scientist in white armor and then the politicians in the black hole, as well. You want to put it. But one has to realize that in a sense, we are a bit, we have made our own problem by being very successful. This is funny because we should be proud of that. But the expectation of our delivery is perhaps overrated in a sense, which is it sounds very negative to the science, but you expect a quick turnaround in the invested public funding that goes into science, and that won't happen, I think. And there's a mismatch, and policies makes it worse because, it's not the right driving, always the right driving force.
On a slightly lighter note, I have a sort of rhetorical question for Robert. If one jumps in a black hole and comes back on the other side after a scrambling time, do you think they should again try to fall back in the black hole at some point?
Well, you never say never, but no, I think actually, honestly, I found being in government incredibly worthwhile. Because, one thing you definitely cannot say that it doesn't matter. Because, as a minister, you make decisions, etc. And I also had an experience that as a scientist in politics and government, you have a special role to play. You have a slightly different way of communicating with Parliament. You probably are not selling a political point of view. You want to understand things, and so one thing I felt, that I've really missed in politics. So what we would have if we would discuss this as an issue, we would say, well, let's clean the blackboard, and can somebody just explain to me why are we discussing this, right? And that's like a nice summary talk or something. That would be the first thing to do. Usually people do not do this in politics. They take action. Why? Because last week they did this, that, and this, that report, and that, motion in Parliament, etc. And I think there's tremendous need and demand for these kind of moments. So I think, science can play a very important role just by asking fundamental questions. You know, why are we discussing this? You know, what are we optimizing? You know, what is exactly, you know, for instance, many of the problems in politics are over-constrained. People don't realize that, you know, they want to optimize 10 different things and they have only 3 dials. So even to explain this concept was very new to many people. Yeah. That you have more constraints than variables. So there are a lot of kind of things that you can do. Now you can do it as a minister, but you can also do it by just helping politicians, etc. So I think there's a real lack of scientific thinking in politics, was my experience. And even though those who were dealing with like scientific issues, often the arguments were political arguments. You know, I can find a majority for this or a majority for that. Well, I think, you know, the great thing that a science background tells you, that you first want to understand the issue and then you want to explain it. And in fact, you know, that's often a way to also bring, as I said, you know, science brings people together, but I think a scientific way to approach also political issues can bring people together, and there's a real need for that. So I hope perhaps some of you will jump into black hole. Could be a micro black hole, you know, you might already be in it.
For those of you who would enthusiastically follow the suggestion of Robert, just bear in mind that science is about finding the truth, but democracy is about finding majorities. And they're not necessarily compatible.
Yeah. Yeah, I think you're quite right by addressing I mean, there are many pressures in some sense that work against, you know, the openly sharing, you know. And I think you said quite rightly, you know, that we have seen the values of sharing. You know, you mentioned the vaccines. So, you know, clearly by sharing that information was extremely important in getting the vaccines fast. And then, of course, it was very disappointing when it was the distribution of vaccines that is kind of this generous sharing attitude was not there. And as you said, you know, many economic arguments that now work against sharing. So again, it's a tricky thing where I feel, you know, it's a trade-off, but I see many of the forces, and they're quite strong, are in the, you know, trying to close things off. Because it's either a risk, you know, it might be seen as a very generous risk, you know, it's in private companies, etc. There are a lot of things that are somehow getting more and more shielded. And I think, you know, the scientific community plays a very important role in pushing the other direction. And as I said, one way to do this is to make these decisions more scientifically informed. You know, I was part of a discussion where people said, you know, anything related to quantum is, you know, have to be secured or something, you know. And I was like, well, wait a moment, you know, the whole world, oh, reality is quantum. How can you? But that's just because these are caricatures. Often in people's mind, they think, oh, that's a key technology that will, will lead to huge security risks. So I think it's very important, that those who make these decisions are informed, that the scientific community plays a certain role. But as I said, there's this balance. You also don't want to be naive, and clearly, our technologies are becoming more and more powerful. They become more and more influential, get more and more impact on everything. So there's more and more interest. So you have this very powerful tool, and obviously, you have to be a little bit more careful how to share it, etc. So I think it's a very important role for the scientific community. And I think one thing we should do, as I said before, we have to inform, particularly train young scientists, to be part of that conversation, be proactive, and don't leave it to other forces to do so. Because if you leave it to industry, or you leave it to politics, or to intelligence or security services, they will all often try to close off, while we see the benefits of opening up. So if you're not engaged in that conversation, you don't have this kind of balanced point of view. So I think that's one of the lessons I learned, is that how important it is that you have these conversations within the scientific community. And important thing is also to determine which areas are safe to collaborate, right? Because if you create a lot of uncertainty, like, oh, there's geopolitical tension, everything can be stolen, that's a very kind of silly point of view. That's a vast caricature of how the world is. There are huge areas where it's totally fine to collaborate, where you need the data, etc. And we should also be very clear as scientists to indicate that that's totally safe to collaborate.
Okay. Well, first of all, thank you so much for the discussion and your contributions. It's been very interesting. I just wanted to ask about your opinion on the impact that the current situation in the US, like the attack to science and so on, could have in Europe. Like whether you have, because there are two options. No, I could see that we could have a risk of going on the same direction, that more, I don't know, at the political level, that we could try to copy and follow some of the things that are already happening there, or maybe the other way around, like maybe there's a counter reaction in terms of policies of defending more and more science. So I was curious whether you have already witnessed any pressure on going one direction or another in Europe.
Can I say something about it? Yeah. So I think you're already pointing out some of the important ingredients. So one thing I think is that often these political forces that you see in the US, they are also operating in Europe, perhaps less pronounced. So it's very good to take notice and see what you can do to prevent situations like that. And in fact, in some way, perhaps, it can be a positive force, because, people see the negative impact. We saw that a little bit with Brexit. I think, the big mess that was created by Brexit stopped the discussion of an exit of the European Union in many other countries, because you see an act of self-destruction and you feel, well, no, I shouldn't go in that direction. So failed experiment is also important. So perhaps this could be a positive thing. But I don't think we should underestimate that the damage that is currently in the US, and nobody knows what the final situation will be. Budgets are still being negotiated, etc. But of course, the US always has been a tremendous service to European scientists. I think many of us have spent time there. If you go to a big US university, you find people from all over the world. So the US has been playing a very important role also in supporting the global scientific enterprise. And so if things go wrong there, we all suffer. So I think actually, it's a very important moment also for Europe, for instance, to stand up and do more. If only to compensate, for there will be just lack of postdoc positions, etc. So, there has been some initiatives in Europe to attract, say, top talent out of the US. I find this a little bit sometimes discomfortable. I think it's more important that if there's just, might be temporary, but if there's a lack of positions for young people, that, Europe should step up and create more positions so that, this will not be, that a whole generation might get lost. I think there's a serious risk for that. And if international collaborations are undercut, then other countries should step up their efforts. So I think in general, if one country is not going in the right direction, I think we all suffer because it's one global community. But I think it should be something that should be an argument for other countries to do a little bit more. And as you said, also make sure that these crazy dynamics, which partly I think very special to the United States. It's a very volatile country. We'll have the best and the worst, and often, very often next to each other, both in time and space. But it's clearly something that you see at least the kernels of it, also in European countries. And like in the Netherlands, there's some political parties that are really echoing the same kind of crazy stuff. Setting the consensus on climate as a way, as activism. It's in some sense the same playbook. So yes, I think this is something that you should observe and learn lessons from.
Yeah, I couldn't help thinking about an initiative that the Commission via the ERC took to introduce specific grants to attract researchers from the United States to Europe. The thing is that they doubled the size of the grant in order to attract US, let's say researchers who are used to a bigger paycheck. And we have just said, yeah, Europe is fantastic in science. There's a bit of a parallel. Why do we need those people? By the way, they're getting paid twice as much as we do. And so there's a lot of competition in the ERC for grants. So you have to be my point is you have to be very careful how you do it. I give no judgment, let's say, of this. I refrain from that. But it is something that, of course, the other way around, we've always pointed at. At the time, Niels Bohr and Einstein and Oppenheimer, and they went to the United States, but they went there for other reasons. So I'm a little bit skeptical about, and to what extent, what we could do. In any case, you can join COST. It's open to the world, Come over here. And by the way, if you don't know anyone, join a COST network. You have many friends, in no time. So thanks.
You have any?
No, of course, this is extremely important. And I think that what we are suffering from is when you have this very extreme movement, but it has been going on for some time, is that when you are exposed to it, it becomes normalized. And we see also in places where we believe that we are safe from it, that there is political movement to interfere with academic freedom or the freedom of universities. And it again goes back to the question that we from the public, we see that universities are very important in designing our society and helping and so on. But that means that it can also work for implementing things that we don't want actually to be implemented. So the way we have migration and this north-south and so on. You can start emphasizing differences and why not to integrate and so on. And we see that even in a country like this, where they come directions from leading posts that we should start looking at these things. And this is very worrying because this openness and we were talking about inclusion and making it possible for everyone to enter science. I think in small countries like Sweden, when you have a very small recruitment pool, let's say to the technical universities. So I'm a professor at Chalmers when I'm not here. There one realized that there was a very small part of Gothenburg, which is a city of 500,000, where the recruitment to a whole technical university was made. There was no inclusion of people of non-Swedish background. females, people without glasses, and so on. There was a lot of exclusion. So it meant that we tried to make an excellent, drive excellence, explore science with a fraction of the potential of the area. And if this is not mismanagement, what is? So it's extremely important. And if there are movements in society that want us to narrow down and exclude and so on, I think it's extremely important to engage, as you say, and perhaps almost make a new civil movement on this. And this becomes a bit, this was more in the 60s, but then, you know, society was on an extreme upturn, right? Everything was going, people were going all over the world, helping developing countries. Turns out that Niels and I have been in developing countries as young, where our parents, who were the children of just the post-war generation, they were going all over. They were following Kennedy's moves and so on, that they were really engaging in making the world better. But now it has turned, and now we're closing in, and we have to really be aware that we don't get, it cannot become normalized to think in these ways. And it's really scary with the US, because attacking full front what is so important for democracy and well-being for mankind is really sad.
Okay. On that note,
okay.
the time is up.
You can start singing to cheer up people.
I think, yeah, it has been a fantastic debate. We have really been all over some really important subjects. I think there are plenty of take-home messages for everybody in this room, young, old, coming from any direction. I'm really sorry for some of the people who still had topics, but yeah, we have reached the end time of this event. But I really want to thank the three eminent speakers here for their input and the very enlightening and thought-provoking debate. So I'll give them a big hand.